Welcome. I'm Bob Sedgwick, Professor of Computer Science at Princeton. This is our online course, Algorithms, developed by myself and Kevin Wayne here at Princeton. We're going to start with an overview, discussion of why you might want to study algorithms, and then a little bit of discussion about the resources that you need to take this course. So what is this course? It's an intermediate level survey course on algorithms. We're going to concentrate on programming and problem solving in the context of real applications. And our focus is going to be on two things: algorithms, which are methods for solving problems, and data structures, which store the information associated with a problem and go hands in hand with algorithms. These are the basic topics that we'll cover in Part 1 and Part 2 of the course. The first part is data types, sorting, and searching. We'll consider a number of data structures and algorithms that are basic to all the methods we consider, including stacks, queues, bags, and priority queues. Then we'll consider classic algorithms for sorting, putting things in order. That's quicksort, merge sort, heap sort, and radix sorts. And we'll consider classic methods for searching, including binary search trees, red-black binary search trees, and hash tables. The second part of the course is for more advanced algorithms, including graph algorithms, classic graph searching algorithms, minimum spanning tree and shortest paths algorithms, algorithms for processing strings, including regular expressions and data compression, and then some advanced algorithms that make use of the basic algorithms that we developed earlier in the course. So why should one study algorithms? Well, their impact is very broad and far-reaching. From the internet to biology to commercial computing, computer graphics, security, multimedia, social networks, and scientific applications, algorithms are all around us. They're used for movies and video games, for particle collision simulation. They're used to study the genome, and all manner of other applications. So that's one important reason to study algorithms. Their impact is broad and far-reaching. Algorithms are also interesting to study because they have ancient roots. The first algorithm we studied goes back to 300 BC, dating at least to Euclid. The concept of an algorithm was formalized actually here at Princeton by Church and Turing in the 1930s. But most algorithms that we consider were discovered in recent decades. In fact, some were discovered by undergraduates in a course like this. And there's plenty of other algorithms waiting to be discovered by students like you. The main reason that people study algorithms is to be able to solve problems that could not otherwise be addressed. For example, in the first lecture, we're going to talk about the network connectivity problem, where the problem is, given a large set of items that are connected together pairwise, is there a way to get from one to another with a path through the connections? As you can see from this example, it's not clear whether or not there's such a path. We need a computer program to do it. In fact, we need an efficient algorithm to do it. In this case, the answer is that there is such a path. Another reason to study algorithms is for intellectual stimulation. Algorithms are very interesting objects to study. Don Knuth, who wrote several books on algorithms and was a pioneer in the field, said that an algorithm must be seen to be believed. You can't just think about an algorithm, you have to work with it. Another quote from Francis Sullivan says that great algorithms are the poetry of computation. Just like verse, they can be terse, elusive, dense, and even mysterious. But once unlocked, they cast a brilliant new light on some aspect of computing. Algorithms are interesting for intellectual stimulation. Another reason many people study algorithms, and I suspect many of you, is it's necessary to understand good algorithms, efficient algorithms, and good data structures in order to be a proficient programmer. Linus Torvalds, who created Linux, says that the difference between a bad programmer and a good one is whether he considers his code or his data structures more important. Bad programmers worry about the code. Good programmers worry about data structures and their relationships, and I might add, the algorithms that process them. Nicholas Wirth, another pioneer in computer science, wrote a famous book called Algorithms plus Data Structures equals Programs. Another reason nowadays to study algorithms is that they have become a common language for understanding nature. Algorithms are computational models, and algorithmic models are replacing mathematical models in scientific inquiry. In the 20th century, scientists developed mathematical models to try to understand natural phenomena. It soon became clear that those mathematical models were difficult to solve. It was difficult to create solutions to be able to test hypotheses against natural phenomena. So more and more and more nowadays, people are developing computational models where they attempt to simulate what might be happening in nature in order to try to better understand it. Algorithms play an extremely important role in this process, and we'll see some examples of this in this course. Another important reason is that if you know how to effectively use algorithms and data structures, you're going to have a much better chance at interviewing for a job in the technology industry than if you don't. So here's a bunch of reasons that I just went through for studying algorithms. Their impact's broad and far-reaching. They have old roots and present new opportunities. They allow us to solve problems that could not otherwise be addressed. You can use them for intellectual stimulation to become a proficient programmer. They might unlock the secrets of life in the universe, and they're good for fun and profit. In fact, a programmer might ask, why study anything else? Well, there's plenty of good reasons to study other things, but I'll submit there's no good reason not to study algorithms. So for this course, we have two resources that I want to talk about and make sure that people are familiar with before entering into the content. This is a publishing model that Kevin Wayne and I developed and have been using for many years, and we think it's a very effective way to support the kinds of lectures that we're going to be giving in this course. Down at the bottom, and it's optional for this course, we have a textbook. It's a traditional textbook that extensively covers the topics in the course. In fact, many more topics than we can present in lecture. And then supporting that textbook is free online material that we call the book site. You can go to the book site to see the lecture slides, but more important, there's code, there's exercises, there's a great deal of information there. In fact, maybe 10 times what's in the book, including a summary of the content. So during this course, you'll be referring to the book site frequently while working online. People often ask about prerequisites. We're assuming that people who take this course know how to program. They know the basics of loops, arrays, functions. They have some exposure to object-oriented programming and recursion. We use the Java language, but we don't dwell on details of Java. We mostly use it as an expository language. We do some math, but not advanced math. If you want to review the material that we think is prerequisite to the material in this course, you can do a quick review by looking at sections 1.1 and 1.2 of the book, either at the book site or in the textbook. If you want an in-depth review, we have a full textbook called An Introduction to Programming in Java, an Interdisciplinary Approach. There's a book site and a textbook as well. But the bottom line is you should be able to program. And the quick exercise to get ready is to write a Java program on your computer, perhaps using our programming model as described on the book site. We'll provide much more detailed information on that as we get into the assignments. You can use your own programming environment if you're comfortable with one, or you can download ours. We have instructions on the web about how to do that. Welcome back. Our topic today is algorithms for processing undirected graphs, which are a model that are widely used for many, many applications. We'll see plenty of examples, and then we'll look at three fundamental algorithms for processing undirected graphs and consider some of the challenges of developing algorithms for this kind of structure. So as introduction, we'll take a look at the basic ideas behind undirected graphs and applications. What is an undirected graph? The definition is very simple. It's a set of vertices connected pairwise by edges. So this is an example of an undirected graph that describes the Paris metro. You've got stations, and if there's a rail line between the stations, there's an edge. So why do we study graphs and graph algorithms? Well, there are literally thousands of practical applications where graphs are an appropriate model, and we'll take a look at a few others in just a minute. Because there are so many applications, there's literally hundreds of graph algorithms known, and these are sometimes quite sophisticated, as we'll see, and also very important in understanding what's going on in an application. Even without the applications, graph is really an interesting and broadly useful abstraction to try to understand. It's so simple to describe, but leads to quite complex and difficult to understand structures. And in general, graph theory and graph algorithms is a very challenging branch of computer science and discrete math that we're just introducing now. So here's an example of a graph in genetics or genomics where it's a network where the nodes are proteins and the edges are interactions among the proteins. And genomicists are trying to understand how these biological processes work, need to understand the nature of connections like this. Here's another example, the internet itself, where every node is a computer and every edge is a node, a computer or communications device, and every edge is a connection. And of course, the internet has grown by leaps and bounds, so this is a huge graph. And there's a lot of need and a lot of interest in understanding properties of this graph. This is a social graph having to do with the way science is carried out. So it's the nodes are scientists' websites, and the edges are clicks connecting one to another. And this one shows how scientists in different fields are interacting. And again, interesting and important to understand properties of this graph. You're certainly familiar with Facebook. That's one of the hugest, one of the biggest graphs. It's absolutely huge, and it's always changing. It's very dynamic, and people want to understand its properties. This is an example of a graph that was used in litigation, where people were trying to understand exactly, precisely, the communications patterns in a particular corporate culture that was of great interest to many people. Another similar example, this is people lobbying the FCC and how are they connected. So from the breadth and variety of these examples, you can see that number one, graphs a very general model, and number two, graphs can be huge. This is another one showing the Framingham Heart Study and connections among people in the study and how it relates to obesity. Those examples in this list shows that graphs are very flexible and very dynamic model, and that the graphs involved can be huge, they can have complex properties, and so our challenge is to try to figure out efficient algorithms that can give us some insight into the structure of graphs like this. That's what we're going to be talking about for the rest of this lecture. So now back to a starting point, which is we need some simple and clear and specific definitions about basic terms that we're talking about, and then we'll look at algorithms that work for small examples, but also the same algorithms do what we need for big graphs of the type that we just considered. So this is the terminology that we'll use for graph processing. So we have a vertex, which is a black dot in this graph, and an edge, which is a black line connecting two vertices, and then a few more concepts that are important in many applications. So one is the idea of a path. That's just a sequence of vertices connected by edges. And the idea of a cycle, which is a path whose first and last vertices are the same. So over on the left, you can see a cycle of length 5 that connects these 5 vertices. And wherever you start, you get back to the same place. So we say that 2 vertices are connected if there's a path between them. And then that definition leads us to the idea of a graph dividing up into connected components, which is subsets of the graph where each pair of vertices is connected. And so one of the algorithms that we're going to look at today is one for identifying connected components in a graph. So that's just one example. So here's some examples of problems that might arise in graph processing that are easily understood just giving these basic definitions. So very first one is, given 2 vertices, is there a path connecting those 2 vertices? Like in the internet graph, you want to know, can I get from where I am to where I want to get? Or maybe you want the shortest path, the most efficient way to get between 2 vertices. You might want to know, is there a cycle in the graph? If the graph maybe represents electrical connectivity, a cycle might represent a short circuit. You would want to check for that. Or maybe you want to systematically go everywhere in the graph. So there's 2 related problems called the Euler tour and the Hamilton tour. Euler tour is there a cycle that uses each edge exactly once? Can I go around the graph and touch every edge in it? Or one called the Hamilton tour, which says, well, I'm really just interested in getting to the vertices. Is there a cycle that uses each vertex exactly once? Or basic connectivity problems. So you want to know, is there some way to connect all the vertices? Is there a path between each pair of vertices in the graph or not? Or you might want to know what's called the minimal spanning tree, which is the shortest set of edges, or the best way to connect all of the vertices. And then various processing issues related to connectivity. For example, is there a vertex whose removal disconnects the graph? Drawing the graph. Can you draw the graph in the plane with no edges crossing? Some of the graphs, the nodes are correspond to places in the plane or cities on the earth or whatever, but some of the other graphs are very abstract, may have nothing to do with geometry, and you might want to know, can you draw it with no crossing edges? Or you might have 2 graphs and the vertex names are different. Do they represent the same graph? So one of the biggest challenges in graph processing that we'll address today in this lecture somewhat is just to decide how difficult are these problems. Some of them are very easy, some of them are very difficult, and some of them actually is unknown how difficult they are. There's such a broad variety of problems that are simply stated. One of the first things that we have to be aware of when doing graph processing is that we are entering into a forest of all different possibilities, and we have to be careful that we're working on a problem that we can solve. And we'll try to give some insights into that during the lectures that we give on graph processing. So that's our introduction to graph processing. As we'll see in a little bit later in the lecture, the way that we're going to set up our graph processing algorithms is to develop an API to cover our representation of the graph and provide a simple set of methods for clients to call to process the graph. So let's take a look at that in detail. The idea is we have to represent a graph within the computer. One of the first things to remember is that you can draw a graph and maybe that provides some kind of intuition about the structure. But you could have 2 drawings that represent the same graph that look pretty different. So one of the things to remember in any graph representation is it can give you some intuition, but that intuition may be misleading. And we'll just remember that as we look at different representations. So first thing is how to represent the vertices. So what we're going to do in this lecture is just use integers between 0 and v minus 1. And the reason we do that is that it allows us to use vertex indexed arrays within the graph representation. And we understand from earlier algorithms lectures that we can use a symbol table to convert names to integers with a symbol table. And so we'll leave that part as a symbol table application and just work with graphs with vertex names between 0 and v minus 1, where v is the number of vertices. Now, we have to remember when we're doing representations that we can have various anomalies in the graph. So we draw edges, but actually in real data we might have multiple edges, or we might have a self loop, and we'll take that into account when we look at the representation, graph representation. So here's the API that we're going to use. So again, our graph processing algorithms are going to be clients of this API. The idea is that we'll use this to build graphs, and then our processing programs will be a client of this program, and it's of this API. And the idea is that most of them have just a few very simple operations that they need to do, and those are the ones that we put in the API. So we have two constructors, one that creates an empty graph with v vertices, another one that creates a graph from an input stream. Then the basic operation for building a graph is just add edge, so that adds an edge connecting two given vertices v and w. The basic operations for processing a graph, well, there's v and e that gives the number of edges and vertices, but then there's an iterator that takes a vertex as argument and iterates through the vertices adjacent to that vertex. All our graph processing can be cast in terms of this iterator. So down here is an example of a client program that prints out every edge in the graph. So we create an input stream, maybe with a given file name, create a graph from that input stream, and we'll look at the code for that. And then the client program for every vertex. So remember, the vertices are numbered between 0 and g dot, the number of vertices minus 1. So for every vertex, we iterate through all the vertices adjacent to that vertex and print out an edge. If there's an edge connecting v and w, we print out v and then a little dash to indicate an edge, and then w. This actually prints out every edge twice in an undirected graph, because if v and w are connected by an edge, then w appears in v's adjacency list and v appears in w's adjacency list. So here's an example of running that client. If we have a file tinyg.txt, our standard is we have the number of vertices as an integer in the first integer in the file, number of edges as the second integer in the file, and then pairs of vertex names. And so the constructor will read those two things and then call add edge for all of these pairs of things, and that enables this client to, if we run it for that graph, to print out all the edges. So everybody adjacent to 0, 6, 2, 1, and 5. Everybody adjacent to 1 is just 0, and so you notice the edge 0, 1 appears twice in the list. So that's the sample client of our basic graph API. And so here's some typical and simple graph processing code that uses the API. So you can write a static method that takes a graph and a vertex as argument and returns the degree, the number of edges that are number of vertices that are connected by an edge to v. So all it does is set a local variable degree to 0 and then iterate through all the vertices adjacent to V and increment that and return it. Similarly, you can compute the maximum degree of a vertex in a graph. And that's for every vertex, compute the degree and find the biggest one. Or the average degree. Well, the average degree, if you think about it, it's just twice the number of edges divided by the vertex. Or you could go through all the way through every vertex and edge and compute the total and divide, but this is probably a much more efficient way to do it. Or say number of self-loops. And so that involves going through the whole graph for every vertex, for every edge adjacent to that vertex. You check whether it's V, if it's got a self-loop. And if it does, then you return the number of self-loops divided by 2, because every edge is counted twice. So those are examples of static methods that a client might use, and just an example of the use of the API. So now, how are we going to implement that? That's our usual standard of let's look at some clients, and now let's talk about a representation that we can use to implement the Graph API. So one possible representation is set of edges representation, where for every edge we just maintain a list, maybe an array of edges or a linked list of edges. So for every edge in the graph there's a representation of it. And that one is a possible representation, but it leads to inefficient implementations, much less efficient, that it would make it unusable for the huge graphs that we see in practice. Another one's called the adjacency matrix representation, where we maintain a two-dimensional V by V array, so a Boolean array, 0, 1, or true or false. And for every edge VW in the graph, you put true for row V in column W and for row W in column V. So there's actually two representations of each edge in an adjacency matrix graph representation. So you can immediately, given V and W, test whether there's an edge connecting V and W. But that's one of the few operations that's efficient with this representation, and it's not very widely used, because for a huge graph, say with billions of vertices, you would have to have billion squared number of entries in this array, which is going to be too big for your computer, most likely. So this one actually isn't that widely used. The one that is most widely used in practice, and the one that we'll stick with, is called the adjacency list representation. And that's where we keep a vertex indexed array, where for every vertex we maintain a list of the vertices that are adjacent to that. So for example, vertex 4 has 5, 6, it's connected to 5, 6, and 3, so its list has 5, 6, and 3 on it. Now, in lower level representations, we'd talk about using linked lists or arrays for these, but actually in modern lingo, with the background that we built with algorithms, what we're going to use is an abstract data type, our BAG representation for this, which is implemented with a linked list, but we don't have to think about it when we're talking about graphs. We keep the vertices, numbers of the vertices that are adjacent to each given vertex in a bag. And we know that we can implement it such that we can iterate through in time proportional to the number of entries, and the space taken is also proportional to the number of entries. And that's going to enable us to process huge graphs. So here's the full implementation of the adjacency list graph representation. The private instance variables that we're going to use are the number of vertices in the graph, and then a array of bags of integers. Data type's a set of values, set operations on those values. So those are the sets of values for a graph. So here's the constructor of an empty graph with v vertices. We keep the value v in the instance variable as usual. Then we create an array of size v and of bags of integers and store that array as the adjacency array of the graph, adjacency lists array. And then, as usual, when we create an array of objects, we go through and for every entry in the array, we initialize with an empty object. So after this code, we have v empty bags. And so that's the constructor, and then the other main engine in building graphs is add edge. And so to add an edge between v and w, we add w to v's bag and we add v to w's bag. That's it. And to iterate through all the vertices adjacent to a given vertex, we simply return the bag, which is iterable. This is a nice example illustrating the power of abstraction because we did the low-level processing that's involved with our bag implementation in one of the early lectures. And now we get to use that to give a very compact implementation and efficient implementation of the graph data structure. So it's really important to understand this code, and you should make sure that you study it. So as I mentioned, in practice, we're going to be using this adjacency list representation because all the algorithms are based on iterating over the vertices adjacent to V, and this gets that done in time proportional to the number of such vertices. So that's number one. And number two, in the real world, the graphs have lots of vertices, but a pretty small vertex degree. Number one, we can afford to represent the graphs when we use the adjacency list representation, because basically our space is proportional to the number of edges. And number two, we can afford to process it because our time taken is proportional to the number of edges that we examine. With the array of edges representation and the adjacency matrix representation, it gets very slow for some very simple tasks, but mostly it's very slow for iterating over the vertices adjacent to a given vertex, which is the key operation. List of edges, you have to go through all the edges to find the ones adjacent to a given vertex. Adjacency matrix, you have to go through all possible vertices adjacent, and that's just going to be much too slow in practice because adjacency list gets it done in time proportional degree of V, which is much smaller for the huge graphs that we see in the real world. So that's our basic API. Next we'll look at some algorithms that are clients of this API. Now we're going to look at depth-first search, which is a classical graph processing algorithm. It's actually maybe one of the oldest algorithms that we study, surprisingly. One way to think about depth-first search is in terms of mazes. It's a pretty familiar way to look at it. And so if you have a maze like the one drawn on the left, you can model it with a graph by creating a vertex for every intersection in the maze and an edge for every passage connecting two intersections. If you're at the entrance to this maze and you want to find a pot of gold somewhere, what you're going to need to do is explore every intersection or explore every edge in the maze. We're going to talk about the explore every intersection option. So that's our goal, is to have an algorithm for doing By the way, this is a famous graph that some of you might recognize. That's the graph for the Pac-Man game. Okay, so one method, classic method that predates computers for exploring a maze is called the Tremo maze exploration algorithm. The idea is to think about having a ball of string. And what you do is, when you walk down a passage, you unroll the string behind you, and you also mark every place that you've been. So you actually have a ball of string and some chalk maybe. So in this case, maybe we walk down this passage here, and now we have some choices about where we might go. So say we go down here, so we unroll our ball of string and mark it. And so now the next time at this intersection we have no choice but to go up here. We go up here and we see, oh, we've already been there, so we're not going to go there. And we come back and we have our ball of string so we can unroll it to figure out where we were. And we go back until we have some other choice, which is this place now. And we mark that we've been these other places. And so now we take another option, say go down this way. And here we take another option, go that way. And then finally, again, we go up this way and we see that we've been there, so we back up and take the last option. And then that gets us to the last vertex in the graph. So mark each visited intersection and each visited passage and retrace our steps when there's no unvisited options. Again, this is a classical algorithm that was studied centuries ago. And in fact, some argue the first use was when Theseus entered the labyrinth and was trying to find the Minotaur. Ariadne didn't want him to get lost in the maze, so she instructed Theseus to use a ball of string to find his way back out. That's the basic algorithm that we're going to use. And it's been studied by many scientists in the time since Theseus. And in fact, Claude Shannon, the founder of information theory, did experiments on mazes with mice to see if they might understand maze exploration. This might help. Okay, so here's what it looks like in a typical maze. Now, one of the things to remember is in a computer representation, normally we're just looking at the vertices and the set of associated edges. We don't see anything other than that. So it's sometimes frustrating watching these. You know that it turned the wrong way and it's going to get trapped here, but the computer doesn't really know that. So it has to back up along here now, and it continues to back up to find another option until it gets free again and finds some place to go. And sometimes it's very frustrating. It seems to be quite close to the goal, like up here, and it turns the wrong way. So we can see it's going to take a long way, but no way the program could really know that. Again, all the program's working with is vertex and set of edges associated with that vertex, and there it finally gets to the goal. Here's a bigger one going faster. The key thing is not so much getting lost and going the wrong way. The key thing is not going anywhere twice. That's the whole thing. Is we have to have the string to know to go back where we came from, and we have to be able to mark where we've been. And with those two things, the algorithm is able to avoid going the same place twice. If you weren't marking, if you try to do this randomly or some other way, it might take you a while to get to the goal. So it doesn't seem like much of accomplishment maybe for a maze, but actually to be able to get there without going any place twice is sort of a profound idea and leads to an efficient algorithm. Okay, so our idea is given in this metacode to do depth first search, that is to visit all the places you can get to from a vertex V. What we're going to do is this simple recursive algorithm. Mark the vertexes visited and then recursively visit all unmarked vertices W that are adjacent to V. That's a very simple description, and it leads to very simple code. It's so simple, actually, it really belies the profound idea underneath this algorithm. Again, there's lots of applications, and for example, this is one way to find whether there exists a path between two vertices, or to find all the vertices connected to a given source vertex. And we'll consider some less abstract applications once we've looked at the code. So how to implement? Here's what we're going to do for our design pattern for graph processing. It's our first example. What we did when we defined an API for graphs was to decouple the graph data type from graph processing. The idea is we're going to create a graph object using that API, which we know allows us to represent a big graph within the computer and gives us the basic operations that we're going to need for graph processing. And then we use that API within a graph processing routine. And the basic idea is that that graph processing routine will go through the graph and collect some information, and then a client of that routine will query its API to get information about the graph. So in the case of depth first search, here's a possible API. So the idea is that what we're going to implement is a program that can find paths in a graph from a given source. So we give a graph and a vertex, and that the constructor is going to do what it needs in order to be able to answer these two queries. First one is I'll give a vertex. Client will give a vertex. Is there a path in the graph from the source to that vertex? You want to be able to answer that efficiently. And then the other thing is to just give the path. What's the path from S to V? Give me all the vertices on the path in time proportional to its length. So here's a client of this API. It's going to take a source vertex S, and it's going to build a pathfinder or a paths object. And that object is going to do the processing it needs to be able to efficiently implement has path to. And then what this does is for every vertex in the graph, if there's a path from S to that vertex, it'll print it out. So that prints out all the vertices connected to X. And that's just one client of this data type. You could print out the paths or whatever else you might. So that's our design pattern that we're going to use over and over again for graph processing routines. And it's important to understand why we use a design pattern like this. We're decoupling the graph representation from the processing of it. As I mentioned, there's hundreds of routines or algorithms that have been developed for processing graphs. An alternative might be to put all those algorithms in one big data type. That's a so-called FAT interface. And that would be a bad plan, because these things maybe are not so well related to each other, and actually all of them really are just iterating through the graph and doing different types of processing. With this way, we're able to separate out and articulate what the graph processing clients are doing, and then the real applications can be clients of these graph processing routines. And everybody's taken advantage of an efficient representation that we already took care of. Okay, so now let's look at a demo of how depth first search is going to work, and then we'll take a look at the implementation. Okay, so here's a demo of depth first search in operation on our sample graph. Again, to visit a vertex, we're going to mark it and then recursively visit all unmarked vertices that are adjacent. So this is our sample graph, and so the first thing we do is realize that we're going to need a vertex indexed array to keep track of which vertices are marked. So that'll just be an array of booleans, and we'll initialize that with all false. We're also going to keep another data structure, a vertex indexed array of ints that for every vertex gives us the vertex that took us there. So let's get started, and you'll see how it works. So this is a depth first search starting at vertex 0. So now to visit vertex 0, we want to mark it. So that's mark 0 as true, and that's the starting point, so we know anything with edge 2. And now what we're going to do is we're going to need to check all the vertices that are adjacent to 0. So that's 6, 2, 1, and 5. The order in which they're checked depends on the representation in the bag. We don't really necessarily care about that. Most of the algorithms are going to check them all, and it doesn't matter that much about the order, although in some cases it's wise to be mindful and maybe use a bag that takes them out in random order. Okay, so to visit 0, we have to check 6, 2, 1, and 5, so let's go ahead and do that. So in this case, 6 is the first thing to get checked. And so now we mark 6 as visited, and now we're going to recursively do a search starting from 6. The other difference when we visit 6 from 0, we're going to put a 0 in this edge 2 entry to say that when we first got to 6, the way we got there was from 0. And that's going to be the data structure that'll help us implement the client query to give us the path back to 0 from any path, from any vertex. Okay, so what do we have to do to visit 6? Well, 6 has 2 adjacent vertices, 0 and 4, so we're going to have to check them. So first we check 0, and that's already marked, so we don't have to do anything. We're only supposed to recursively visit unmarked vertices. And then we check 4. And 4 is unmarked, so we're going to have to recursively visit it. So next thing we do is visit 4. Mark 4 as having been visited with a true in the marked array, fourth entry of the marked array. And we fill in edge 2 saying we got to 4 from 6. And so now to visit 4, we have to recursively check 5, 6, and 3, and again that order is where they happen to be in our bag. So first we check 5. 5 is not marked, so we're going to visit 5. We're going to mark it, say we got there from 4, and then go ahead and visit 3, 4, and 0 in that order. First we visit 3. That one also is not yet marked, so we're going to recursively visit it. So that's mark 3, say we got there from 5, and then go ahead and to visit 3 recursively, we have to check 5 and 4. Check 5, well, we just came there, it's marked, so we don't have to do anything. Check 4, that's also been marked, so we don't have to do anything. So now, finally, this is the first time in the recursive calls that we're ready to return. We're done with depth first search from 3. So now we're done with 3, and we can, unwinding the recursion, we can now continue our search from 5. And the next thing we have to do from 5, we had already checked 3, so now we're going to check 4. And we've already visited 4, so we don't have to do anything. That's already marked. And we check 0, and that one's already marked, so now we're done with 5, and we can back one more level up in the recursion. So now for 4, we have to go through and look at 6 and 3. 6 is marked, so we don't have to do anything. 3 is marked, so we don't have to do anything. And so we're going to be done with 4. After finishing 4, we're done with 6, and so now we're in the recursion back at 0. We've already checked 6, so now we've got to check 2 next. We check 2, and so we recurse and go there, mark 2, and then say we got there from 0. And now to visit 2, all we check is 0, and that's marked, so we don't have to do anything, and we're done with 2. And then check 1, visit 1, that's the last vertex we're visiting. Check 0, it's already marked, so we don't do anything. We return, and now we're at the last step is to, from 0, 5 is on its list, we have to check if we've been there. We can see that it's marked and we have been there, so we're done with 0. That's a depth first search from vertex 0, and we have visited all the vertices that are reachable from 0, number 1, and number 2, for each one of those vertices we kept track of how we got there from 0. So if we now want to know for any one of those vertices how to get back to 0, we have the information that we need. For example, say we want to find the path from 5 back to 0. We know we got to 5 from 4. We know we got to 4 from 6. We know we got to 6 from 0. So we can go back through using that edge-to array to find the path. So the depth first search calculation built these data structures, and now clients, these data structures built in the constructor serve as the basis for being able to efficiently answer client queries. That's the depth first search demo. So this is just a summary of the things I talked about during that demo. Our goal is to find all the vertices connected to a given vertex S and also a path in order to be able to answer client queries. And the algorithm we're going to use is based on like maze exploration, where we use recursion, mark each vertex, keep track of the edge we took to visit it, and return when there's no unvisited options. We're using 2 data structures to implement this, both vertex indexed arrays, one named mark that will tell us which vertices we've been to, and another one, edge2, that maintains the tree of paths, where edge2w equals v means that vw was taken the first time that we went to w. So now let's look at the code. Then, given all this background, the code for implementing depth first search is remarkably compact. So here's our private instance variables, the marked and edge2 vertex indexed arrays, and the source S. And the constructor just goes through and creates the arrays and initializes them. We won't repeat that code. And so here's the last thing the constructor does after it creates the arrays is does a DFS on the graph from the given source. And it's a remarkably compact implementation. To do depth first search from a vertex V, what we do is mark V, set mark to true. Then for everybody adjacent to V, we check if it's marked. If it's not marked, then we do a recursive call, and we set edge to W equals V. Again, remarkably compact code that gets the job done. So now let's look at some of the properties of depth first search. So first thing is we want to be sure that convince ourselves that it marks all the vertices connected to S in time proportional to some of their degrees, which for sparse graphs is going to be small. So first thing is convince yourself that if you marked a vertex, then there has to be a way to get to that vertex from S. And so, well, that's easy to see because the only way to mark a vertex is get there through a sequence of recursive calls, and every recursive call corresponds to an edge on a path from S to W. But you also have to be able to show that you get to every vertex that's connected to S. And that's a little more intricate, and this diagram is supposed to help you out in understanding that. If you had some unmarked vertex, then maybe there's a bunch of unmarked vertices, and it's connected to S and it's not marked, so that means there has to be an edge on a path from S to W that goes from a marked vertex to an unmarked one. But the design of the algorithm says that there's no such edge. If you're on a marked vertex, then you're going to go through and look at all the adjacent ones, and if it's not marked, you're going to mark it. So that's a outline of the proof that DFS marks all the vertices. And in the running time, it only visits each marked vertex once, or each vertex connected to S once, and so for each one of them, it goes through all the adjacent vertices. So that's the basic properties of depth-first search. Now the other thing that is important is that a client who has uses this algorithm after the depth-first search, after the constructor has done the depth-first search and built these data structures, client can find the vertices connected to the source in constant time, and it can find a path to S if one exists in time proportional to its length. Well, the marked array provides the first part, and the second part is just a property of the edge to array. It's what's called a parent length representation of a tree rooted at S. So if a vertex is connected to S, then its edge to is its parent in the tree. So this code here is going to, for a given, has path to, so that's just return marked, that's the first part. And then to actually get the path to a given vertex. Here's the code for doing that. We actually use a stack to keep track of the path because we get it in reverse order. If there's no path, we return null. Otherwise, we keep a variable x and we just follow up through the edge to array, pushing the vertex onto the stack. And then moving up the tree in the array, and then finally push S itself onto the path, and then we have a stack which is iterable, which will give us our path. That's in time proportional to the length of the path, and it's worthwhile to check your understanding of how stacks and iterators work to take a look at this code to see that it does the job. So that's depth-first search. Now, it's not the optimal graph searching method for all applications, and here's an amusing representation of how depth-first search can maybe create problems sometimes. So I'm getting ready for a date. What situations do I prepare for? Well, medical emergency, dancing, food too expensive. Okay, what kind of medical emergencies could happen? Well, it could be snake bite or a lightning strike or fall from a chair. Well, what about snakes? Do I have to worry about corn snakes or garter snakes or copperhead? And then, well, I better better study snakes. And then the date says, I'm here to pick you up. You're not dressed. And well, so I really need to stop using depth-first search. We're going to look at other graph searching algorithms, but if you always try to expand the next thing that you come to, that's depth-first search, and there's a lot of natural situations where that naturally comes to mind. Here's another example. I took this photo of the Taj Mahal a couple of years ago, and I didn't like the color of the sky. So I used Photoshop's magic wand to make it more blue. And the implementation, now this is a huge graph. The picture's got millions of pixels. And the way that the flood-filled, the magic wand works is to build from a photo what's called a grid graph, where every vertex is a pixel. and every edge connects two pixels that are the same color, approximately the same color, and it builds a blob of all the pixels that have the same color as a given pixel. So when I click on one, it does a depth first search to find all the connected pixels and therefore change them to the new color. That's a fine example of depth first search on a huge graph that people use every day. So that's our first non-trivial graph processing algorithm, depth first search. Okay, now that we've discussed breadth first search and depth first search and connected components, three very useful graph processing algorithm for all sorts of real applications. Now we're going to go back to the idea of the different problems that might arise when doing graph processing, and what are our intuition with this experience on what types of problems are difficult and what types of problems are easy. It's not that I have any real answers to that, but we want to keep coming back to this issue so that we can appreciate a great algorithm when we see it. Here's a challenge, or an example of a challenge. So here's a problem that comes up in plenty of applications. So you want to know if a given graph is bipartite. So what bipartite means is you can divide the edges into two subsets, divide the vertices into two subsets with the property that every edge connects a vertex in one subset to a vertex in another. So in this case, we can assign 0, 3, and 4 to be red vertices, and if we do that, then every edge connects a red to a white vertex. That's a bipartite graph. And we saw an example of bipartite graph, the Kevin Bacon graph. We had movies and performers, two different types of vertices, and every edge went from a movie to a performer. And in general, in other applications, so you want to know, is a graph bipartite? So by graph processing challenge, I mean is how difficult is this problem? So what do you think based on our experience? Is this a problem that any programmer could do? Or maybe you need to be a typical diligent student in this course. Or maybe it's difficult enough that you ought to pay somebody to do it. Or actually maybe it's even an expert couldn't do it, and we'll talk about the precise meaning of that later on. Or maybe we don't even know how difficult it is. Or maybe we can show that it's impossible to solve this problem. These are pretty broad categories, and you'd like to think that we could categorize problems in these kinds of categories. So what about bipartite? We'll do this for a bunch of problems, but what about bipartiteness? Well, the answer for that one is that you can use DFS to get this done. I wouldn't think that any program can do it. Ask a friend. But with DFS, you can see in the book a pretty simple DFS-based solution to this problem that'll tell you whether a graph is bipartite by labeling vertices in such a way, if it is bipartite, that all the edges have the property to go from one vertex to another. Definitely a good exercise after this lecture is to try to write a program that tests whether graph's bipartite or not. Okay, here's another application of this, by the way. That dating graph for the sexual transmitted diseases, so there's males and females. Is that one going to be bipartite? I think maybe this one is, but nowadays maybe not in general. Okay, what about this one? Does the graph contain a cycle or not? So in this case, there's a cycle, 0 to 5 to 4 to 6, back to 0. And there's other cycles too, 0, 1, 3, 2, 0, 2, 4, 6. Those are all cycles. How hard is it to find a cycle in a graph in these categorizations? Well, that one it's very simple. This one maybe any programmer could do, maybe. You have to have the graph representation, but you have to use DFS. Well, you can figure out a way to do it without probably, but anyway, it's really simple with DFS. You don't need to hire an expert for finding a cycle. All right, here's a classic graph processing problem that dates back to the 18th century. It's this town, Königsberg in Prussia at the time, where there's an island. And the river kind of comes in and branches around the island and then goes out in two branches. And there's a bunch of bridges. There's 5 bridges onto the island, 2 from the banks and 1 across to this third peninsula. And then there's 2 bridges crossing that way. So a total of 7 bridges, 1, 2, 3, 4, 5, 6, 7. And Euler, who's a famous mathematician, would go out on a Sunday stroll in this place and came up with the idea, could anyone find a way to go on a Sunday stroll and cross each one of these bridges exactly once? That's often talked of as the original graph processing problem. In terms of graphs, is there a cycle that uses every edge exactly once? Given a graph, is there a cycle that uses every edge exactly once? And actually, Euler proved, so as they say, the first theorem in graph theory, if it's connected and all the vertices have even degree, you can always do it. In this case, you can't because there's a vertex with odd degree. So that's the answer to the existence. Is there a cycle? But suppose you wanted to find the cycle. So you can go ahead and check the degree of every vertex. We looked at easy code for that to know that there exists a cycle. But how about finding one that uses every edge exactly once? So in this case, here's a cycle that uses every edge exactly once. And this graph, every vertex has even degree. And if you go 0, 1, 2, 3, 4, 2, 0, 6, 4, 5, 0, you get to every edge exactly once. That's an Eulerian cycle. So how about that one? Is that any programmer? Or do you have to hire an expert, or is it impossible? This one, we have it listed as a typical diligent algorithm student could do it, but it's a bit of a challenge. It's an interesting program, and again, once you get through the bipartite graph one, you can think about this one. It makes some sense what the algorithm does, but it might take you a few tries to get the code debugged, let's say. And you find code for it on the book site. All right, so that's Eulerian cycle. What about if you want to visit every vertex exactly once? So you don't care about going over all the edges, you just want to get to all the places. That's called in this case, there is a way. For this graph, 0, 5, 3, 4, 6, 2, 1, 0. So that's a way to get to every vertex exactly once. This is sometimes called the traveling salesperson problem on graphs, where the traveling salesperson has to get to every city and wants to just go there once without retracing steps. So how about that one? Every edge is more to visit. It might seem more challenging. And actually, maybe if you have any experience with this, you realize that this one is intractable. That's called the Hamiltonian cycle problem, and it's a classical NP-complete problem. We'll be talking about NP-complete problems at the end of the course, but basically the idea is that nobody knows an efficient solution to this problem for large graphs. And it's a frustrating situation that we'll talk about. But you're definitely not going to solve it by just being a diligent algorithm student. and not even hiring an expert will get it solved, no matter how much the expert charges. So the intuition on finding a cycle that visits every edge once, yeah, you could do it. Find a cycle that visits every vertex once, probably not. That's the kind of challenge that we face when addressing applications of graph processing. Here's another example. The problem is, given two graphs, you want to know, are they identical except for the way that we named the vertex? So here's an example of these two graphs don't look all that identical at all. But if you take 0 here and rename it 4, and 1 and rename it 3, and like that, then 0 here and rename it 4, and 1 and rename it 3, and like that, then you'll see that they are the same graph. They represent the same connections. And in so many applications where maybe the vertex names are a bit arbitrary, or you just want to know, really the interest is in the structure of the connections, you might want to know, it's just the way that I named the vertex makes the graph different. If I have two classes that have two different kinds of interactions, is it the same interactions that's independent of the people, or a scientific experiment studying a property of the universe or whatever? You might want to know, is that connection structure the same or not? That's called the graph isomorphism problem. How difficult do you think that one is? You know, you could you can try all possible ways of renaming the vertices, but there's really a lot of ways, n factorial ways, way too many to try for a huge graph. Is there an efficient way to do it? Or is it intractable, like the Hamiltonian path problem, where it's in this category that nobody knows an efficient algorithm for, but there could be one? Actually, for graph isomorphism, that's one that has stumped mathematicians and computer scientists for many years. Nobody knows even how to classify this problem. We don't know if it's easy or if it's in a class of problems that are we don't know how to solve, but there could be a solution. We can't show that it's impossible or guaranteed to be difficult. Nobody knows how to classify this problem. Again, pointing out that even for a relatively simple problem to state, the state of our knowledge and understanding the properties of algorithms to solve such problems is incomplete for sure. So one last one. Here's a graph processing challenge. This graph, when it's laid out, it's got two edges that cross between 3 and 4 and 0 and 5. And in general, if you have a graph that you got, say the social networking graph of a small class, you want to study that graph and look at it. You want to draw it on the plane, and maybe you want to try to do it without having edges cross. So in this case, there is a way to place the vertices in the plane so that when you draw the edges, no two of them cross. So how difficult is that problem? Even is it possible to do or not? That's a classic problem in graph processing that came up from the first time that people were representing graphs in computers. And the answer to this one is also interesting to contemplate. There's a linear time algorithm known for this based on DFS. So that means running times could run it on huge graphs. You could know whether or not you could lay it out in the plane. It was discovered by Tarjan in the 1970s. And you heard that name come up again in graph processing. Based on DFS, but if you really want to get this done, you need to hire an expert, because that is quite a complex algorithm and probably beyond what a diligent algorithm student or professor might accomplish. That's kind of another point on this range of difficulty of graph processing problems. So there's no question that graph processing is challenging, and this introductory lecture gave us numerous useful graph processing algorithms but still leaves us with the feeling that there's plenty more to know, and we'll cover some more in later lectures. Next, we're going to talk about breadth-first search, which is a completely different way to process all the vertices connected to a given vertex. It'll get the job done, but it has totally different properties that are useful in different ways for different applications. To understand breadth-first search, we'll start right out with a demo. So breadth-first search is not a recursive algorithm. It uses a queue as an auxiliary data structure. And it's also quite similar, quite simple to explain. So what we're going to do is we're going to put the source vertex on a queue and then repeat the following until the queue is empty. Remove the next vertex from the queue in FIFO order, then add to the queue all unmarked vertices that are adjacent to V and mark them. And just keep doing that until the queue is empty. Let's see how that works on our example. This is a smaller example, just a 6-vertex graph with 8 edges. So add 0 to the queue. So we just take 0 and put it on the queue. That's where we start. And now go into repeat until queue is empty, remove a vertex, add all unmarked vertex adjacent and mark them. So we dequeue 0, and then in order to process 0, we need to check all its adjacent vertices. So in this case, that's 2, 1, and 5. And again, the order depends on how the bag was constructed for vertices adjacent to 0. So we check 2, and that is not marked, so we have to add it to the queue. Then we check 1, that's not marked, so we add it to the queue. Then we check 5, and that's not marked, so we add it to the queue. So that's, we finished processing 0, 0's done. So now remove the next vertex from the queue. In this case, it's 2. We're going to take 2 off the queue and process it by adding to the queue all the unmarked vertices that are adjacent. So to process 2, we have to check 0, 1, 3, and 4. We check 0, that's already marked, so we don't do anything. We check 1, that's also already marked, so we don't do anything. In fact, it's on the queue. We check 3, and that one is unmarked, so we mark it and add it to the queue. And then we check 4, that one's unmarked, so we mark it and add it to the queue. By the way, I didn't mention, but we're also keeping track of 2 auxiliary data structures for this. One is the edge-to array, which is the same as before. What edge did we use to get to this? So 4, we got to 4 from 2, and 2 we got to 2 from 0. So again, that's going to be a tree that gives us a path back to the source. And instead of marked, we also keep a more detailed information, which is the length of the path, because we do it because it's easy to do it. Okay, so 4, we check 4 and add it to the queue, and now we're done with 2. So now we have 1, 5, 3, and 4 are all in the queue, and we're going to process them. And since we've marked everything, all we're going to be doing now is checking vertices that are marked. So for 1, we check 0, and that's marked, and we check 2, and that's marked. So then we're done with 1. Next thing off the queue is 5, and we check 3, and that's marked, and we check 0, and that's marked, so we're done with 5. And then 3, we got to check 5, and then 4, and then 2, and they're all marked, and now we're done with 3. And then finally the last one, always the last one, everybody else is marked, it's connected. Check 3. Check 2, it's marked, and we're done. So what this process, the result of this computation, again, is a tree rooted at the source, and we can follow back through the tree to get paths from each node to the source. And not only that, we can get the distance, the number of edges on the path from each node to the source. So that's a demo of breadth-first search, and next we'll take a look at properties of this algorithm. All right, so now we've considered two different methods for processing all vertices in a graph, and actually they're quite closely related, even though the computations are quite different. Essentially, depth-first search uses recursion, so it corresponds to putting unvisited vertices on a stack. Breadth-first search, explicitly, we put the unvisited vertices on the queue. And actually, breadth-first search solves another problem that often we want to solve, called the shortest path problem. Actually, the path that you get back from breadth-first search is the path from the source to the given vertex that uses the fewest number of edges. And we'll look at that in just a minute. And the idea is that the breadth-first search examines the vertices in the graph in increasing distance from the source. So let's take a look at that. So breadth-first search computes shortest paths, that is, it builds the data structure that we can answer shortest path queries from the source with, from S to all other vertices in the graph in time proportional to E plus V, the number of edges plus the number of vertices. And so let's look at why that's the case. So the first thing is, how do we know that it computes shortest paths? Well, the intuition is, and you can fill in the details, the queue always contains some vertices of distance k from the source, followed by some vertices of distance k plus 1. So they're on a queue. We're processing them in first in, first out order. So say we're at a state when all of these vertices are on the queue. We're going to have processed vertex 0. As soon as we get this one, we'll delete vertex 0 from the queue. And then when we're putting these adjacent ones on, we're adding the ones of distance 2. But we're not going to process any of those until we're done with the ones of distance 1 and so forth. So it's not hard to show that always you have either one of the two distances from the source on the queue. And that means the first time we get to a vertex, that's the shortest path to that vertex. And again, the running time, we only visit vertices once because we mark them. So it's time proportional to the number of vertices plus the number of edges in the graph. So that's breadth-first search properties. And then here's the implementation, which is simply code for the basic method that we outlined in pseudocode. So our private instance variables are marked, or in the demo we used dist2, but just for simplicity, let's use marked. Edge2 then is how we get to the first vertex, and then the source. And so you have a constructor that builds those arrays the same way as before, and then calls BFS. So BFS builds a queue. That's what it's going to use. It enqueues the source and marks the source. And then this is just in code what we said in words before. While the queue is not empty, we pull off the next vertex from the queue, call it V. For everybody adjacent to V, we go ahead and check. If it's marked, we ignore it and move to the next. If it's not marked, then we put it on the queue, mark it, and remember the edge. And again, this is an example of the power of abstraction and the utility of our design pattern. All we're doing in terms of the graph data type is being a client to go through all the adjacent vertices. But it allows us to implement this completely different algorithm in really an accessible way. So that's the implementation of breadth-first search. And then the client for getting the paths back is the same as for depth first search. So here's an old application of breadth first search in computer networks. It's very important. When you're communicating from one place to another, you want to get there in the fewest number of hops. This is the ARPANET, the predecessor of the Internet, as of July 1977. Things were slow, and computers were small and slow. It's important to do these things in small number of hops. And with breadth first search, you could take this graph and figure out the shortest way to get from one place to another. That's a typical application of breadth first search. Here's another one, so-called Kevin Bacon numbers. And nowadays, actually, you can type Bacon and an actor's name and get the answer to this. There's, if you're not familiar with it, you can become familiar with it by Kevin Bacon numbers. The idea is you have a graph where the vertices are actors and the edge, you think of an edge connecting two actors if they were in a movie together. And so what you want to find is, given an actor, what's the shortest way to get to Kevin Bacon connected by, so we have edges for actors and edges for movies in connection if the actor's in the movie. So Buzz Morrow and Tatina Ramirez were in Sweet Dreams together, and these two actors were in this movie together, and so forth. And you get a way to Kevin Bacon from any actor. And this is another pop culture application. This is so-called 6 degrees, which you can get to anyone with 6 steps in this way. So that's all implementation of breadth first search on the Kevin Bacon graph, where we include one vertex for each performer, one vertex for each movie, connect the movie to all performers that appear in the movie, and the shortest path from Kevin Bacon to every actor. If you follow back through that path, you get you get the proof of the Kevin Bacon number for each actor, and we have implementation of that on the book site. So that's another example. And actually there's a maybe even older, or at least similar age example that mathematicians are fond of, and that's called the so-called Erdős number. So in this one, it's mathematician. The nodes are mathematicians, and there's an edge if the two mathematicians have co-authored a paper. And Paul Erdős was a very productive Hungarian mathematician who traveled the world, co-authoring papers with people all over the world. A very interesting and prolific character who actually did quite a bit of research on properties of graphs. And maybe even more so than Kevin Bacon. The idea is he was so prolific that pretty much every mathematician has a pretty low Erdős number. So that's our second example of a graph processing algorithm, breadth first search. Next, we're going to look at a slightly different graph processing application, but it's a graph processing algorithm that's useful in many applications, as we'll see in a minute, and slightly different than depth and breadth first search. It's called computing connected components. Now, I mentioned this a little bit when we talked about basic definitions. So the idea is that if there's a path between two vertices, we say they're connected. And what we want to do is pre-process the graph, that is, build a data type that can answer queries of the form, is V connected to W in constant time? Now we want to be able to do that for a huge sparse graph of the type that appears in practice. We can't use if we could use the adjacency matrix data structure, maybe we could do that, but we can't. We're going to build a class that uses our standard representation that will enable clients to find connected components. Really interesting to think about this one. We're getting the job done that we could get done if we had a huge sparse matrix, but if we have billions of vertices, there's no way we can have billions squared in the matrix, so we have to find another way to do it. So here's the data type that we want to implement. So it's called CC, and it's going to, the constructor is going to build the data structure that finds the connected components in the given graph to be able to efficiently answer these connectivity queries. It'll also be able to count the number of connected components, and it also assigns an identifier from 0 to count -1 that identifies the connected component that every vertex is in. Now if you maybe this sounds a little bit similar to what we did for the union find problem. Union find problem, we were taking edges and we wanted to have queries that well, union is like add an edge to the graph, and then find is like, are these two things connected yet? Now, with union find, we found that we couldn't quite answer the thing in constant time. Remember, this is a very slowly growing question. It's constant in practical terms, but not really. So it's less efficient than the algorithm that we're going to talk about, because it doesn't quite get constant time. On the other hand, in another way, it's better than the algorithm that we're going to talk about, because you can intermix the unions and finds. And in this case, because we're working with a graph, it's like we're taking all the unions and then we're handling find requests. So anyway, what we're going to use to implement this is a depth-first search approach. So we'll do the depth-first search. We'll just keep different data than we did when we were finding paths. The algorithm is based on the notion that connection is equivalence relation. Recall, a equivalence relation has these three properties. Every vertex is connected to itself. If V is connected to W, then W is connected to V. And if V is connected to W and W to X, then V is connected to X. And those basic operations underlie the algorithm that we're going to talk about. So the equivalence relation is a general mathematical concept that applies in graph theory in this case. And as I already mentioned, in the case of graph, it implies that the vertices divide up into connected components, which are maximal sets of connected vertices. So our sample graph has 3 connected components. And what we'll do is assign identifiers to each one of the components. And that will, for every vertex, give us an identifier number for that vertex. And that's the data structure that our depth-first search is going to build. And that immediately gives the constant time implementation of the connectivity queries. Given 2 vertices, you look up their ID, and if they're equal, they're in the same connected component. If they're different, they're not. So that's the data structure that we're going to build. It's like a union find tree where there's just all the trees are flat. That's what I just said. Given connected components, we can answer queries in constant time. Here's a big grid graph that we used when we're talking about union find, and it turns out that this one's got 63 connected components. And again, when you really think about it, it's kind of amazing that we can do this computation in linear time, even for huge graphs. And it's really important to be able to do so for those very huge graphs that we talked about in so many applications. If you can process all the edges, you can also find out the connected components and be set up to answer connectivity queries. This is a simple algorithm, but really it's ingenious. Okay, so let's look at the implementation. So our goal is to partition the vertices into connected components. So we're going to use DFS and marking. And so what we're going to do is, for a general graph, for every unmarked vertex, we're going to run DFS to find all the vertices that are connected to that one, that are going to be part of the same component. So we use the marking to help control the DFS, but also to control the connected components, the vertices that have already been processed and known to be in a given connected component. So let's look at a demo to understand how this algorithm works. So again, we're going to use depth-first search and our summary of depth-first search to visit a vertex. We mark it as visited and then recursively visit all the unmarked vertices that are adjacent. So in this case, so we'll start, we're going to visit all the vertices in the graph in order to identify the connected components. So we'll start by visiting 0. To visit 0, we have to check 6, 2, 1, and 5. So we start by checking 6. We mark it as visited, so that's entry 6 in the array. And now we're going to keep this other vertex indexed array, which is the ID, the connected component number. So all we're saying by putting a 0 in that entry is that 6 and 0 are in the same connected component. Every vertex that we encounter during the depth-first search from 0, we're going to assign a value of 0. Okay, so what do we have to do to visit 6? We have to check 0, and then we have to check 4. And 4 is unmarked, so we're going to recurse and visit 4. To visit 4, we have to check 5. 5 is unmarked, so we recurse to visit 5. And to visit 5, we have to check 3, 4, and 0. 3 is unmarked. This is the same depth-first search that we did before, but now we're just keeping track of the connected component number, and we're assigning every vertex that we encounter with the same ID as 0. Okay, so now we have to visit 3. To visit 3, we have to check 5 and 4. 5 was marked, nothing to do. 4 was marked, nothing to do. So we're done with 3. Done with 3, we can continue the depth-first search from 5. We have to check 4 and 0. 4 was marked, 0 was marked, so we're done. And now we can continue with the depth-first search of 4. We have to check 6 and 3. 6 was marked, 3 was marked, and we're done. And we can, now 6 is done, and now we can continue with 0, and we have to check 2. Check 2, it's not marked, so we mark it and give it a connected component number of 0. To visit 2, all we do is check 0, which is marked, so we're done, and then we do the same thing with 1. Unmarked, so we visit it, assign it 0, and then visit 1. And to do that, we check 0, which is marked, so we're done with 1, and then to finish 0, we have to check 5, and that's marked, so we don't have to do anything, and we're done with 0. So now we're done with the first connected component, but we're not done with the whole graph. So what we want to do is go look for, so that's a connected component corresponding to 0. Now what we want to do is go look for an unmarked vertex. So we started at 0, and we check 1, 2, 3, 4, 5, and 6, and they're all marked. And so the next unmarked vertex that we find in the graph is 7. So once we return from the depth-first search for 0, we increment a counter, which is our how many connected components have we seen. And now we're going to assign that number to everything that's connected to 7 on the depth first search from 7. So what do we do to depth first search from 7? We check 8. 8's unmarked, so we go visit it. So we assign it connected component number of 1, same as 7, and mark it. And then go ahead and recurse to visit 8. We check 7, which is marked, so there's nothing to do, and we're done with 8. And then we're done with 7. So now we're done with all the vertices that were connected to 7. We increment our counter of number of components to 2 and look for another vertex. So now we check 8, which we already know is marked, connected to 7. And so now 9 is unmarked, so we're going to do a DFS from 9. And everybody connected to 9 is going to get assigned a connected component number of 2. So to visit 9, we have to check 11, and that was unmarked. And so we visit it, give it a 2. To visit 11, we have to check 9, which is marked, so nothing to do, and 12, which is unmarked, so we visit it and give it a number of 2. To visit 12, we have to check 11, which was marked, and 9, which is also marked, and then we're done with 12. And then we're done with 11, and then to finish doing 9, we have to check 10 and 12. 10 is unmarked, so we mark it and give it a number of 2. To visit 10, we check 9, which is marked, so we're done. And then finally, to finish the DFS, we check 12 from 9, and that's marked, so we're done with 9. And now we keep looking, and we find that 10, 11, and 12 are all marked. So we've completed the computation. And for every vertex, we have a connected component number, and for any given query, we can test whether they're in the same connected component simply by looking up that number and seeing if it's equal. That's a demo of connected components computation. Okay, so here's the code for finding connected components with DFS, which is another straightforward DFS implementation, just like the other one. It just keeps slightly different data structure. We keep the marked data structure, which is the vertices that we visited. And then we keep this vertex indexed array ID, which gives the identifier, the component containing V. I think we call it CC on the demo. And then a count of the number of components that we've seen. The constructor creates the marked array, and it creates this ID array. But now the constructor does more work than a single call on DFS. What it does is it goes through, this is the constructor, goes through every vertex in the array, in the graph, and if it's not marked, it does a DFS. And that DFS will mark a lot of other vertices, but when it's done, all of those are going to get assigned the value of count, and we're going to increment count, then go and look for another unmarked vertex. Anything that wasn't marked by that first DFS, we'll do a DFS from that one and mark all its vertices with the next value for the ID. So now let's look at the implementation of DFS. It's a recursive array, just like the one that we did for pathfinding, except all that we do when we mark a vertex, we also simply set its ID to the current component name. So all the vertices that are discovered in the same call of DFS have the same ID. And to visit a vertex, you go through all its adjacent vertices, and any that are not marked, you give a recursive DFS call. Again, this code is amazingly compact and elegant. When we're going through the demo step by step, maybe you could see that the underlying computation is actually kind of complex, but recursion and the graph processing API that we've set up provides compact and easy to understand implementation. So that's using DFS to find connected components. And then to return the ID of a given vertex, you just look it up in the array, and to return the number of components, just return count, and then you can build up the needed connectivity API from those. So that's depth-first search to find connected components. We'll just talk briefly about two applications from scientific applications. So here's an application of sexually transmitted diseases at a high school. And simply the vertices are people, blue are men and pink are women, and you have an edge between if there was a contact, and so it's obvious that you're going to be interested in the connected components of this graph to be able to properly study sexually transmitted diseases. If these individuals had no contact with these, then whichever one has a disease, maybe it won't spread. Or if you add a new edge, then maybe you have a problem. That's just one example of studying spread of disease. Here's another example that we use for that's similar to the flood fill example. And this is processing data from a scientific experiment. And in this case, this image comes from a photograph, and the white things are particles that are moving. And all we get is a image where it's a grayscale image. And so what we'll do to do this processing is we want to identify the movement of these particles over the time. And the way we do it is build a grid graph like the one for the flood fill application, and do an edge connecting two vertices if their difference in their grayscale values is greater than less than some threshold. And so then if you do that and then find the connected components, then you can identify blobs which correspond to real particles in this simulation. And they do that every frame in a movie, then you can track moving particles over time. So these are maybe fairly high resolution images. These are graphs with lots and lots of edges, and you need to be able to do this computation quickly in order to do this scientific experiment. And we use this as an example in our first year programming course. But it's based on computing connected components using depth-first search. So that's our third example of a graph processing algorithm. Today we're going to look at directed graphs, which is another graph processing model that's very useful in many applications. It's very similar to the undirected graph model that we looked at last time, but there are some really profound differences. After introducing the concept and looking at the API, we'll look at three important classic algorithms for processing directed graphs. The introduction has to do with just explaining the concept and seeing what it does to our graph processing problems, like the ones that we talked about for undirected graphs last time. So the idea is that the edges now have direction. A directed graph, or a digraph, is a set of vertices that are connected pairwise by directed edges. So it's a list of pairs of vertices where the order of the pair matters. So an edge, we say an edge goes from one vertex to another one, whereas undirected graphs, we just talked about connections. When we're processing such graphs or traveling around them, we have to follow edges in the given direction. So for example, if we talk about a path in a digraph, it looks like there's a connection between 2 and 0, but only goes from 2 to 0. If you want to go from 0 to 2, you have to follow the edges in direction going from 0 to 5 to 4 and then to 2. In a directed graph, in this digraph, you can't see 2 directly from 0. Similarly, a directed cycle follows the edges around the direction to get back to the original vertex. Also, vertices have in degree and out degree in digraphs. And the out degree obviously is the number of arrows leaving the vertex, and the in degree is the number of arrows coming into the vertex. Those are the basic definitions. Let's look at a couple of applications. One obvious one is road networks, where we put a vertex according to intersection and an edge for roads, and we look at a situation where the roads are one way or can be one way. So if you've driven in lower Manhattan, you're very familiar with this map, which has lots of one-way streets, and it's not always clear how to get from one place to another. You can have some two-way streets that have edges in both directions, but with digraphs, we allow the abstraction of one-way streets. Here's another more abstract example. This is the political blogosphere with connections if blogs have links to one another. As you can see, most of the links go from blue to blue or from red to red, although there are some orange links that go from blue to red and a few purple ones that go from red to blue. And this gives some insight to the communications in the political blogosphere, at least in 2004. Here's another one. This is a study of the crash in 2008, and it was a directed graph that showed the structure of banks lending to one another. An edge corresponds to an overnight loan, and a vertex corresponds to the bank. From studying this diagram, experts could see how the banks divided into groups and were therefore vulnerable in these groups. And we'll look at more detailed definitions of how these groups are defined a little later on. This is just an example of the use of a digraph. And it's a digraph. One bank lends money to another. That's not the same as the banks being connected in as in an undirected graph. The direction really matters. This is another one from logic, where the vertices correspond to Boolean variables and the edges correspond to implication. And people use graphs like this to study in logical verification and also studying electric circuits. Electric circuits themselves can be digraphs where circuit elements have input and output. And so the edge, of course, takes the output of one element to the input of another. Trying to understand the behavior of such a circuit involves processing a digraph. Here's another abstraction, the so-called WordNet graph, where vertices correspond to what's called synsets and edges correspond to hypernym relationships where a word is an instance of another one. So there's a lot of different events like a miracle or human activity and so forth. And graphs of this type are very useful in studying applications involving meanings in human languages. Here's a famous one. General McChrystal said that once we understand this graph, the war in Afghanistan will be over. So with all these types of applications, and there's many, many others, just as with graph processing, the digraph as a model distinct from graph processing is important. There's many direct applications where we have connections between objects, but the direction of the connection matters. So what about digraph processing algorithms? Well, we're going to look at many problems that are very similar to the ones that we looked at for undirected graphs, but you can see that they're going to be a bit more complicated. Even a human has trouble looking at a digraph, trying to figure out a simple problem like, is there a path from S to T in this digraph? It seems like there's quite a few possibilities to consider to convince yourself whether or not there's a path. And for the huge digraphs examples that I looked at before, obviously we're going to need a computer program, and we're going to have a bit of a challenge figuring out what's going on. Of course, you might want to know the shortest directed path from S to T. For example, if you're driving around lower Manhattan, you certainly want to have a solution to that problem. Then there's another problem called the topological sort problem, which is a general model that's useful in all kinds of applications where we're scheduling events that involve precedence constraints. In the graph abstraction or the digraph abstraction, it amounts to the problem of trying to draw the digraph so that all the edges point up. That's called topological sorting. And then connectivity is more complicated for digraphs than for undirected graphs. There's the concept of strong connectivity, which means for any given pair of vertices u and v, you want to know, is there going to be a directed path from u to v and another directed path from v to u? That's a much more complicated problem than connectivity in undirected graphs. A generalization of that, or a query related to strong connectivity, is so-called transitive closure. And for that, you just want to be able to answer the query, given vertices v and w, is there a path from w to v? That's transitive closure. Actually, you're familiar with the web is a gigantic directed graph. If there's a link from page A to page B, that's a directed edge. And digraph processing is used in famous PageRank algorithm to determine the importance of a web page. Those are just a couple of examples of digraph processing problems that introduce the idea. To develop digraph processing algorithms, we're going to need an API. We'll use the same design pattern that we use for undirected graphs, where we develop an API for building graphs that can serve as a client for all our graph processing algorithms. And it's very similar, if not close to identical, to the undirected graph API, except the class is named Digraph. And other than that, it's got add edge, where we add a directed edge, but now we're saying it's an edge from V to W. And then an iterator that gives the vertices that point from the given vertex. So we're getting, those are the edges that we can travel along to get around the graph. We have V and E. And another new method that is not relevant for undirected graphs is the reverse. So that's a method that returns a digraph where all the edges are reversed. And we'll see that's actually an important method to have for one of the algorithms that we'll talk about today. So here's a typical client, very similar to the one that we did for undirected graphs, where we read a digraph from input stream. So that's pairs of edges, pairs of vertices that represent an edge from first vertex to the second one. And then for every vertex, we print out for every edge that you can get to from that vertex, for every other vertex you get to from that vertex, we print out a little graphical representation of the edge V to W, where the little arrow we use with a minus sign and a greater than. So for example, with the input file tinydg.txt for directed graph, this one's got 13 vertices, 22 edges. It's got an edge from 4 to 2, from 2 to 3, 3 to 2, and so forth. And if we execute this sample client, we get the edges printed out. It builds the graph and then prints out the edges. And the order in which they come out is in order of vertex, and the order in which each edge comes out depends on the representation, just as for graphs. We'll skip through the possibilities of keeping a list of edges or using a matrix for digraphs, because again, in practical problems, the graphs are huge and sparse. So the average vertex degree, in degree and out degree is low. And we can't afford to keep space proportional to the number of possible vertices that a vertex could connect to for each vertex. So it's very similar to, or exactly the same really, to the one that we use for undirected graphs. We keep a vertex indexed array where for each vertex we can keep a bag of all the vertices that you can get to from that vertex. So vertex 6 has out degree 4, and there's 4 vertices on its list, 9, 4, 8, and 0. And when we process the graph, we're going to visit those vertices in that order, which is just determined by the order in which they appeared in the input. So here's the implementation that we used for undirected graphs last time. And you'll see that the only difference for digraphs is we change graph to digraph, and we only have one representation of each edge. V goes to W. For undirected graphs, we had W goes to V as well. Otherwise, the code's exactly the same. We have an iterator for the vertices adjacent to V, but that's the difference between directed graphs and undirected graphs. Again, the reason we do that is that we can get basic graph processing processed in a reasonable amount of time, where every time we deal with a vertex, we can get to its neighbors, or the places you can get to from that vertex, in time proportional to the number of vertices. You simply can't afford to do that with other representations. So that's the Digraph API, which is virtually identical to the Graph API. Okay, first we're going to look at the search algorithm for digraphs. And this is the finding the paths, or what are all the vertices that we can get to from a given vertex along a directed path. And again, this is a little more complex for a digraph, it would seem, than for a graph. So in this case, that's the set of vertices that you can get to from the given vertex S. Notice that this set is characterized by every edge crossing the boundary goes in. If there were an edge that went out, that would give another member of the set. Well, actually, it looks more complicated to a human, but to the computer, it looks exactly, precisely the same. In fact, the method that we looked at for undirected graphs is actually a digraph processing algorithm. It treats every connection between two vertices as two directed edges, one in each direction. So DFS that we looked at last time is actually a digraph algorithm, and we use precisely the same code. So to visit a vertex V, we mark the vertex as visited and recursively visit all unmarked vertices W that you can get to from V. Let's look at a demo just to reinforce that. So here's a sample digraph with the edges over at the right. Let's look at depth first search on that digraph. So we're going to look at the vertices that we can get to from vertex 0 in this digraph. Again, we have two vertex indexed arrays, one called marked, which says whether we can get there from V, and the other called edge2, which gives us the vertex that took us there. With that, we can recover the paths from vertex 0 to each vertex that can be reached from vertex 0. So we start off by visiting vertex 0, and now check the edges that are adjacent to it with directed edges going out. So there's 5, and then there's going to be 1, but 5 is unmarked, so we have to recursively visit 5. So we mark 5, and we say we got there from 0. The path from to 5 is 0 to 5. And so now we're going to recursively visit all the unmarked vertices pointed to from 5. In this case, it's just 4, but 4 is unmarked, so we're going to recursively visit 4 and say we got there from 5. And now recursively, we have to check all the unmarked vertices pointing from 4. There's 3 and 2. First we do 3, and that's unmarked. So we got to visit 3 and say that we got there from 4. And now to visit 3, we looked at all the vertices pointing from 3. We can check 5. We've already been to 5. That's marked, so we don't have to do anything. And then we check 2. 2 is unmarked, so we continue with the depth first search and visit 2. So now to visit, we mark 2 and say we got there from 3, and now we check the vertices we can get to from 2. In this case it's 0, which we've already been to, and 3, which we've already been to. So now we're done with vertex 2, and we can return and continue the search from 3. Well, actually, that was the last one from 3, so we're done with 3 as well. So now we're at 4. We still haven't checked the edge from 4 to 2, so now we do that. And of course, we've been to 2, so we don't have any further processing, and we're done with 4. 4 was the only edge we get to from 5, so we're going to be done with 5 as well. And then what about 0? Well, we have to check 1. 1's not visited, so we visit 1, mark it, and return, and then we're done with 0. And that gives the set of all vertices that are reachable from 0. And not only that, the edge to array gives the information that we need to reconstruct a path from any of those, from 0 to any of those vertices, using precisely the same method that we used before. We get to 4 from 5, we get to 5 from 0, so 0, 5, 4 is a path to 4, and we can do that for any vertex in that set. Okay, so what about the code? The code is exactly the same as for undirected graphs. That's the code for undirected graphs that we looked at last time. To get the code for digraphs, we just changed the names. It's the same code otherwise. The constructor builds the array of marked vertices and also builds edge 2, just to avoid clutter, left that one off this slide. And then it makes the call on DFS. Then the recursive DFS does the work. It marks the vertex, and for every adjacent vertex, if it's not marked, it does the DFS. And then the client can ask whether any given vertex is reachable from S after the constructor has done its work. That's depth first search in directed graphs. Actually, we already did it. Now here's just a couple of applications where this kind of code is used. One is so-called program control flow analysis. Actually, every program can be viewed as a digraph where the vertices are basic blocks of instructions that are just executed one after the other with no conditionals. And then edges represent a jump. If there's an if statement, a vertex will have 2 edges going out of it, or a loop, which involves a conditional. So analyzing a program, people write systems to analyze programs to look at their structure by studying the digraphs. For example, one thing that happens often is there's unreachable code. Another thing you might want to do is determine whether you can get to the exit or not by doing this digraph processing. So that's actually a widely used technique in software system development to try to improve code by doing this kind of digraph processing. And of course, these digraphs can be huge. Another classic use of depth first search in digraphs is garbage collection that's used in systems like Java, where data structures are digraphs. We build objects and then we create references to other objects. And so the data that any program's used is really set as a digraph. So there's the idea of roots. So your program has some live objects that it can access through whatever state it's in. But a language like Java, there's automatic garbage collection, which means the programmer, when it's done with an object, maybe it overwrites one of these pointers or something, there's going to be some blocks that are not directly accessible by the program. And so what's interesting is the set of reachable objects that can be indirectly accessed by the program, starting and following a chain of pointers. So those are the ones that can't be collected or reclaimed by the system for reusing the memory. But all the other ones, the gray ones that can't be reached by the program, there's no reason to keep them live. May as well collect them and return them for reuse. So there's a so-called mark and sweep algorithm that actually dates back to 1960, where you run DFS to mark all reachable objects and then go through and sweep through all possible objects, and if its object is unmarked, it's garbage, so add it to the list of free memory. And that's a classic method that's still widely used. It uses an extra bit per object because you have to have that for the mark, but still it's a effective and useful digraph solution. So DFS with reachability that we just showed, and pathfinding is similar, and there's a couple of other simple digraph problems that we'll consider. These are so far examples. But it's also interesting that DFS is the basis for solving digraph problems that are not so simple or immediate to solve. This was pointed out 40 years ago by Bob Tarjan in the seminal paper that showed that depth-first search can allow us to solve problems that seem pretty complicated actually in linear time. And we're going to look at an example of that later on. So that's depth-first search. What about breadth-first search? Well, in the same way that we saw for depth-first search, every undirected graph is actually a digraph that has edges in both directions. So BFS is really a directed graph algorithm, and we can use exactly the same code to find shortest paths from a source to any given vertex. So we use a queue. We put the source on a queue and mark it as visited, and then as long as the queue is non-empty, we remove the least recently added vertex and add to the queue and mark as visited all the unmarked vertices that you can get to from that vertex. And the same proof shows that BFS computes shortest paths, the ones with the fewest number of edges, from S to each other vertex in a digraph in time proportional to in linear time. So you want the GPS in your car to use BFS when you're driving around lower Manhattan. So let's look at a demo, again, just to see the distinction between breadth-first search in digraphs and see how it works. So this is a smaller digraph again with 6 vertices and 8 edges. We take a queue and we take our source vertex and put it on the queue to get started. Then queue's non-empty, so we remove 0 and we check all the vertices that are adjacent that we get to. So we're going to, and 0 is 0 distance from 0. So first we'll check 2, and that one is not marked, so we mark it and put it on the queue. And then we'll check 1, and that one's not marked, so we mark it and put it on the queue. Then we're done with 0. Now queue's not empty, so we pull the least recently added off, that's 2. And now we're going to check the vertices you can get to from 2. Notice both 1 and 2 are distance 1 from 0. And now, since we're going from 2, everything that we encounter will be distance 2 from the source. So we find 4, it's distance 2 from the source, and we get there from vertex 2, unmarked. So we fill in those data structures and put it on the queue. Then we're done with 2, so we go back to the queue, and 1's on the queue. So we pull 1 off, it's distance 1 from 0. Remember, the proofs showed that everything on the queue is one of 2 distance, either k or k plus 1. In this case, we've got 1 at distance 1 and 4 at distance 2. So now we're going to pull 1 off the queue and look at the edges you can get to, places you can get to from 1. We check 2, but that's already marked, so we ignore it, and then we're done with 1. Now 4 is left on the queue, so we pull it off and check adjacent vertices. In this case 3, it's unmarked, so we put it on the queue. Then we're done with 4. Then from 3, we check 5, and that's unmarked, and it's 1 more distance from the source, so we put it on the queue. And then finally, we check 2, which we already visited, so we don't have to do anything. And then finally, we pull 5 off the queue, check where you can get to from 5, and it's 0, which is marked, so we're done. And so that's breadth first search, which gives us this directed tree from the source, which gives the shortest path to all the vertices that you can get to from that source. You can use a version of this to solve a more general problem known as the multiple source shortest paths problem. In this problem, you're given a digraph and a set of source vertices, and you want to find the shortest path from any vertex in the set to each other vertex. So for example, in this case, if the set is 1, 7, and 10, what's the shortest path to 4 from one of those vertices? Well, it turns out in this case to be 7, 6 to 4. Shortest path to 5 is 7, 6, 0, 5. Shortest path to 12 is 10 to 12. That's a more general problem, but it's actually easy to solve. How do we implement this? We just use a different constructor. We just use BFS, but initialize by put all the source vertices on the queue to get started. So that is every vertex so you put those on the queue and they're 0 from the desired source, and then any vertex you can get to from any one of those is going to be 1, and so forth. So the result still gives away, the edge to array will still give a way to get from any vertex, the shortest way to get from any vertex to each of the source vertices. Here's a application of breadth first search. Let's say you want to crawl the whole web. Well, all the web that you can access from some starting web page, say like Princeton's starting web page. Again, the digraph model, each vertex is a web page, each edge is a link on that web page to some other web page, and so all we want to do is get to all the other vertices on the web. And so solution is, well, we don't actually build the digraph, we just use an implicit digraph, because for every web page, we can find the links to other web pages on it, and we'll just build those as we encounter them. So we're going to start with a source, which is the root web page. We're going to have a queue of the sites that we still need to explore. What we're going to do is also have a set of discovered websites. This corresponds to our marked array. But since we don't know how many vertices there are on the web, all we're going to do is keep track of the ones that we've been to. We don't use a vertex indexed array. We don't even bother with, because we'll just use the vertex names and do the lookup as indicated we could do. So all we do is use breadth first search, the same method is if the queue's non-empty, pick a website off the queue and just add to the queue all the websites to which it links. But all of those websites, you check whether they're in the set of the ones that you've seen already. Now, you might run out of space for this set before you get to the whole web, but anyway, conceptually, this is a way that you could go. One thing to think about is why not use DFS for this? One reason is you're going to go far away in your search for the web. Maybe that's what you want. But the real problem, in point of fact, is there's some web pages that would trap such a search by creating new web pages and make links to them the first time that you visit them. So they trap searches like that because DFS would always go to a new web page like that and it'd keep creating new ones and you wouldn't get very far. With breadth-first search, you're taking a wide search of the pages that are close, and that's often maybe what you want for such a search. And just to show how simple the idea is, this is complete code for it's kind of a bare bones web crawler, but it'll get to a lot of websites. So let's look at it. We do this example because, again, it really indicates the power of using appropriate abstractions to implement the algorithms that we're interested in. This one, we're going to use a queue of strings. That's the websites that we have to still yet to go to. And then a set of strings is going to be the ones that we've already been to. That's equivalent to the marked array. We'll start with Princeton's website, add it to the queue of places we have to go, and also mark it. Discovered.add just means mark it. So now, while the queue is not empty, what we're going to do is read the raw HTML from the next website in the queue. So this is code using our input library that gets that job done. And then this is a little fooling around with regular expressions. We'll talk about algorithms like this later on that essentially tries to find all URLs within the text of that website. And for all of those URLs, and we'll look at what goes behind this code later on in the course. For all those URLs, it's going to check if it's marked. That's discovered.contains. And if it's not marked, it'll mark it and put it on the queue. A very simple program with a very powerful effect that illustrates breadth-first search. Now we'll look at topological sorting, a digraph processing application that doesn't quite have a parallel with undirected graphs. And it's a very general model that is very widely used. And here's the simplest example of it, called precedence scheduling. So the idea is that you've got a set of tasks that have to be completed, but there's precedence constraints. And you want to know in what order should you schedule the tasks. So you might think of this as like courses in a university curriculum. So as a model, we'll use the vertices will be the tasks, and the edges will be the precedence constraint. And all this says is there's an edge from 3 to 6. That means you have to take Introduction to Computer Science before you take Advanced Programming. And so there's all these sorts of constraints in the graph. And so what you want is what's called a feasible schedule. So that's just an order in which you can take a linear order in which you can take the courses one after the other that respects the precedence. So that corresponds to drawing the graph such that all the edges point upwards. And this model is used to study manufacturing processes and many other applications. So that's the topological sorting problem. So first thing is, a topological sort works on a DAG, so-called DAG. That's a digraph that has no cycles. if you have a cycle, there's no way you're going to be able to solve the problem. In fact, a simpler graph processing problem is just find out if a graph has a cycle. We'll talk about that in a second, but let's do topological sort first. So we know that the graph has no cycles. It's a directed acyclic graph. And what we want to do is find a way to redraw the DAGs so that all the edges point upwards, or give a bottom to top order so that all the edges are pointing upwards. That's called a topological order of the graph. And that'll give, in this case, an order in which maybe you could take the courses or perform the manufacturing process or whatever else. So that's the problem. So how we're going to solve it? Well, we're going to use DFS. In fact, one of the lessons for, particularly for digraph processing, is DFS is going to provide a way to solve it, and it might be hard to find a different way. So let's look at a demo of topological sort. And all it is just run DFS, but there's a particular point at which we want to take the vertices out or to get the order, and that's called reverse DFS post order. So let's look at how that works. All we do is, when we do the DFS, when we're done with a vertex, we put it on a stack or put it out. So let's look at how that works. We just run DFS the same as before, but we're not keeping track of anything except the vertices that we're done with. So visit vertex 0, we have to check the places that you can get to from 0. It's 1, 2, and 5. So we check 1. 1 is unmarked, so we're going to mark it and recursively visit 1. So we do that. We have to check 4. And 4 again is unmarked, so we recurse. But now both of the edges to 4 are in, so there's nowhere to go from 4. So we're done with 4. When we're done with 4, we output it, actually put it on a stack. So that's order. The order in which we're done with the vertices, that's called post order. So now, once we're done with 4, now we're done with 1. There's nowhere else to go, so we put it on the post order. Now we're back at 0, and we have to check the other vertices we get to from 0. So here's 2, we can get to from 2. It's unmarked, so we visit it. But there's no place to go, so we're done with it, so we put it on the post order and go back to 0. Then we go to 5, unmarked, so we visit it. Then we check 2, which is marked, so nothing to do, and then we're done with 5. Once we're done with 5, then we're done with 0, and that's the post order, the vertices that you get to from 0. So now we have to check all the other vertices in the graph. We have to find some other place, and so we just check the vertices in order. Next one that we find that's unmarked is 3. And so to visit 3, we have to check 2, 4, 5, and 6. And 2, 4, and 5 are all marked. So nothing to do. 6 is unmarked, so we go visit 6. When we visit 6, 0 and 4 are already marked, so there's nothing to do. Then we're done with 6, and finally we're done with 3. When we're done with a vertex, we put it out. That's post order, or if we put it on a stack, then we get reverse post order, and that turns out is the answer that we need. So the code is pretty simple, but we'll have to look a little more carefully to be convinced that it works. So it's depth first search, but we have an additional data structure, which is a stack of integers, which is the vertices in reverse post order. The constructor just creates that stack And then the only thing we change to DFS is when we're done with a vertex, before exiting, we put that vertex on the reverse post stack. And then the client simply gets the stack returned. That's an iterable, and iterating through that will give the vertices in the reverse DFS post order, which is the topologically sorted order. It's a very simple and compelling use of DFS. Actually, this is an amazingly simple algorithm, but it went undiscovered for many years. People were using much more complicated algorithms for this problem. Okay, so reverse DFS post order of a DAG is a topological order. That's the correctness proof that we have to consider. This diagram over here is a record of the recursive calls for that example that we just did. To visit 0, we call it visit 1, and then we visit 4, and then we're done with 4, and then we're done with 1, and then we visit 2, done with 2, then do 5, which checks 2, and 5 done, and so forth. So this gives a record of the calls just for reference in this proof for that example. All right, so now we want to consider any edge where V points to W, and we want to consider the point where DFS of V is called. And there's a bunch of cases. One case is that DFSW has already been called and returned. So in this example, when V equals 3, W equals 2, 4, or 5, they were already done. So if we put out those vertex numbers before we put 3 out, then the arrow from V to W is going to point up. They were already done. So that's case 1. That's an easy case. Case 2, they're all easy cases. Case 2 is DFSW hasn't been called yet, but if there's an edge from V to W, we're going to call it, and then it's recursive. It's going to finish before we're done with 3. So again, the edge from V to W is going to point up 3 to 6. And the only other possible case might be that DFSW has already been called but not returned. But that can't happen because there's no cycles. If DFSW had been called but not yet returned, then the function call stack is going to have a path from W to V on it, and so if we have an edge VW, that would give a cycle, but there's no cycles. So from those observations, we know that all vertices pointing from 3 are done before 3 is done, so they appear after 3 in the topological order, or they point up if we put the vertices in reverse topological order. So that's a correctness proof for topological order. So a similar process is to detect a cycle. Topological sort doesn't work if a graph's got a cycle, so one of the things we might want to do is just find cycles in digraphs. If you're a college and you put out a curriculum that's got a directed cycle, you have a problem, so you might want to process that first. If there's a directed cycle, you can't have a topological order. If there's no directed cycle, then we just found it. So one thing you might want is, given a digraph, find a directed cycle, and how are you going to do that? You're going to use DFS, and that's a simple algorithm that you might want to think about. It's in a few lines in the book. Precedence scheduling is an excellent example of the use of search in a directed graph. This is the cycle of length 1, of course, that requires itself as a prerequisite. This is just an example of a very widely used computation. It really has many, many applications. So for example, the Java compiler actually does cycle detection. If you have a class A extends B, and another one B extends C, and another one C extends A, that's going to create a problem. A class hierarchy is not supposed to have cycles, and it'll actually, the Java compiler will actually give a error message saying there's cyclic inheritance. You're not allowed to do that. So there's many applications that involve essentially digraphs that aren't supposed to have cycles. Another example is Microsoft Excel. So if you do a cyclic reference like this in Excel, which in a big spreadsheet you can imagine might happen, that's an error. And not only does Microsoft Excel flag the error, it says you have created a circular reference. Try one of the following. And it's actually got a circular reference toolbar that will help you figure out what to do in that case. So cycle detection and topological sorting are important applications of depth-first search in digraphs. As our final digraph processing algorithm, we'll take a look at computing strong components. So the definition, two vertices V and W in a digraph are strongly connected if there's a directed path from V to W and another directed path from W to V. And the thing about strongly connected is that it's an equivalence relation. That is, each vertex is strongly connected to itself. If V is connected to W strongly and W is strongly connected to, then W is strongly connected to V. That just means there's directed paths connecting them. And it's also transitive. If V is connected to W and W to X, then V is strongly connected to X. To get from V to X, you go from V to W and W to X. And to get from X to V, you go from X to W and W to V. So that means that since it's an equivalence relation, it divides the digraph up into sets called strongly connected components that have the property that there's directed paths connecting each pair of vertices in the set. So for example, 9 and 12 are strongly connected. There's a path from 12 to 9, another one from 9 to 12, and so forth. So our challenge is to compute the strong components in digraphs. And it's worth comparing this to what we did for connected components in undirected graphs. So this is just a quick review. In an undirected graph, if there's a path between two vertices, they're connected. That's an equivalence relation, divides them up into connected components. And what we did was, our design pattern is to build our graph processing algorithm as a constructor that takes a graph and does the pre-processing to create a table like this one, which assigns a unique ID to all the vertices in each given component, so that we can have a constant time client query to check whether two given vertices are in the same connected component or not. So linear time processing, pre-processing in the constructor to build the table, constant time client queries. And that's as good performance as we could expect to have for a graph processing algorithm. Remarkably, we're able to do the same thing for strong connectivity. It's a much more sophisticated algorithm, but the design pattern and the bottom line for the client is the same. There's a constructor that processes the graph in linear time and assigns a unique ID to each one of the strongly connected components in the graph. So one's in a component by itself, 0, 2, 3, 4, and 5, 6 and 8, 7, and 9, 10, and 12. There's 5 different strongly connected components in this graph. The constructor builds that array, and the client gets to, in constant time, know whether two vertices are strongly connected or not. It's quite amazing that we can solve this problem in this way. And as I mentioned, it's got an interesting history that I'll talk about in a second. So here's an example of strong component application. So the food web graph, this is a very small subset of that graph. The vertices are all the species, and an edge goes from producer to consumer. So if animal A eats animal B, there's an edge from A to B. And what a strong component corresponds to in this graph is kind of a subset of species that have a common energy flow. They mutually eat each other. And that's extremely important in ecological studies. Another example is, again, in processing software. Big software is made up of modules, and the vertices are the modules, and edges if one depends on another. And so a strong component in this graph is a subset of mutually interacting modules. And in a huge program like Internet Explorer, you want to know what the strong components are so that you can package them together and maybe improve the design. So again, software these graphs can be huge, and this kind of graph processing can be extremely important, improving the design of software. Now again, this algorithm has an interesting history. Along with scheduling and other things, it's a core problem in operations research that was widely studied, but really not understood how difficult it was. In Tarjan's paper in 1972 was a big surprise that this could be solved in linear time with depth-first search. Now, this algorithm had a couple of other data structures and is, I guess, a diligent student in this class could understand it with quite a bit of work. But it really demonstrated the importance of depth-first search in graph processing. Now, the algorithm that we're going to talk about today actually was invented in the 80s by Kosaraju and independently by Sharir. And the story goes that Kosaraju had to go lecture about Tarjan's algorithm, and he forgot his notes. And he had taught it a number of times. He was trying to figure out what Tarjan's algorithm did. And he developed this other algorithm that's extremely simple to implement, and that's what we're going to look at today. And actually, in the 1990s, Gabau and Melhorn, particularly Melhorn, had to implement this algorithm for a big software package, and he found another simple linear time algorithm. So this story indicates even for fundamental problems in graph processing, there's algorithms out there still waiting to be discovered. And this algorithm is a good example of that. So I'll give the intuition in the code, and you see how the algorithm works. Fully convincing yourself or proving why it works is a bit more of a challenge. We'll leave that mostly for the book, but let's describe what it is. So the first idea is to think about the reverse graph. So if we take a graph and we reverse the sense of all the edges, we're going to get the same strong components. We need edges in both directions, so if we switch the directions, we're still going to have edges in both directions. The second concept is called the kernel DAG, and what that does is it kind of, you think about contracting each strong component into a single vertex. And then just worry about the edges that go from one strong component to another. So the digraph that you get that way turns out to be acyclic. If it was cyclic, it would involve, it would create a bigger strong component, it would coalesce a couple of strong components into one. So if we think about that processing, that kernel DAG, that's the edges that go between strong components. And we get a DAG, and we know how to deal with a DAG. So the idea of the algorithm is to go ahead and compute the topological order or the reverse post order in the kernel DAG, at least put out the edges of the original digraph in order so that all the edges in the kernel DAG point from right to left. That's like a topological sort. And then we run DFS, but instead of considering the vertices in numerical order for the DFS, we consider them in that reverse topological order. So it's extremely easy to implement this algorithm. Of course, we're going to use DFS. So let's look at a demo at how the algorithm works. Okay, so this is a digraph, and our goal is to compute the strong components. And we're going to do it in two phases, two DFSs. One is to compute the reverse post order in the reverse of the graph, and the other is to run the DFS, but for the order in which we visit the vertices, we use that reverse post order that we computed. So here goes. So first we'll do the DFS in the reverse graph. That's the graph, that's the reverse graph. Remember, these two have the same strong components. There's our marked array. We do the DFS, and reverse post order means that when we're done with the vertex, we put it out. Check 6, unmarked, check 8, unmarked, check 6, it's marked, so we're done with 8, and so that's the reverse post order. And again, as before, I put it on a stack, but we'll just list them in reverse order in this demo. So 8's done, so 6, lots of places to go from 6, so let's check 7. That's unmarked, so we go to 7. No place to go from 7, so we're done with 7. We put it on the reverse post order list. We're also done with 6 because 4 and 9 are coming in this example, so put it on the list. Next place to go from 0 is 2, so we check 2. That's unmarked, so we mark it and recurse, and we check the vertices adjacent to 2. First 4, that's unmarked, so then we recurse and go to 4. We got to go to 11 first and recurse. So now we're at 11. And from 11 we go to 9, which is unmarked. So we have a pretty long recursive stack right here. So from 9, we have to check a bunch of things. We'll check 12 first and then visit 12. It's unmarked. From 12, we check 11, which is marked, nowhere to go. Then we check 10, that's unmarked, so we go to 10. Visit 10, it's unmarked, so we recurse, and then go to 9. And that's marked, and that's everywhere we get from 10, so we're done with 10, so we put it on the list in return. And now we're done with 12, so we put it on the list and return. And now at 9, we have to check 7, which is marked, and 6, which is marked, and then we're done, so we put it on the list. Then we're done with 11, we put it on the list. Then we're finished with 4, so we check 6, which is marked, and we check 5, which is unmarked, so we recurse to 5. From 5, we check 3, which is unmarked, so we recurse. Then we check 4, which is marked. We check 2, which is marked, and then we're done with 3, so we put it on the list. And then from 5, we check 0, it's marked, so we're done with 5, we put it on the list. And that means that we're now done with 4, and then we're also done with 2 after checking 3, and then we go to 0 and put it on the list. So that's all the vertices that you get to from 0. We look for more vertices, and it's 1, and it's marked, so that's the last one in the reverse post order. So that's a reverse post order of the reverse graph. And all we're going to do is take that order and use that order to check vertices at the top level in the depth first search of our regular graph. We have to check all the other vertices to make sure we're done. So that's phase 1. So now we just do a DFS in the original graph using that order that we just computed. So we don't start with 0 the way we always have. Now we start with 1. We visit 1, it's unmarked, and now all the vertices that we visit during that DFS are going to be in the same strong component. That's the theorem that makes this algorithm work. In this case, there's only the 1, so vertex 1 is in its own strong component with label 0. So now we've got to start, 1's all done, so now we have to start with looking for another vertex to search from. In this case, it's 0 is second on the list, so that's where we start with 0. And now all the vertices that we can reach from 0 are going to have strong, in this graph, are going to have strong component label 1. So we do the DFS. So first we get to 5. That's in the same strong component. We check 4, and it's unmarked, so we label it. We check 3, it's unmarked. We check 5, which is marked. We check 2, which is unmarked. So now we have shown that 0, 2, 3, 4, and 5 are all in the same strong component. And now we're going to find both vertices we get to from 2 are marked, so we're done with 2. Then we're done with 3. 4, we have to check 2, which is marked, and then we're done with 4 and 5. From 0, we can check 1, but that's already marked, so that's not relevant for this search. And then we're done with 0, and we've established that 0, 2, 3, 4, and 5 are all in the same strong component. So that's the second one. So now we continue and we check all of those, and they're all marked. So the next vertex in the reverse post order reverse graph is 11. So we visit 11, check 4, it's already marked. Check 12, it's not, so we mark it, and these are the third strong component. They get labeled with 2. Then we get to 9. From 9 we check 11 and nowhere to go. Then we check 10, and so that's in the strong component. From 10 we check 12, which is marked. We're done with 10. We're done with 9. We're done with 12, and we're done with 11. So that's our second third strong component, 9, 10, 11, and 12. So we're done with those, and now we go through the list to find another unmarked vertex. 9's marked, 12's marked, 10's marked. We get to 6. From 6, 9's already marked, 4's already marked, 8's not marked, so we go there. From 8 we can get to 6, and that's it. 0's already marked, so we can only get to 8 from 6 at this point, and so that's a strong component. And then finally we finish up by doing 7. So the end of the computation gives us the strong component array, which is a unique ID for each of the vertices, so that 2 vertices in the same strong component have the same ID, and that supports constant time strong connectivity checks for clients. So the bottom line is that this algorithm is a very simple, even though it might be mysterious, algorithm for computing the strong component. First, run DFS on the reverse graph to compute the reverse post order. Then run DFS on the original graph, considering the vertices in the order given by the first DFS. These diagrams give a summary of the computation. I'm not going to spend too much time explaining why and how it works in this lecture, but these kinds of diagrams give the detail that can give some intuition about how and why the algorithm works. For the proof, it requires some mathematical sophistication, and you'll find it in the book. But the programming of it is quite simple, and prove that it's efficient all it does is run DFS twice. But to really see the correctness proof, you want to look at the second printing of the textbook. We got it wrong in the first printing. But look at the implementation. So this is connected components in an undirected graph with DFS that we did last time. and I'm sure many of you thought it was one of the simplest algorithms that we looked at. We just mark the vertices and do recursive DFS, and that's the end of it. If you take that code and just add, well, change the names, and then just instead of going for the vertices from 0 through v minus 1, if you first compute the depth first order that you get by running doing a depth first search of the reverse graph, and then you iterate through the vertices in that order, you get an algorithm for strong connectivity. It's really remarkable that just changing that one line will perform this computation that was thought to be difficult for many years, and people were learning quite difficult codes for it for many, many years. So that's a quick summary of digraph processing. We talked about single source reachability, getting the paths from a vertex to any vertex that can be reached from that vertex with a directed path. We talked about topological sort in graphs that have no cycles, and that uses DFS. And we talked about computing strong components in a digraph with 2 DFSs. Digraph processing is really a testimony to the ingenuity that's possible in algorithmic graph processing. Today we're going to talk about minimum spanning trees. This is a terrific topic for this course because it combines a number of classic algorithms with modern data structures to solve a variety of huge problems that are important in practical applications nowadays. We'll start with a brief introduction. What is a minimal spanning tree? Well, it's defined on a graph. Now we generalize the idea of a graph one more time to allow weights on the edges. So these are positive numbers associated with each edge. And let's say the graph is connected. So we have a connected graph with weighted edges. Now a spanning tree of a graph is a subgraph that is connected and has no cycles. So out of all the spanning trees, we want to find one that has minimum weight. So that's not a spanning tree because it's not connected. This set of black edges is not a spanning tree because it's not acyclic. But here's one that is a spanning tree. And if you add up the weights of all the edges, 4 plus 6 plus 8 plus 5 plus 11 plus 9 plus 7, that's 50. And you could see maybe you could get another spanning tree by removing this edge and adding that edge. That'd have slightly higher weight. And so the goal is to find a spanning tree of minimum weight. Now, there is a brute force algorithm that is impractical and probably would be difficult even to code up, and that is let's try all possible spanning trees. Now, certainly we want to do better than that. Here's some examples of some huge spanning trees that are being worked on in practice nowadays. This is the bicycle routes in Seattle. And it kind of gives a quick way to get from downtown out to the suburbs, you can see. This is the idea of an MST as a model of natural phenomenon. And there are many observed natural phenomenon that seem to be well modeled by spanning trees. This is a purely random graph and a minimal spanning tree of that random graph. And this is an image that came up in cancer research having to do with the arrangement of nuclei in the epithelium. And you can see that this tree that's observed in nature is quite similar in character to the MST of the random graph. So that's another example. This is an example from image processing. There's a process known as dithering to remove fuzziness in medical and other images. And computing the MSD of a huge graph built from such images is yet another application. So it's bottom line for this introduction is that MST is easily defined. It's the minimum weight set of edges that connect the vertices in a weighted graph. And it's got diverse applications from dithering and face verification to road networks in satellite imagery to Ethernet networks and to network designs of all kind. And it goes back a long way to the even early 20th century for electrical and hydraulic networks. So that's an introduction to the idea of a minimum spanning tree. To introduce the algorithms for minimum spanning tree, we're going to look at a general algorithm called a greedy algorithm. It's a good example of a general principle in algorithm design that will help us prove correctness of our algorithms. To begin, we'll make some simplifying assumptions. First, we assume that the edge weights are all distinct and that the graph is connected. And this is just to simplify the presentation. As a consequence of these two assumptions, we know that the minimum spanning tree exists and is unique. Our algorithms will still work when edge weights are not distinct. If the graph is not connected, it'll find spanning trees of components, but these two assumptions simplify the presentation. Now, to understand our algorithms, we're going to start with a general operation on a graph called making a cut. So a cut in a graph is a partition of its vertices into two non-empty sets. And we'll indicate that just by coloring some of the vertices gray and others white. So that's a partition into two sets, the gray vertices and the white vertices. Every vertex is either gray or white, and there's at least one in each set. Now, given a cut, a crossing edge connects a vertex in one set with a vertex in the other. So every edge that connects a gray vertex to a white vertex is a crossing edge. So that's a second definition that gives us a way to talk about edges and graphs when we compute the minimum spanning tree. So an important property that is relevant to MST algorithms is that given any cut at all, the cut defines a set of crossing edges. The minimum weight crossing edge is in the MST. Remember, no two edges have the same weight, so there's a single edge that has minimum weight from the edges in the cut. So in this case, the thick red edge is the minimum weight. It's the shortest edge connecting a gray vertex with a white one, and that edge has to be in the MST. That's the cut property. Here's just a quick proof of that property. I'll hand wave a bit through the discussions of the proof. It's usually not appropriate to fully dimension proofs in the lecture, so you should look at the book or the online materials to be sure that you understand the proofs or reread these slides. But I'll try to give all the steps. So we're trying to prove the cut property, giving any cut the crossing edge minimum weights in MST. So let's suppose the contradiction. So suppose that we have a minimum weight crossing edge that's not in the MST. So in this case, that edge E, suppose, is not in the MST. It means that one of the other crossing edges has to be in the MST, otherwise the MST wouldn't be connected. Then if you add E to the MST, you get a cycle, and some other edge in that cycle has to be a crossing edge. That's the way to think about it. Remember, MST is the minimal way to connect the graph, and if you add an edge to a tree, you get a cycle, and then there's some other edge that has to be a crossing edge. But if you remove that edge and add E, then you're going to get a spanning tree, and that spanning tree is smaller than the one that you had. So that supposition had to be a contradiction. So it has to be that the minimum weight crossing edge is in the MST. So that's the cut property. So now given that property, we can develop what's called a greedy algorithm, which is the easiest algorithm we can come up with. So what we're going to do is start with all edges colored gray, find any cut that has no black crossing edges. The algorithm's going to color some of the edges black, and color the minimum weight edge of that cut black, and just repeat the algorithm, finding any cut with no black crossing edges, color the minimum weight edge black, and keep going until you have v-1 edges that are colored black. And the claim is that that's going to compute an MST. Let's look at a demo of that just to make sure that we follow what's going on. So we start with all edges colored gray. We're supposed to find a cut with no black crossing edges and color its min weight edge black. Well, that could be any cut. In this case, we'll take the cut that has 3, 2, and 6 on one side and 1, 0, 0, 1, 4, 5, 7 on the other side. Look at all the crossing edges. Minimum weight crossing edge is the one from 0 to 2. So that's the one that will color black. So now we have 0, 2 on the MST, it's colored black. So again, any cut that doesn't have a black crossing edge. So in this case, let's do the cut that just has 5 on one side and all the others on the other side. In this case, there's 3 crossing edges. The smallest one is 5, 7. Color that one black. Again, any cut that has no black crossing edges. So let's just take 6, the cut that has 6 on one side and all the others on the other. 2, 6 is the minimum crossing edge. So 6, 2, and so we put that one on the MST. As we get more and more black edges, it's going to be harder to find a cut with no black crossing edges, but we press on. So now let's do the cut with 0, 2, 4, and 6 on one side colored white, and 1, 3, 5, and 7 on the others. So there's a lot of crossing edges in that cut, but the smallest one is the one between 0 and 7, so that's the one that we color black and add to the MST. So now we have 4 edges. Next cut, 1 and 3 on one side. Smallest edge in that, the smallest crossing edge for that cut is 2, 3. Now one more. Now let's put 1 and 4. Now almost all the edges left are crossing edges. So 1 and 4 on one side, all the rest are in the other. And the minimum weight crossing edge is the one from 1 to 7. Notice in this case we got the nodes in the tree on one side of the cut and the nodes not in the tree on the other side of the cut. One of our algorithms will always have that property. So now we add 1 and 7 to that, and now the last thing is the only cut that has no black edges is the one that puts 4 on one side and all the rest on the other, and the minimum weight crossing edge for that one is 5, 4. So now we've got 8 vertices and 7 vertices in the 7 edges in the MST. So we've found the MST. We've got v-1 edges colored black, and we've found the MST. So the greedy algorithm is a very general algorithm. We're allowed to find any cut at all that has no black crossing edges. So let's do the correctness proof, and then we'll look at some specific instances of the greedy algorithm. First of all, since we took the minimum crossing edge of a cut always to color black, any black edge is in the MST. That's the cut property. Do a cut, no black crossing edges, you can color it black. That's in the MST. So that's first observation. Now, when we have fewer than v-1 black edges, there has to be a cut that has no black crossing edges. That is, the algorithm doesn't get stuck. And so the way to think about that is just take the vertices in one of the connected components and make that the cut. Then there's going to be, since that's a connected component, there's going to be no black edges in the crossing edges for that cut. So the algorithm doesn't get stuck. If you don't have an MST yet, there's going to be some cut with no black crossing edges. And that's it. The greedy algorithm computes the MST. Any edge colored black is in the MST, and you can always add to the set of black edges if you don't have V-1. Once you have V-1, you've got V-1 edges that are in the MST. The MST has V-1 edges. Greedy algorithm computes the MST. So now what we want to do is implementations of the greedy algorithm or specializations of it really that differ in, first of all, the way that they choose the cut, which cut are we going to use, and also the way in which they find the minimum weight edge in the cut. Again, those could both be expensive operations and prohibitively expensive for huge graphs. What we're going to look at is two classic implementations called Kruskal's algorithm and Prim's algorithm, although in both cases we use modern data structures to make them efficient for huge graphs. And there's another interesting algorithm called Borufka's algorithm that kind of combines the two, briefly mentioned. Now, before getting to those, what about removing the two simplifying assumptions? So what happens if you have a situation where the edge weights are not all distinct? So in this case, 1, 2, and 2, 4 both have the same edge weight. Well, so also to 1, 3, and 3, 4. And so it means there's multiple MSTs. So in this case, there's two different MSTs. So the greedy algorithm is still correct, it turns out. Our correctness proof doesn't quite work, but that can be fixed with a little bit work. And so the fact is it's still correct. And if the graph is not connected, as I mentioned, what we'll get is what's called a minimum spanning forest, which is the MST of each component. Essentially, it's like independently computing the MSTs of the components. But basically, what the greedy algorithm gives us is an easy way to prove correctness for specific algorithms. All we have to show is that they're finding a cut and taking the minimum weight edge from that cut. And then we can prove correctness of a more complicated algorithm. In general, in algorithm design, this is proven to be effective in all kinds of domains. Trying to come up with a general algorithm that you can prove works efficiently, and then using that to help design specific. So before we can develop code for our implementations, we need to settle on an API for edge-weighted graphs. Now, this actually needs a bit of discussion. It would seem to be simple to add weights, but there's a few technicalities that it's easy to understand, but it's going to take a little explanation. So the whole idea is that we need an edge abstraction. Before, for directed graphs and undirected graphs, we're talking about graphs in terms of connections. And the edges were really implicit. So for a vertex, we'd keep a bag of vertices that it's connected to, but we wouldn't explicitly represent edges. For weighted edges, we're going to need to do that. So we're going to start out with an abstraction just for processing edges. Now it's simple. The constructor is just going to create an edge. So what is an edge? A weighted edge is two vertices that it connects, and then a double value, which is the weight. So that's clearly one thing we have to do is construct the edge. Now, what do we want to do when we process edges? Well, one thing we want to do is compare two edges. So that is, we want to compare the weights in a typical compare and return a negative value if less than 0 if equal and a positive value if 1, just like any other compare. So we want a method that takes an edge as argument and compares that edge to this edge for sure. We want to be able to extract the weight and have a string representation of the edge. But then what about getting the vertices out of the edge? Well, the fact is that usually in the algorithm, we're holding on to a vertex. And generally what we want to do is get the other vertex. So if we have a vertex v that we're holding on to, what we want is the other vertex. So that's the way that we'll get the vertex to that a given edge. We're on a vertex and we have an edge. We want to get the edge the vertex that connects to, we just call the other method. And if we have an edge and we're just getting started, then we're happy to take either vertex. So we have either and other for getting the vertices out of the edges. And we almost always do this kind of idiom where we pick out, we have an edge E that we have to process. We pick out either edge and put that in V, and we pick out the other edge and put that in W. So that's just code for getting us the V and W without adopting some convention on how to use those names that might be required if you tried to access the instance variables directly or through getter methods. So that's the Edge API. So it's easy to implement. We're going to have instance variables for V and W and the weight. The constructor just sets those instance variables. Either just returns V arbitrarily, and then other, given a vertex, that vertex is V, it returns W, otherwise it returns V, so that's easy. And then compare to is straightforward, just using the weight instance variable of this, which is the keyword referring to this object, and that, which is the argument edge that we're given. So that's a complete implementation of the weighted edge API, and now our MST algorithms can be clients of that. First we need a graph API that has weighted edges. We're going to use edge-weighted graph, and it's going to have the same characteristics of the graph and directed graph API that we articulated before. We're going to create empty graph with a certain number of vertices, and we do that so we can use vertex indexed arrays as internal data structures. We'll have create a weighted graph from an input stream. Then the main operation to build graphs is just to add edges. And then the key operation that all the algorithms want to perform, as usual, is an iterable that give all the edges adjacent to a given vertex. So now we want the edges themselves, because they have the weights, not just the vertex that it's connected to. So this, with the edge API, the edge abstraction, we get the edge, which gives us the weight and the other vertex at the same time. Since we're using edges as distinct entities, it's easy to allow self-loops in parallel edges in the Graph API, and it doesn't have any impact on the MST algorithm, so we'll go ahead and do that. How do we represent edge-weighted graphs? Well, it's the straightforward extension of what we did for undirected graphs. We're going to maintain a vertex indexed array of edgeless. For every vertex, we have a list of the edges connected to that vertex. For example, in this graph, weighted graph, there's an edge. The ones connected to vertex 0 are an edge that connects 6 and 0 and has weight 0.58, and an edge that connects 2 and 0 and has 0.26. 0 and 4 has 0.38, 0 and 7 has 0.16. As with our undirected graph representations, each edge object is going to appear twice, once for each vertex that it connects. And it's actually not the object, it's a reference to the object in Java. So a graph is a vertex indexed array of bags of edges. And since it's undirected, each edge is going to appear twice. So when we build a graph, just as with undirected, unweighted graphs, we have to add, if we have an edge that connects V and W, we have to add that edge to both V and W's adjacency lists. Otherwise, it's quite similar to our code for graph. We have a bag of edges instead of a bag of integers, which are vertex indices. Constructor builds the bag and builds the array and then fills the bag associated with each vertex as a new empty bag. And then add edge adds the edge to both V and W's bag. And iterable just returns the bag associated with the given vertex, and that's all the edges that are incident on that vertex, and that's a bag which is iterable. So again, as for all the algorithms that we've been looking at, the clients will just iterate, usually have a vertex, and it'll iterate through the edges adjacent to that vertex. So that's the representation of the graph. What about representing the MST? Well, usually the client of an MST algorithm is going to want to have us compute the MST for a given edge-weighted graph. So we'll just do that in a class named MST and make that the constructor. So then, as usual in our graph processing paradigm, the constructor will do all the work, and then the client can ask queries about what happened. And in this case, what's relevant is what are the edges in the MST? And the MST client is just going to want to iterate through those edges. It might also want the total weight of the MST, so we can provide that too. For example, if we take an example with our tiny edge-weighted graph, we're going to have the number of vertices, the number of edges, and then a list of vertex pairs, which are the edge connections and the associated weights. What we'll want is this is the test client is just going to print the edges in the MST, the minimal weight edges that connect them all, the set of edges in the MST, and the weight. And this is the code for that test client. We build an input stream, which is given the argument, so that's the file name. And then we use the constructor from the input stream to build an edge-weighted graph. Then we do an MST, calling the MST constructor with that graph as an argument. That creates an MST. And then we use the iterator, that MST.edges will give us an iterable set of the edges that are in the MST that it computed in the constructor. And it'll print out the edges using toString for edge, and then print out the weight. So that's the code that gives the test client for this MST API. So for that graph, we get that output with that code. So that's the quick introduction to the APIs we use for MSTs. Now we'll look at Kruskal's algorithm for computing the MST. This is an old algorithm that dates back over 50 years, but it's an effective way to solve the problem. The idea is very simple. We're going to take the edges and we're going to sort them by weight. And we're going to consider them in order of ascending weight. And the algorithm is simply add the next edge to the tree unless that edge would create a cycle. If the edge creates a cycle, ignore it and go on to the next one. Let's look at a demo of Kruskal's algorithm. Okay, so we have the edges sorted by weight, and we're going to take them in ascending order of weight. The smallest edge is in the MST, and so we add that to the tree. Doesn't create a cycle. Next smallest edge is 2, 3. That doesn't create a cycle. Next one is 1, 7. That's fine. Next one is 0, 2. Next one, 5, 7. Now, when we get to 1, 3, that one creates a cycle. And the algorithm says, creates a cycle, just ignore it. Next one is 1, 5. That one also creates a cycle, 1, 5, 7. Again, just ignore it. 2, 7 creates a cycle, not in the MST. 4, 5, that next smallest edge, does not create a cycle, so we add it to the MST. 1, 2 creates a cycle, 4, 7 creates a cycle, 0, 4 creates a cycle, and finally we get to 6, 2, which does not create a cycle, so we add that to the tree. At this point, we have an MST. We could check that we have v-1 edges and stop, or we can just keep going and see that the other edges in the graph create a cycle. And when we're done considering all the edges, then we have computed the minimum spanning tree. That's with Kruskal's algorithm. Consider the edges in ascending order of weight, add the next edge to T, unless doing so would create a cycle. Now let's look at what Kruskal's algorithm does on a very large graph. You get a good feeling for what it's doing. It's taking the small edges and they coalesce together in little clusters, and eventually the edges get longer and longer, and they connect together the clusters. But initially it's broken up into the very small edges. And after a while, if you look at the larger clusters, eventually an edge will come that'll connect them together. It's not going to be so easy to see how the algorithm ends. There's some long edge there. That's the longest edge in the MST that'll finally connect the graph. This simulation really gives a good feeling for Kruskal's algorithm. In fact, when we first had personal computers, I was fortunate enough to be at Xerox PARC, and I remember very well in the late 70s, this is one of the first algorithms that I wanted to see visualized on a personal computer. And I wrote a program at that time that produced pretty much this image. It's a very interesting way to look at MST algorithms. All right, so it's easy to implement. We have to prove that it computes the MST, of course, and we've done a lot of work setting that up, and we do so just by proving that it's a special case of the greedy MST algorithm. So what does that mean? Well, suppose that Kruskal's algorithm colors a given edge black. So say it's VW. So we'll define a cut that is the set of vertices that are connected to V. So it might be just V, but if there's any black edges connecting V to other vertices, we put all of those in the cut. So for that cut, there's no black crossing edge because it's a component. And the other thing is that there's no crossing edge with lower weight than VW. And why is that? Well, we haven't examined any of those edges yet, and they're all longer because we're considering the edges in increasing order of their weight. So this new edge that connects V somewhere else is a crossing edge of minimal weight, and so therefore the algorithm always finds a cut and colors the crossing edge of minimal weight for that cut black, and it's an instance of the greedy algorithm. Now, we still are a bit away from having an implementation of Kruskal's algorithm. So the question is, how do we know whether adding a new edge to the tree will cause a cycle? So you might think about how difficult that is. I've got a tree that's represented as a set of edges or however, and I have a new edge, and I want to know whether it creates a cycle or not. How difficult is that going to be? Well, it turns out way back in the first lecture of Algorithms Part 1, we had a way. Well, one thing we could do is just run DFS to check if we can get to W from V. That would take time proportional to V. But the union find data structure that we did in the first lecture absolutely does the job. It's just testing whether this edge connects anybody in the equivalence class corresponding to V with anybody in the equivalence class corresponding to Y, to W. And if it did, it creates a cycle. So union find is exactly what we need. So what we're gonna do is maintain a set for each of the connected components in the spanning tree that we've built up so far. And so if the new edge connects vertices that are in the same set, then that means it would create a cycle. Otherwise, we're going to be adding the edge to the tree, so then we just do the union operation and merge the set containing V with the set containing W. Those are the two things that we need to do, and those are the two things that union find does for us. So this leads to a very compact implementation of Kruskal's algorithm. Now, to consider the edges in order, we'll use a priority queue, a modern data structure. Let's take a look at every line in this implementation of Kruskal's algorithm. We're going to have a queue of edges. That's how we're going to represent the MST. It could be a stack or a bag, but we'll use a queue. And then the Kruskal MST algorithm takes a graph, and it's going to compute the MST in this MST. And to do that, it's going to use a priority queue, a min priority queue, minimum oriented priority queue of edges. We'll build that minimum priority queue. Now edges are comparable. We had a compare to method. So our generic priority queue code is going to work fine. And so what we'll do is we'll put all the edges in the graph into the priority queue. So that's building a priority queue containing all the edges in the graph. Alternatively, we could put the edges in an array and sort the array, but priority queue is a more elegant way to express this, and it is a way to look at more efficient algorithms as well. Okay, so that's priority queue, so that's a first data structure from part 1 that we're going to make use of. And then the second one is the union find data structure. So we're going to build a union find data structure for vertices because the spanning forest divides the vertices into equivalence classes. So then we go into the main loop. And the main loop stops in two conditions. We run out of edges is one, or would have a minimum spanning forest, or the other condition is we get to V minus 1 edges in the MST. As long as neither one of those is true, then we've got an edge in the priority queue, and we want to take the smallest one. We want to get its vertices, V and W, either another. And then we want to check using the union find algorithm if they're connected. If they're connected, we don't want to do anything. If they're not connected, then we want to merge them and put that edge onto the MST. That's it. And then that's the full implementation. And then we have the edges method for the client to return the MST. It's quite a compact implementation of a classic algorithm using the basic data structures that we built up in algorithm part 1, data structures and algorithms of priority queue and union find gives a really fine implementation of this MST algorithm. So what about the running time of this algorithm? Well, it's not hard to see that it's going to compute the MST in time proportional to E log E. It's linear-arithmetic in the number of edges, which means that we can use it for huge graphs. So this table is just a proof that summarizes the costs. We're going to first build the priority queue, and we can do that in linear time using bottom-up construction method. We have to, every edge comes off the priority queue, so there's E of them, and it takes log E per operation. And then union operations, every vertex is involved in one, and connected operations, every edge is involved in one. So the total time is dominated by the E log E for the priority queue operations. One thing to note is that if the edges come in sorted order for some reason, it's almost linear. The order of growth is E log star V. Actually, we don't have to always sort them. We can, in real life situations, we can stop when we get the V-1 edges in the MST. When we have those V-1 edges, we can stop, and usually that's for practical situations. That's way before we see all the edges in the graph. So that's Kruskal's algorithm for computing the MST. Next, we'll look at another classic algorithm for computing the MST called Prim's algorithm. It's also an extremely simple algorithm to state. What we're going to do now is start with vertex 0, and we're going to grow the tree one edge at a time, always keeping it connected. The way we're going to do that is add to the tree the minimum weight edge that has exactly one endpoint in the tree computed so far. And we'll keep doing that until we've grown the whole V-1 edge tree. Let's look at a demo to see how that works. So we start with vertex 0, and we're supposed to add the min weight edge that's connected to 0. So that's 0, 7. Out of all the edges connected to 0, that's the one of minimum weight. So now we have one edge, 2 vertices on the tree, and so now we want to add the min weight edge that connects to the tree. In this case, that's 7, 1. Out of all the edges that connect to the tree, 1, 7 is the shortest one, so that's the one that we add. So now we have 2 edges on the tree. Continuing, now the min weight edge that connects to the tree is 0, 2. So we add that one. So now we have 3 edges, 4 vertices on the tree. Closest vertex to the tree, or the smallest edge coming out of the tree, is 2, 3. So we add that one. So now we have 3 more vertices to go. And you can see that the next one that's going to come is 5. That's closer to the tree than 4 or 6. So we do that, add 5. Now there's 2 more. And so out of all those edges, the closest one to the tree is 4, 5. It's a little shorter than 4, 7 and 0, 4. So that's the one that gets added. And then finally, 6 gets added to the tree by the shortest edge that connects it to the tree, which is 6, 2. So start with vertex 0, add an edge at a time to the tree, It's the shortest edge that goes from a tree vertex to a non-tree vertex. That's Prim's algorithm. Now let's look at Prim's algorithm running on the same huge graph that we ran for Kruskal's. This also is a fascinating dynamic process. Usually the new edge is close to the last edge added, but every once in a while it gets stuck and so jumps to a new place to add edges to the MST. This algorithm's a little bit easier to follow, but it's a very interesting dynamic process. You can see that it when it's easy, it just sticks where it was, and when it runs into some long edges, it gets stuck and tries somewhere else. Always adding to the tree, the shortest edge that connects a non-tree vertex to a tree vertex. And you can see the last few things to be added were the vertices in the upper left corner. So that's a visualization of Prim's algorithm. Completely different character, but it comes out to the same tree as Kruskal's algorithm, as long as the edge weights are distinct. So we need to prove Prim's algorithm correct. And this one has been rediscovered a few times, depending on how you cast the data structure for implementing finding the minimum. But the basic algorithm has been known since at least 1930, and it's a proof that it computes the MST, again, comes because it's a special case of the greedy MST algorithm. So let's suppose that E is the min weight edge connecting a vertex on the tree to a vertex not on the tree. Well, you take as you cut the tree vertices, there's no black crossing edge from the tree vertices to non-tree vertex. That's the definition, it's not on the tree. And there's no crossing edge of low weight, because that's the minimum one that we picked by design. So it's a special case of the greedy algorithm where you take as the cut the set of vertices currently on the tree. That's Prim's algorithm. Now, how are we going to implement Prim's algorithm? How are we going to find the minimum weight edge with exactly one point in T? Well, one thing that we could do is just try all the edges, and maybe some early implementations would do that. But what we're going to do is use a modern data structure, a priority queue. So we're going to keep the edges on a priority queue that have exactly one endpoint in T, and then we can just pick out the minimum weight one. That's the so-called lazy implementation of Prim's algorithm. We'll look at another one called the eager implementation afterwards. So what we need to do is find the minimum weight edge with exactly one endpoint in the tree. So the solution is to make a priority queue of the edges that have at least one endpoint in the tree. And then we, using as priority, the key is the edge and the priority is the weight of the edge. And so we're going to use delete min to find the next edge to add to the tree. And then we have to update the priority queue when we consider that edge. Now, there's going to be some edges on the priority queue that are obsolete, and we've already found better ways to connect them. So we'll just disregard an edge that has both endpoints in the tree. We've already found a way to connect them, and we don't need that edge for the minimum spanning tree. That's why it's called a lazy implementation. We allow stuff to be on the priority queue that we know is obsolete, and then when we pull it off the queue, we test whether it belongs in the tree or not. But then the key step in the algorithm is to what do you do when you get a new vertex for the minimum spanning tree and a new edge. So that means that one of the vertices is on the tree, let's say that's V, and the other one is not on the tree, that means W. And so what we want to do is add W to the tree, but then we also want to add to the priority queue any edge that's incident to W. So that's got the possibility, as long as this other endpoint is not in the tree. So those edges have the possibility of being minimum spanning tree edges in the future, unless some better way to connect their incident vertex to the tree is found before they come off the queue. That's the algorithm, the lazy solution of Prim's algorithm. So let's take a demo of that. So what we're going to do is start with a vertex and greedily grow the tree, add to T the min-weight edge with exactly one endpoint in the tree. That's Prim's algorithm. But now we're going to show the data structure, the priority queue that allows us to do this by keeping all the edges that we know about that connect, that possibly could be that edge on a priority queue. So let's look at what happens for our sample graph. So we start at vertex 0, that's fine. Now we're going to add that to the tree, vertex 0 to the tree, and we're going to put on the priority queue all the edges that are incident to 0. And just for the demo, we'll just show the edges sorted by weight with the understanding that we have a heap data structure or something under there to give us the smallest one. But for the demo, it's easiest to see them sorted by weight. Okay, so then to greedily grow the tree, we have to pick 0, 7 off the priority queue. So we'll show that one on the MST. And then the vertex that's not on the tree at that point is 7. So we're going to add 7 to the tree. And so first we add 0, 7 to be an MST edge. And then we add to the priority queue all the edges that are incident to 7, all the edges incident to 7 that point to places, the vertices that are not on the tree, that are connected to vertices that are not on the tree. So we don't put 0, 7 back on because 0 is already on the tree. So we put all those on the priority queue. And again, keep them sorted by weight. So now let's continue. So smallest thing is 1, 7. That's the smallest edge to a from a tree edge to a non-tree edge. And so that's delete 1, 7 from the priority queue and add it to the MST. So we do that. And now that takes us to 1. And so now we have to add to the priority queue all the edges that connect 1 to non-tree edges. So that's what the asterisks are, the new edges on the priority queue. And again, we keep them sorted by weight. So now what we want on the priority queue is a subset of the, we want to be sure that every edge that connects a tree edge to a non-tree edge is on the priority queue. We might have a few others as well, and we'll see that in a second. So now 0, 2 is the smallest, so we take 0, 2 and add it to the MST. So notice now that once we add 2 to the MST, this edge between 1 and 2 becomes obsolete. It's never going to be added to the MST. At the time that we put 1 on, we thought maybe that was a good way to get to 2, but now we know there's a better way to get to 2, so that edge becomes obsolete. And the lazy implementation just leaves that edge on the priority queue. So now let's continue. We added 0, 2 to the MST, and we have to add everybody incident to 2 that is not on the tree to the priority queue. So in this case, it's 2, 3, and 6, 2. We don't have to add 1, 2, and 2, 7 because they go to tree edges. We don't add them back on. Okay, so now the smallest is 2, 3. So take that, add it to the MST, and add all the edges incident to 3 to non-tree vertices. In this case, it's just 3, 6, and that's a long one. So now the next edge for the MST is 5, 7. Take that off the priority queue, put on the MST, and now all edges incident to 5 that go to non-tree vertices. So it's just 5, 4. Add that one. So now the next edge that will come off the priority queue is 1, 3, but that's an obsolete edge. We already have 1, 3 connected in the MST. because we were lazy, we left that one on the priority queue. So now we just pull it off and discard it because it connects 2 tree vertices. And same with 1.5, that connects 2 tree vertices. We already have a better way to connect them. 2.7 connects 2 tree vertices. And finally we get to 4.5. 4.5 now gets deleted from the priority queue and added to the MST. Everybody connected to 4, that's just 6, and that's a long one goes on. Now we have some obsolete edges. We get to that 1.2, and then 4.7 is obsolete, and 0.4 is obsolete. And finally, the last edge to get added to the MST is 6.2. And after deleting 6.2 from the priority queue and adding the MST, we have computed the MST. We have v-1 edges on v vertices, and that's implementation of the lazy version of Prim's algorithm. And it's just a version of Prim's algorithm. What we showed was the underlying data structure, the priority queue, that ensures that we always get the shortest edge connecting a tree vertex to a non-tree vertex. So let's look at the code for Prim's algorithm. Again, the data structures that we build up in part 1 of this course give us a very compact implementation of this MST algorithm. So we're going to need 3 instance variables. One is a existence array, a vertex indexed array of Booleans that for each vertex will tell us whether or not it's on the MST. Then we have the list of edges on the MST that is going to be returned to the client after the MST is computed for iterable. And then we'll have the priority queue of edges that connect tree vertices with non-tree vertices. There's a superset of the edges that connect tree vertices and non-tree vertices. Given a graph, we'll build the priority queue, we'll initialize all the data structures, and then we'll visit, and we'll show what the visit routine does. That's the one that processes each vertex when it gets added to the tree. We'll look at that in the next slide. So the main loop is, while the priority queue is not empty, we pull off the minimum edge from the priority queue. We get its constituent vertices. If they're both marked, then we just ignore it. They're already on the MST. Otherwise, we put the edge on the MST, and whichever vertex was not on the tree, we visit and put on the tree. And the visit routine is the one that puts the vertex on the tree and puts all its incident edges onto the priority queue. So to visit a vertex, we set its corresponding entry in the marked array to be true, so it's added to the tree. And then for every edge that's adjacent to that, we're going to, if its other edge is not marked, we're going to put it on the priority queue. So if it's an edge that goes from a tree vertex to a non-tree vertex, we put it on the priority queue. And then we have the client query method to get the MST once the MST is built. Again, the data structures that we've used give a very compact and complete implementation of Prim's algorithm. What's the running time of the algorithm? It's correct because it implements Prim's algorithm as we showed. It's an instance of the greedy algorithm. And it's easy to see that the running time is always going to be proportional to E log E in the worst case. And that's because you could put all the edges on the priority queue so every edge would have to come off the priority queue, so that's E times, and then the cost would be proportional to E for inserting and deleting every edge off the priority queue. E log E is a fine running time. The extra space proportional to E might be considered annoying or inelegant or inefficient. So there's a more efficient version of Prim's algorithm where we clear off that dead weight on the priority queue. And that's the eager implementation of Prim's algorithm that we'll look at next. In practice, the lazy implementation works pretty well, but the eager implementation is also a very elegant and efficient algorithm, and it's worth learning both. So for the eager solution, what we're going to do is the priority queue is going to have vertices, and it's going to have at most one entry per vertex. And so those are the vertices that are not on the tree but are connected by an edge to the tree. And the priority of a given vertex is going to be the weight of the shortest edge connecting that vertex to the tree. So if we look at this little example here, where we've built the tree for 0, 7, and 1, then the black entries in this are the edges that are on the MST, so that's 0, 7, and 1, 7. And the red ones are the ones that are on the priority queue because they're connected by an edge to some vertex that's on the tree. And for each one of them, there's a particular edge that that's the shortest, that connects that vertex to the tree. And so that's the key for the priority queue. So that's what we're going to want for at any time during the execution of the algorithm. We're going to want the vertices that are connected to the tree by one vertex, and we're going to know the shortest edge connecting that vertex to the tree. So then the algorithm is, again, delete the minimum vertex, and it's got an associated edge that connects it to the tree, and we put that one on the tree. And then we have to update the priority queue. So what do we have to update the priority queue? So we have this vertex that's not on the tree. We consider all the edges that are incident to that vertex. If they point to a tree vertex, then we're going to ignore it. There's no problem. If it's not already on the priority queue, we're going to put that new vertex on the priority queue. And then the other thing is, if the vertex is on the priority queue and we just found a shorter way to get to it, then we're going to have to decrease the priority of that vertex. So let's look at how that works in a demo. So again, it's just an implementation of Prim's algorithm. It's just how do we get the min weight edge that connects to the tree, and this is a more efficient way to do it. So again, we start out with our graph, start at 0, and let's get going. So now the priority queue has vertices, and so there's 4 vertices that are just one edge away from the tree, and we keep them on the priority queue in order of their distance to the tree. And we also keep the edge, 2 vertex index arrays. One is the edge that takes us to the tree, and the other is the length of that edge. And again, we'll keep them sorted on the priority queue just to make the demo easier to follow. So the next vertex to go to the tree is 7. The next edge to get added to the tree is edge 2 of 7, and then we go from there. So that's the smallest one. We take that for the tree, and now we have to update the priority queue. So how do we update the priority queue? Well, we have to look at everybody incident to 7, and so let's look at, so for example, 7, 2. We don't need to put 7, 2 on the priority queue since we already have a better way to connect 2 to the tree. That's 2, 0, so we don't have to change anything. Same with 7, 4. But 7.5 and 7.1, 1 and 5 are not on the priority queue, so we have to put them on the priority queue and then save the edges and length that get them to 7, which will get them to the tree. So now on our priority queue, we have our current tree, and we have all vertices that were within one edge of the tree and the edge that gets them to the tree and their length. So we're ready for another step of the algorithm. So now 1.7 is the smallest thing in the priority queue. And so we put that on the MST. And now we look at everybody connected to 1. And again, 1.7 we can throw out because it's on the tree. 1.5 we don't need because we have a shorter way to get to the tree. 1.2 we don't need because we have a shorter way to get 2 to the tree. But we haven't seen 3 yet, so we add vertex 3 to the priority queue and say we get to the tree by 1.3, distance 0.29. All the vertices within one edge of the tree and the edge and the length of the shortest edge that gets to the tree from that vertex. That's what we're maintaining at every step. Okay, so next vertex to come to the tree is 2. And so we put that on the tree, and now we look at everybody that connected to 2. So now we have our first example of decreased key, but let's check them all. So 2.0, 2.7, and 2.1 take us to vertices that are already on the tree. So it's 2.3 and 2.6. So what we need to do for 3, we had thought that the best way to get to the tree from 3 was to go to 1. But adding this new edge 2 means we now know a better way to get from 3 to the tree. So we have to update the priority, update the edge 2 and the priority. We have to decrease the key of the priority. So that's an operation that we're going to need from our priority queue, and it's something that has to be factored into our priority queue implementation. And the same thing for 6. We thought we had a good way to get to the tree from 0, but 2 brings 6 closer to the tree, so we have to update that information and say now the best way to get from 6 to the tree is 6.2 and that its length. We have to decrease the key. And this definitely involves some reshuffling in the priority queue, and our implementation is going to take that into account. So with those changes, now we have the following situation. We've got 4 edges on the tree, 3 edges on the tree. Now we're going to add the 4th, which is 2.3. That's the smallest thing on the priority queue. So we add 2.3 to the MST, and now we have to go to the things connected to 3, and well, there's nothing to add since we already have a better way to 6. So next one that gets added is 5.7. And check edges from 5.7. So we from 5 we're going to decrease the key of 4 from 0.38 to 0.5 because the best way to get from 4 to the tree is no longer 4.0, it's 4.5. So again, decrease the key and discard the longer edge to the tree. And in fact, that's the next edge that we pick. And we don't bother putting 4.6 on because we already have a better way to get from 6 to the tree. And then the last edge that we add is 6.2. So again, it's the eager version of Prim's algorithm is an implementation that always connects to the tree, the vertex that's closest to the tree, but we use a more efficient data structure to do it that can only have at most one entry per vertex as opposed to one entry per edge. So that's the eager version of Prim's algorithm. Okay, rather than focus on the code for the eager version, which is quite similar to the code for the lazy version, we're going to talk briefly about the key data structure that we need to implement this. And it's an implementation of the priority queue that allows us to decrease keys. And so this is a advanced version of the priority queue that we talked about in part 1 of the course, but it's necessary for algorithms like this. So what we're going to do is, the problem is that we have keys that the priority queue algorithm doesn't really needs to know when we change values of keys, and so we have to do that through the API. And so what we're going to do is allow the client to change the key by specifying the index and the new key, and then the implementation will take care of changing the value and updating its data structures to reflect the changed values. You can't have the client changing values without informing the implementation, the priority queue implementation. That's the basic challenge for this data structure. So since we are working with vertex indexed arrays and graphs, and the priority queue implementation might do the same, we'll just associate an index, kind of pass that idea on to the priority queue to make it, allow it to implement these operations efficiently. So the constructor gets to know how many indices or how many keys there are going to be at most ever in the priority queue, and so it can make use of that to implement efficient data structures for the operations. And so insert just associates a key with a given index. Decrease key allows to decrease the key associated with a given index. We can check whether that's a bug should be int k is an index on the priority queue. We can remove a minimal key and give its associated index, check whether it's empty and get the size. Now it's pretty much a topic for part 1 of the course, but we'll give just one slide here to show how these indices kind of help things go around. We're basically going to use the same code, the heap-based implementation of min-pq, but we'll keep parallel arrays that allow us to access quickly all the information that we need. So the things on the queue are accessed by index, and so we'll keep the values in keys, so that's where the keys are. So PQ of I will give the index of the key that's in heap position I, and QPI is the heap position of the key with index I. So that is the information that you need when the client changes a value. You need to get to the, you have to actually first of all change the value, but then you may need to adjust the heap to reflect the changed value. So instead of a swim with an index, we get the heap position of the given index and so forth. So if you look in the book, you'll see the code for index priority queue, and it's definitely a confusing topic for a lecture, but it's important to realize that it's possible to implement this decrease key operation in logarithmic time without ever having to search through everything for anything using the idea of indexing. So with that change, we get, for all the operations, we get time proportional to log v. And what do we have to do for the eager version of Prim's algorithm? We might have to insert every vertex once and delete min every vertex one, and we might do as many as e decrease key operations. So that gives us a total running time of e log v. But the main thing is that the amount of space for the priority queue is only v, not e, and that can make a difference for a huge graph. So there are modifications that you can make to this that give a more efficient running time. For example, one easy thing to do is to use, since the operation we're performing most often is the decrease key, If we use a multi-way heap, like say a 4-way heap, or in general a D-way heap, then that reduces the cost of that operation, and it slightly increases the cost for insert and delete min, but there's not many of those. So we can get the running time to log base E over V of V, and that if you do the math for various types of graphs, that's going to be faster. And in fact, a data structure called the Fibonacci heap was invented in the 80s that actually gets the running time down to E plus V log V, although that data structure is too complicated to actually use in practice. If you have a dense graph, then you wouldn't even use a heap, you just use an array and find the minimum by going through everything, since every vertex has lots of connected vertices. So we didn't consider that one because the huge graphs that we find in practice are sparse, and a binary heap is going to be much faster. And if you really have a performance critical situation, it's worthwhile to do a 4-way heap. That's the basic bottom line and the running time of Prim's algorithm. So we're going to complete our study of MST algorithms by considering some context, both as an unsolved problem in theoretical computer science and as a practical problem. So the unsolved problem in theoretical computer science that has defied researchers for many decades is it possible to find a linear time MST algorithm? Is there an algorithm that only examines each edge at most once on the average? Now, this doesn't have that much practical consequence, since the versions of Prim's algorithm that we've talked about can get the running time down quite low for the sparse graphs, the huge sparse graphs that we encounter in practice. But it's like union find, it's a tantalizing problem. Unlike union find, it hasn't been resolved yet. Union find, remember, we couldn't get a linear algorithm, but at least Tarjan proved that no such algorithm exists. For MST, we're not even there yet. And a lot of people have worked on it. Let's just go with this simple model where what you get to do is compare edges, compare weights on edges. In 1975, Yao proved that there exists an algorithm that's worst case running time is E log V. In 1976, Sheraton and Tarjan came up with another such algorithm. And then Fredman and Tarjan found the E plus V log V algorithm, or E log star V for MSTs in '84. Here's another one, E log star V. Now remember, log star V is the number of times you take log to get to 1, so it's less than 6 in the natural universe. So these are very, very close to linear algorithms. The names in orange are people who work at Princeton, so we're trumpeting Princeton a little bit here. In '97, Chazelle showed that it's close to the inverse Ackermann function, that even more slowly growing than log star V. In 2000, got rid of the log factor, so very, very close to linear. Now, in 2002, optimal, well, let's talk about that. They showed an algorithm that it's better not to talk about the theory of that. And then still the open question is there an algorithm whose worst case running time is guaranteed to be proportional to E? Or could someone prove that no such algorithm exists? It's one of the most tantalizing open questions in computer science. As we get into graph algorithms in more detail, we'll see some other examples of problems for which we know pretty good algorithms, but would like to know whether there are better algorithms or not, and MST is a fine example of that. That's the orange means Princeton. There is a randomized linear time algorithm that was discovered in 1995, but that's not the same as solving it worst case in linear time. So that's one context. MST is an important problem that's still being studied by theoretical computer scientists, and we still don't know the best algorithm. Here's another one. So-called Euclidean MST. And this one is what's appropriate in some practical situations. So now you have points in the plane, and the graph is an implicit dense graph. That is, we take as an edge in the graph the distance between each point and every other point. So if there's n points, there's n squared edges because every point's connected to every other point. And what we want is, in that graph, we want to find the subset of edges that connects all the points that's minimal. That's actually, in a lot of practical problems, that's what you want. As it stands, the algorithms that we've talked about are not useful for this because they're going to take quadratic time, because E is quadratic. That's how many edges there are in the graph. You could just go ahead and build the graph with the n squared over 2 distances and run Prim's algorithm, but that's not very satisfying for a huge number of points. It's actually not too difficult to exploit the geometry of the situation and get it done in time proportional to n log n. What is typically done is to build a subgraph where each point is connected to a certain number of points that are close to it. There's a particular graph called the Voronoi diagram, or the Delaunay triangulation, that does that, and it's been proved, number one, that that graph has a linear number of edges, not quadratic, and it's also, the MST is a subgraph of the Delaunay triangulation, so you can get it done in linear rhythmic time for Euclidean MST. Separate problem, related, but still very interesting in many practical applications. Here's another application in many scientific studies. There's the idea of clustering. And so what we want to do is we have a set of objects and they're related by a distance function that specifies how close they are. And what we want to do is divide the objects into a given number k of coherent groups so that objects in different clusters are far apart. So we're going to see how things cluster together. And here's a really old example of a application of this where there was an outbreak of cholera deaths in London in the 1850s. And if you plot where all the deaths happened, the scientific study could find that they were clustered around certain places, and actually they were able to identify well pumps that were leading to the cholera just by doing this clustering study. And that's a very special case. There's many other applications where clustering is an important process, important thing to be able to compute. So like mobile networks, for web search, there's an idea of a distance between documents, and you want to categorize them in clusters. There's all the objects that have been discovered in the sky. You want to cluster them together in a reasonable way, and all kinds of processing having to do with huge databases, trying to get information that seems close together to be close together into a relatively small number of clusters. So there's an approach called single link clustering, where you talk about the single link, the distance between two clusters equaling the distance between the two closest objects, one in each cluster. And so so-called single link clustering is given an integer k, find the k clustering that maximizes the distance between the two closest clusters. So that's a well-defined computational problem. And there's a very well-known algorithm in the science literature for this problem, single link clustering. Form the V clusters, find the closest pair of objects such that each object's in a different cluster, and merge the two clusters and repeat until they're exactly k clusters. And you'll find this algorithm in the scientific literature. What's amazing is that this is Kruskal's algorithm. Just stop when you found the k connected components. So that or another thing you could do is just run Prim's algorithm, and then after you've run Prim's algorithm, get rid of the largest edges until you're left with k clusters. So all the efficient algorithms that we've talked about are going to apply for single link clustering, and actually scientists who also know some computer science now are able to handle huge problems that would not be possible without efficient algorithms. This is just one example where a cancer study where experiments are connecting genes with the way they're expressed in different parts of the body, and trying to cluster together tumors in similar tissues. And again, such experimental results can result in huge amounts of data, and MST algorithms are playing a role in scientific research of this type. That's our context for minimal spanning trees. Today we're going to talk about shortest paths algorithm. This is another problem on graphs that's very easy to state. If we use again a slightly different graph model, last time we had edge-weighted graphs for computing minimum spanning trees. Now we're going to have edge-weighted directed graphs. So now the edges are directed, but they're weighted, and the problem that we're going to be looking at is to find the shortest path from one vertex to another. So in this example, we've got a directed graph with a variety of edges, the directed edges, and our goal is to find, given two vertices, say 0 to 6, what's the shortest path that takes us from 0 to 6, where the length of the path is the sum of its weights. And in this case, the shortest is from 0 to 2, 2 to 7, 7 to 3, and 3 to 6. Now, the algorithms that we're going to look at for this are classic algorithms. And this is an example where years ago we would teach these algorithms and say, well, they will be important someday when people have devices with maps on them and will want to get around. Nowadays, of course, everyone's familiar with these kinds of devices. When you have a map and you want to get from one place to another, or you have a device in your car that gives you directions to get from one place to another, these devices are implementing the classic algorithms that we're going to talk about today. Not only that, and even more important, shortest paths is a really interesting and important problem-solving model. There's all kinds of important practical problems that can be recast as shortest paths problems. And because we have efficient solutions to the shortest path, efficient algorithms for finding shortest paths, we have efficient solutions to all these kinds of problems. All around us, from texture mapping to network routing protocols to pipelining to trucks or to traffic planning, we find shortest paths applications. And we'll look at a couple surprising examples later on today. So one thing to think about is let's specify really what the problem's all about, and there's all different variants similar to many other problems we've studied. So one thing is what vertices are we talking about? So of course the most familiar is so-called source sink. What's the shortest path from one vertex to another? But actually, more useful often is so-called single source shortest paths, which is all the paths from one vertex to every other. And this is the one, for example, that the navigation system in your car might use. The source is where you are, and it'll compute the shortest path to every place else. And then when you ask for someplace, it'll just pick the one that you want, in a manner very similar to the API that we're going to talk about. Another thing that you might do if you didn't have that many vertices is compute all pairs shortest paths. So pre-compute the paths between all pairs of vertices and then immediately be able to answer a client query. This is the type of thing that was used on old maps, for example. Another thing is the edge weights. Usually we think of it in terms of positive edge weights because the maps are geometric and so the length of an edge is proportional to its distance in the plane. But actually for many problems there may be much more arbitrary. And actually one of the big issues that we'll see is whether the edge weights are positive or negative. And those types of restrictions are going to give rise to different types of algorithms. Another issue that arises, and is particularly important in the presence of negative weights, as we'll see at the end, is whether or not the graph has directed cycles, and particularly whether the total length of a cycle is negative or not. And we'll get to that at the end. So, and also just to reduce some clutter in our code in the slides, we'll throughout the lecture make the simplifying assumption that there are paths from the source to every vertex. We won't worry about driving to islands and other such issues. To get started, we have to develop our APIs, and this will be straightforward because this is the fourth variation of a graph API that we've done. We started with regular undirected graphs, then we did digraphs, then we did weighted graphs, and now we're doing weighted digraphs. So to begin, we're going to need a API for processing edges. And this is actually simpler for digraphs than it was for undirected graphs, because we have this concept of one of the vertices is where the edge goes from, and the other vertex is where it goes to. So we have a constructor that builds an edge from the vertex that's given as first argument to the vertex that's given as second argument, and then there's a double that's the weight. And then the client can ask for the from vertex or the to vertex or the weight, or there's a string representation. And always in our code, we'll use the idiom at the bottom of the slide for processing an edge. We'll pick out v, which is e.from, and w, which is e.to, and then our code will process v and w. The implementation of a weighted directed edge is very similar to the one for undirected graphs, but simpler because the constructor simply sets the instance variables from its argument, and from and to are simply getter methods, as is weight. So that's an implementation of directed edge for directed weighted graphs. So now what about the graph itself? So edge weighted digraph. So as usual, we have a constructor that takes the number of vertices in the graph, so it can build data structures that are vertex index arrays. Or we can read from an input stream. And then the key methods are add edge, which takes a directed edge and adds it to the graph. And then the iterable for adjacency lists, which returns an iterable of all the edges that point from a given vertex. So since we're processing edges, we can have self loops and parallel edges, and most of our code will simply use ADJ method to iterate through the edges adjacent to vertices. Representation is very similar to the other representations that we've seen, except simpler because there's only one representation of each edge. So there's the instance variable for the adjacency list is a vertex indexed array. Each entry is a bag of directed edges, actually references to directed edges. So all the code for building and processing this is very straightforward version of code that we've seen before. Here's the implementation for edge-weighted digraphs. It's the same as our edge-weighted graph, except we just replace graph with digraph everywhere. When we add an edge, we only add it to the from vertices adjacency list. So v is e.from, edge v equals add the edge to that. And then to get all the vertices adjacent to a given vertex, we just use the vertex index array to get its adjacency list and return that bag, which is iterable, so that the client can iterate through all those vertices. A very straightforward version of what we did for edge-weighted graphs. Okay, so now our client for that program is our single source shortest paths API. And so it works in a manner very similar to others that we've done. Now we'll call it SP. The constructor takes a graph and a source vertex, and it'll go ahead and build the data structures. It'll find the shortest paths from the S vertex to every other vertex in the graph, and build the data structures so that it can efficiently answer client queries of, first, what's the length of the shortest path from S to a given vertex, and second, what's the path, given an iterable that gives the path from the source vertex to the given vertex. So this test client here will print out all the shortest paths from the given vertex S to every other vertex in the graph. Go through all the vertices. For every vertex, you print S to V and the distance from S to V. And then for every edge in the path, you simply print out the edge. So it'll print for every vertex the distance from S to that vertex followed by the path. So for example, for the sample graph that we gave with vertex 0 as the source, it'll print out the path from 0 to every vertex in the graph. So that's a test client that we'll use to make sure to check and learn the operation of our algorithms. And this API is going to be effective even for huge graphs. So that's an introduction to our shortest paths API. To put all our algorithms into context and better understand them, what we'll do now is go through some basic properties of shortest paths in edge-weighted directed graphs. So what kind of data structures are going to need, first of all? Our goal is to find the shortest path from S to every other vertex. So the first observation is that there's going to be a shortest paths tree solution. Well, if no two paths have the same length, then certainly it's going to be such a solution. And there's a number of ways to convince yourself that there's going to be a tree. If you've got two paths to the same vertex, you can delete the last edge on one of them and keep going until all that's left is a tree, for example. So what we want to do is compute a tree. Now, we've done that in several algorithms before, and a reasonable way to represent the shortest paths tree is to use two vertex indexed arrays. The first one is for every vertex, compute the length of the shortest path from S to that vertex. So in this case, we have this shortest paths tree, and we'll keep the length of the shortest path from the source 0 to each vertex. So 0, 2, the length of that shortest path is 0.26. 0, 2, 7, it's 0.60, and like that. So because you go from 0 to 2, 0.36, and from 2 to 7, 0.34, you get 0.60. And so forth. And then the other thing, as we've done before, is use parent link representation where edge to V is going to be the last edge that takes us to V. And by following back through that array, we can get the path, as we've done several times before. If we want the path from 0 to 6, we go to edge to 6 and says, well, the last thing we do is 3 to 6. Then we go to 3 and say the way we get to 3 is from 7. We go to 7, say the way we get to 7 is from 2. We go to 2 and say that's the way we get to 0. And if we put all those things on a stack, and then we can return them as an iterable to the client, and that gives the edges on the shortest path. So that's the data structures that we're going to use for shortest paths. This is actually the code that does what I just said. The client query, give me the distance. It just returns, uses V to index into the instance array and returns the distance. And if the client asks for the path, then we make a stack. And then we use a variable E, which is a directed edge, and we start at edge 2V, and as long as it's not null, we push it onto the path, and then go to the edge 2 entry for the vertex that we came from, and that gives the vertex that we came from to get to that vertex, and keep going until we run out of vertices, which happens at the source. And then return the path, and that's an iterable that gives the client the path. So that's the implementation of the two query methods. So now what we're going to want to talk about for the rest of the lecture is the algorithms that build these data structures. Now all of the algorithms that we look at are based on a concept called relaxation, or edge relaxation. So now recall that our data structures, so we're going to talk about relaxing an edge from V to W, and we have an example here from V to W. And at the point that we're going to relax this edge, we'll have our data structures in process, and dis2, we haven't seen all edges, we haven't seen all paths in the intermediate part of some algorithm. So, but we'll try to make sure that dis2V for every vertex is the length of the shortest known path to that vertex. And that's going to be the same for W. So these are all the edges that are in edge 2 that we know paths from S to some vertex. So dis2V and dis2W will contain the shortest known paths. Now, if we, also edge 2W and V is the, edge 2W is the last edge and the shortest known path from S to W. The same with edge 2V, of course. Now, so to relax along the edge from V to W, essentially that means let's update the data structures to take that edge into account. And what happens in this case is that the edge gives a better way to get to W. So that's what relaxing is. That edge gives us a new shortest path, so we want to include it in the data structures. So since it has a shorter path, we have to update both dis2W and edge2W. That is, we have a new way to get to W, so we have to throw away that old edge that came to W, and we have a new shorter distance. Instead of 7.2 that came that old way, we have 4.4 that gets us a new way. So edge relaxation is a very natural operation. When we consider a new edge, does it give a new shortest path to that vertex or not? If it doesn't, we ignore it. If it does, we update the data structures to include that edge and forget about the old edge that took us to that vertex. That's edge relaxation. And this is easy implementation of edge relaxation in code. So to relax an edge, we pull out its from and to vertices in V and W according to our standard idiom, and then we just see if the distance to W that's was the shortest path before is bigger than the distance to V plus the weight of the edge that would take us from V to W. If it's bigger, that means we found a new path. If it's less than or equal, we ignore it. And if we found a new path, we have to update the distance to W to be the new distance to V plus follow VW, and then we have to update edge to W and throw away the old version and say that our new edge from V to W is the best path to W as far as we know. So that's easy code for edge relaxation. Now, we're going to use edge relaxation in a really fundamental way to compute shortest paths. But there's one other important idea, which is called optimality conditions. And this is a way to know that we have shortest paths. We have computed all the shortest paths. So the shortest path optimality conditions are embodied in this proposition. So we have an edge-weighted digraph, and we have the dist2 array. Let's just talk about the distances, and the paths go with the distances. But the key point is that the dist2 array represents shortest path distances from the given source S, if and only if these two conditions hold. So the first thing is, if it's the length for every vertex, dist2v is the length of some path from S to the vertex, and our algorithms will always ensure that. And then the second thing is, for every edge VW, we have this condition that the dist2w that we have stored is less than or equal to dist2v plus the weight of the edge from V to W. That's the shortest path optimality conditions. If they're equal, so sometimes they'll be equal, for example, if VW is the last edge on the shortest path, and sometimes they'll be greater, but it'll never be smaller. There'll never be a way to get to W that we haven't found. That's the shortest path optimality conditions. And again, just a quick proof, although the best way to understand proofs is to read them slowly, not listen to them spoken quickly, but I'll quickly outline them. So here's the necessary. Suppose that, so we want to prove that if this is true, then we have shortest path. So to do that, we assume the contrary. Suppose that the distance to W is bigger than the distance to V plus E dot weight for some edge, then that path is going to give a path to W that's shorter than distance W, because V is a path and the weight's shorter, and that is a contradiction to the idea that you have shortest paths, so there can't be any such edge where that condition holds. So that's necessary. And then sufficient, suppose that we have a shortest path from S to W, then we're assuming these conditions all hold, then for every edge on the path, this has to all hold. So it starts at the end. So the distance to the last edge goes from VK minus 1 to VK. So distance to VK is less than or equal to the distance to VK minus 1 plus the weight of the kth edge. And so just continuing down that way, then from the source to the first edge, so source plus the weight of the first edge is greater or equal distance to the first vertex after the source. And all those conditions have to hold. And then what we can do is just add up all those weights and simplify it. And then that shows that the distance to W is equal to the length of the shortest path. And so it's got to be the weight of the shortest path, because it's the weight of some path and it's got that weight. It's got to be the weight of the shortest path. So if those conditions hold, we have shortest paths. So the point of this proof, it's a slightly complicated proof, but it's not too bad. It's quite natural, is that all we have to know to check that we have computed shortest paths is that these optimality conditions hold. To prove that an algorithm computes shortest paths, we just have to prove that it ends up with the optimality conditions in force. and that's what we'll be doing. And the optimality condition really is just saying there's no edge there that we missed. Okay, so with that idea, in fact, there's a very simple, easy to state, generic algorithm that is going to compute shortest paths. And it's very simple. We start with the distance to the source being 0 and the distance to every other vertex infinity. And all we do is repeat until the optimality conditions are satisfied, relax any edge. Just go ahead and relax edges until the optimality conditions are satisfied. So that's a very general algorithm. We don't say how to decide which edge to relax or how to know the optimality conditions are satisfied. But still, it's quite an amazingly simple generic algorithm. So how do we know, how can we show that it computes the SPT? Well, it's pretty simple. Throughout the algorithm, we're making sure that, because of the way that we do relax edges, the distance to V is the length of a simple path from S to V, and the edge to V is the last edge on that path. That's what relaxation does for any vertex that we touch. And not only that, every relaxation that succeeds decreases the distances. And we've assumed that there's a way to get to every vertex, and there's only a finite number of paths, so it can decrease at most a finite number of times. So it's going to the algorithm's going to terminate. It's as simple as that. Again, this is a little bit of a mind-blowing concept, but we'll leave that for more careful study, and just for now realize that all we have to do is relax along edges. And what we're going to do now is look at different ways of figuring out how to choose which edge to relax. The first algorithm that we'll look at is a classic algorithm known as Dijkstra's algorithm, one of the most famous of all algorithms. And that is effective when the weights are non-negative. Then we'll look at an algorithm that works even with negative weights as long as there aren't any directed cycles. And then we'll look at an even older algorithm than Dijkstra's, the Bellman-Ford algorithm, that can solve the shortest path problem in graphs with negative weights as long as there's no negative cycles. Now we'll look at Dijkstra's algorithm for finding shortest paths in graphs with non-negative edge weights. Dijkstra is a famous figure in computer science, and you can amuse yourself by reading some of the things that he wrote. He was a very prolific writer and kept notebooks, and here are really some of his famous quotes. Now you need to maybe know something about old languages to appreciate some of these. For example, COBOL was one of the first business-oriented languages, programming languages, and it tried to make it so that programs kind of read like English language sentences. But purists in computer science, such as Dijkstra, really didn't like that language, as you can tell. The use of COBOL cripples the mind. Its teaching should therefore be regarded as a criminal offense. Actually, when I first came to Princeton, was setting up the department here, there was a big donor who actually wanted to have me fired and the department closed down because we wouldn't teach COBOL. I didn't know about Dijkstra's quote at that time. I wish I had. And there's some other opinions that Dijkstra had. You can amuse yourself on the web reading some of his writings. But he was, here's another one that's actually pretty relevant today. Object-oriented programming is an exceptionally bad idea which only could have originated in California. Dijkstra worked in Texas, University of Texas for a while, and of course came from the Netherlands. Okay, but Dijkstra did invent a very, very important algorithm that's very widely used for solving the shortest paths problem. It's the one that's in your Maps app and in your car and many, many other applications. So let's take a look at how that algorithm works. It's a very simple algorithm. We consider, what we're going to do is consider the vertices in increasing order of their distance from the source. So in the way we're going to do that is take the next vertex, add it to the tree, and relax all the edges that point from that vertex. So let's talk about it in terms of a demo, and then we'll look at the code. So our mandate is to consider vertices in increasing order of distance from the source. Our source is 0 in this case. What vertices are closest to the source? We can look at the edges that point from that vertex. Let's start out with vertex is 0 is at distance 0 from the source, so we pick it. Then we add that vertex to the shortest path tree and relax all its edges. And relaxing all the edges pointing from 0 in this case is just going to update the dist2 and edge2 entries for 5, 8, and 9. So in this case, this says that the shortest path from 0 to 1 is to go along 0, 1, and that's distance 5. And from 0 to 4, it's to go along 0, 4, and that's distance 9, and 0 to 7, let's go take 0, 7, that's distance 8. And the edge weights are positive. We're not going to find a shorter path to any one of the edge weights are positive, and those are the shortest paths that we know so far to those vertices. Now the first key point of the algorithm is take the closest one. If you take the closest one, in this case it's 1, then we know we're not going to find a shorter path to 1. The only other way to go out of 0 is to take one of these other edges, and they're longer. And all the edge weights are positive, so we're not going to find a shorter way from 0 to 1 than to take the edge 0, 1. So that means that edge 0, 1's on the shortest path tree. That's what the algorithm says. Take the next closest vertex to the source. In this case it's 1. And then we're going to add that vertex to the tree and relax all the edges that point from that. So now both 0 and 1 are on the tree, so now let's look at the edges pointing to that. And we have to relax each one of those. So in this case, if you go from 1 to 4, then we look at 4, we know a path of length 9, and 1 to 4 doesn't give us a shorter path. So we leave that edge alone. 1 to 3 gives us a shorter path to 3, which is going to be 20, because you went from 0 to 1, and then 1 to 3 is of length 20. And 1 to 2, also we didn't know a way to 2, but now we know one, or a better one, is 17. That completes the relaxation of all the edges pointing from 1. So now we have 0 and 1 on the tree, and we consider next the next closest vertex to the source. So what we have in dist2 is the shortest path to all the vertices that we've seen so far, and this one says that and we've been to 0 and 1, so the next closest one is 7, which is distance 8. So we're going to choose vertex 7. And again, that's the shortest path we've seen so far. We're not going to find a shorter one, because to get to every other vertex is longer. And so we know it's on the shortest path tree. And now we're going to relax all the edges pointing from 7. In this case, both of them, the one from 7 to 2 gives us a shorter way to 2 than what we knew before. And the one from 7 to 5 gives us a shorter way to 5 than we knew before. Well, we hadn't been to 5 before. So that relaxes 7. So now 7's on the shortest path tree. So now 4 is the next closest path vertex to the source from the edge 0, 4, which is of length 9. So that's the one that we're going to pick next for the tree. We're not going to find a shorter path there. And we relax along all its edges. In this case, we find a shorter path to 5 than we knew before, and a shorter path to 6. Well, we visit 6 for the first time. Okay, so that's 4. So now we just have to worry about 2, 3, 5, and 6, and 5 is the winner there. So we select vertex 5, relax along its edges. In this case, those edges both give us better paths than we knew before. So now we're left with 3 vertices, and 2 is the winner. This is the 2 from the source is 14. To 3 it's 20, and to 6 it's 26. We relax its edges, and it gives us, again, new shorter paths to both 3 and 6. And then the next to last step is to pick 3, and that does not give us a new way to 6. And then finally we pick 6. And then we now know the shortest paths to all the vertices from vertex 0. If we just take the edge 2 edges, that's from to 1 you take 0, to 5 you take 2, and so forth. You get the shortest paths tree, and that gives the shortest way to get from the source to every vertex. That's a simulation of Dijkstra's algorithm. Here's a demo of Dijkstra's algorithm running on a large digraph. So the source is the vertex in the center with the open circle, and you can see it considers the vertices in the graph in order of their distance from the source. Now you can see this is maybe like a lake in the middle of the graph, and so it's not going to move on from those vertices. It's going to take a little while to get around the lake. And again, if this visualization is produced by our code, and it gives a very natural feeling for the way that the algorithm works. This, in principle, and I think in fact, in many cases, is what your car does when you turn the map system on. It computes the shortest path to everywhere, and then it's all ready when you ask for a certain place, how to get there. So here's just starting from another point in the graph. If you happen to live at a corner of the earth, then it's going to be slightly longer to get to the other corner. And a nice feeling for how the algorithm gets its job done. Again, when it gets into those blank areas, it takes a little while to get it over to the other side. And of course, if we had islands, if we had little roads in the middle there that were not connected, there'd be no way to get to them from the source, and we wouldn't see them. And that's fine for the way our algorithm works. We just leave that out of the demo in the proofs to avoid adding an extra comment about that for every algorithm. So that's a visualization of Dijkstra's algorithm on a large graph. So how do we prove it's correct? Well, essentially, we prove that it's an instance of the generic algorithm. So first thing is that every edge is relaxed exactly once. Every time we put a vertex onto the tree, we relax all the edges that come from that vertex, and we never reconsider the vertex. And what does relaxation do? Relaxation ensures that after the relaxation, either way that it was before, afterwards you have the distance to W is less than or equal to the distance to V plus plus the weight of the edge. Either it's equal because we just made it that way, or it's less because it was before and the edge is not relevant. This inequality is going to hold for every entry for every edge corresponding to every edge, for just 2 entries corresponding to every edge, because number 1, the dis2 values are always increasing. We never, I'm sorry, are always decreasing. The only thing we ever only reason we ever change dis2w is to make it smaller. If we found an edge that would make it bigger, we ignore that edge. So it's always decreasing. So when we change dis2w, we're not going to make that inequality false. We're just going to make it better. And dis2v is not going to change at all. Once we relax an edge from a vertex, we're done with that vertex. We're not going to process it at all. So then when we're done, we have the optimality conditions hold. That exactly is the optimality condition. And not only that, we have a path from the source to every vertex. So that's a correctness proof for Dijkstra's algorithm based on the optimality conditions. Here's the code. It's similar to code that we've seen before. We're going to use the indexed priority queue that allows us to implement the decrease key operation. And we have our edge2 and dis2 arrays that are part of the shortest paths computation, and the goal of the shortest paths computation. So we initialize, the constructor initializes those arrays, including the index minimum PQ. And we start out with all the distances infinity, except for the distance to the source is 0. We put the source on the priority queue, and then what we're going to do is take the edge that's closest to the source off the priority, that's on the priority queue, off, and then relax all the edges that are adjacent to that. So I'm using our standard iterator to get all the edges that emanate from that vertex and relax them. And then the relax code is just like the code that we showed when describing relaxation, except that it also updates the priority queue. If the vertex that edge goes to is on the priority queue, it gives a new shorter way to get to that, so we have to decrease the key on the priority queue. If it's not on the priority queue, we insert it. And that's it. That's a complete implementation of Dijkstra's algorithm using modern data structures. Now, this algorithm might seem very familiar if you've been paying attention. It's essentially the same algorithm as Prim's algorithm. The difference is that in both cases, we're building what's called a spanning tree of the graph. But in Prim's algorithm, we take a vertex that's not on the tree using the rule of let's take the vertex that's closest to the tree, anywhere on the tree, closest to some vertex on the tree. For Dijkstra's algorithm, we take next the vertex that's closest to the source through a path that goes through the tree and then into a non-tree vertex. That's the difference. And the differences in the code have to do with the fact that Prim's algorithm is for an undirected graph, Dijkstra's algorithm is for a directed graph, but essentially they're the same algorithm. And actually, several of the algorithms that we've talked about are in this same family. They compute a spanning tree. You have a tree that takes care of that records where you've been in the graph from every vertex back to where you started. And they use different rules for choosing which vertex to add next. For breadth first search, you use a queue. For depth first search, you use something like a stack, and then you have to decide what to do if you encounter a vertex you've been to before. But many graph algorithms use this same basic idea. So in particular, when we're talking about what the running time of Dijkstra's algorithm, it depends on what priority queue implementation we use. And it's the same considerations as for Prim's algorithm. We have v insert operations. Every vertex goes onto the priority queue. V delete min, every vertex comes off the priority queue. And for every edge, in the worst case, we could compute a decrease key operation. So the original implementations of Dijkstra's algorithm used an unordered array which would mean that it would take time proportional to v to find the minimum, to find the vertex closest to the source. So the total running time be proportional to v squared. That's not adequate for the huge sparse graphs that we see in practice today, like the map in your car. So the binary heap data structure makes it feasible to run this algorithm, and that's where all the operations take time proportional to log v. We have to use the indexing trick that we talked about last time to support decreased key, but still we get a total running time of e log v, which makes it feasible. And just as with Prim's algorithm, by using a implementation of the priority queue that can do a faster decreased key, you can get a faster algorithm. And in practice, something like a four-way heap is going to give quite a fast algorithm. That's a little more expensive to insert, but much faster to delete min and decrease key. And again, there's a theoretical data structure that's not useful in practice that gets the running time down to e plus v log v. Of course, if your graph is dense, and again, the examples I use, they're not, the array implementation is optimal. You can't do any better. You have to go through all the edges. You might as well find the minimum at the same time. But in practice, people use binary heaps for sparse graphs, maybe going to four-way if the performance is really critical. The bottom line is we have extremely efficient implementations for the huge graphs that arise in practice nowadays. Now we're going to look at shortest paths in edge-weighted DAGs. This is a very common situation, and we'll see a couple of important applications. Suppose that you've got an edge-weighted digraph. That's our input to shortest paths. But there's no directed cycles. And actually that's true in many applications, and we'll see some. The question is, does the fact that it has no directed cycles make it easier to find shortest paths than in a general digraph? And the answer is yes, it certainly does. So let's take a look at what happens. And the algorithm is very simple. What we're going to do is just consider the vertices in topological order. Since there's no cycles, we know there's a topological ordering where we can lay out the graph and all the edges point to vertices that we haven't seen yet. And so we just relax all edges pointing from each vertex, taking them in topological order. Again, this will be easy to see in an example. All right, so here's a edge-weighted directed acyclic graph. And the first thing that we do is sort the vertices in topological order. And we talked about an algorithm for doing that a couple of lectures ago. Just using depth first search. So we consider vertex 0 and relax all the edges coming from vertex 0. And that gives us shortest paths to 1, 4, and 7. So next we consider vertex 1. We don't do anything except take the next vertex in topological order. We could have also taken 4 in this case. And so we're going to add that and then just relax along all the edges coming from that vertex. In this case, that gives us new shortest paths to 2 and to 3. Next is 4, relax, and that gives us new shortest paths to 5 and 6. Next in topological order is 7, relax, and that gives us the new shortest path to 2, but not to 5. The path that we already had to 5 was better. So next in the order is 5. Relax along its edges, and it gives us better ways to get to both 2 and to 6. Then 2's next. Relax along its edges, and it gives us new, better ways to get to both 3 and 6. Then we do 3 and relax, and that doesn't help, and then we do 6. And when we're done, all we did was consider the edges in topological order and relax. Then we have a shortest paths tree from the source to every vertex in the directed acyclic weighted digraph. So that's a demo of a simple algorithm for that case. All right, why does that algorithm, considering the vertices in topological order, work for edge-weighted DAGs? Now, one thing that's pretty important about this is that the edge weights could even be negative. It doesn't matter to this algorithm. So let's look again. Every edge is relaxed exactly once. When we add a vertex to the tree, we relax each of the edges that go from that vertex. And again, just as with Dijkstra, after we're done with the relaxation, we have this condition holds that distance to W is less than or equal to distance to V plus the edge weight. Either it was beforehand and we ignored the weight, or we made it equal. And so when we relax an edge, we have that condition. And again, the inequality holds until the algorithm terminates. Well, first, again, we only decrease values in the dis-true array. We don't change it to increase. So the only thing that can happen to dis-true W is that it gets smaller, and that's not going to violate the inequality. And then the other thing is, dis2 V is not going to change because of the topological order. When we process V's in topological order, that means we're not going to find an edge that points to V. So dis2 V is not going to change, and the edge weight doesn't change. So the inequality holds. And this is true even if the edge weights are negative. So shortest path optimality conditions hold, and so this simple algorithm finds shortest paths in edge-weighted directed acyclic graphs, whether or not the edge weights are positive or negative. Pretty easy algorithm to implement. So this is acyclic shortest paths. So the goal is to compute edge 2 and dis2, and then we use those to respond to client queries of the length of the shortest path and the path itself. This is the constructor. We build the arrays. We initialize as distances to infinity, distance to source to 0. Then we use our topological sort algorithm on digraphs to compute an iterable that gives us the vertices in topological order, and that's the order method in this topological class. So that's using the API that we set up for topological sorting, which has to be adapted to weighted digraphs, but that's just adding some nomenclature. So we take the vertices in topological order. We take, for every vertex in topological order, taken in topological order, we take every edge that emanates from that vertex and relax it. Couldn't be simpler. And then we're done, we have the shortest paths, and that works even for negative edge weights. Pretty simple. Now, as an example of a familiar application of shortest paths in DAGs and weighted DAGs, we'll look at the idea of seam carving. And this is a relatively recent algorithm that was developed that has important application that you'll see in this YouTube film clip.
Seam carving for content-aware image resizing. Digital media today has the ability to support dynamic page layouts. By changing the window or display size, we can change the layout of a document. However, images embedded in a document typically remain rigid in size and shape. Resizing is also important to fit images into different displays. Current techniques, including cropping or scaling, are limited in their abilities to capture the image content. We present a method for content-aware resizing of images. Our technique enables resizing while adapting the image content and layout. This is sometimes called retargeting. We also define a flexible multi-size representation for images that supports continuous resizing. An image can be shrunk in a non-uniform manner while preserving its features, but it can also be extended beyond its original size. Instead of scrolling through images that do not fit in a given display, we gracefully resize them to fit inside the window. For example, assume that we need to change the width of an image. The simplest way to do this is to remove columns of pixels from the image. The best column to remove would be the least noticeable or least important column. We can search for this column by defining an importance or energy function on the image. In this example, we use the gradient magnitude of the image. Next, we look for the column which contains the least energy and remove it. However, using such an approach quickly leads to serious artifacts. Therefore, instead of using rigid columns, we search for connected paths of pixels, or seams, from one side of the image to the other that contain the least energy. This can be done using a simple dynamic programming algorithm as described in the paper in both vertical and horizontal directions. Here's another example of an image, its energy function, and the least noticeable horizontal and vertical seams. By successively removing horizontal and vertical seams, the image can be resized in a non-uniform manner. The order of seam removal in an image defines an order on the pixels of the image. By storing the simple indexing information, we create content-aware multi-size images.
So that's a amazingly powerful image processing process, and you'll find it all over image processing applications, from Photoshop to GIMP to ImageMagick, and actually nowadays almost any image that you see on your cell phone or your tablet. And what really does that have to do with shortest paths? Well, it's actually a direct application of shortest paths on a directed acyclic graph. So what we do is build a huge directed acyclic graph, and this is a really huge graph because images now at high resolution can have millions or billions of pixels. And so every pixel corresponds to a vertex in this graph, and the edges are going to be just directed edges from every pixel to its 3 downward neighbors. And then there's what weight do we assign to the pixels? Well, there's an energy function that has to do with the image processing that is a function of the 8 neighboring pixels. Every pixel has a relationship with all its neighboring pixels, and the energy function is an image processing concept that is perfect for assigning weights in this instance. And so that gives the weights, and then a seam is just the shortest path that goes from the top to the bottom. So you could imagine an imaginary source that goes all to the top ones, and just run the shortest path algorithm that we just gave, and it'll find a seam. So that's the lowest energy 1 pixel cut through the image. And then the resizing algorithm just deletes one pixel on each row along that seam, and that's the algorithm. So it's a shortest path algorithm that allows and enables the resizing for a really huge graph. And it's really important to realize that you have to have an efficient implementation of the shortest path algorithm because there's so many pixels. And certainly the topological sort algorithm that we gave is extremely efficient linear time algorithm. And you can see the effects of that efficient algorithm all around you. Here's another completely different application of shortest paths in directed acyclic graphs. And the idea is that actually, since negative weights are allowed, we can find longest paths in edge-weighted DAGs just by negating all the weights. So what I want is, I have a again, I have an edge-weighted DAG, and what I want is, this is with, I guess, 5 as the source. I don't want the shortest path from 5 to 2. I want the longest path from 5 to 2. And we'll see an application why that's important in a minute. And in order to get that, all I do is just negate all the weights and then run shortest paths. And if you add up negative weights to get the smallest negative number, then negate the answer, that's the longest path. And it works because the algorithm, topological sort algorithm, doesn't care whether the weights are positive or negative. In general graphs, it does matter, as we'll see in a minute, but for acyclic graphs, it doesn't matter. We can find longest paths in acyclic graphs just by negating all the weights. Therefore, we can solve the longest paths problem. So that's a key point, and now we can look at applications of that problem. And there's a really important application for longest paths in edge-weighted directed acyclic graphs, and that's called the job scheduling problem. And this is just another example to show the importance of the shortest paths problem as a problem-solving model. This particular problem doesn't seem related to shortest paths at all, but we'll show how to formulate it as a shortest paths problem, and that's great because we have an efficient solution to the shortest paths problem. Or actually, it's a longest paths problem in this case. So this is just an example that arises, say, in manufacturing or other applications where you have a complex set of interacting processes. So this is called job scheduling, parallel job scheduling. So I've got a bunch of, this is, say, a factory manager has a bunch of jobs to manage, and they have durations and precedence constraints. So durations just means the job takes a certain amount of time, and precedence constraints means that you can't start job 1 until after job 0 is done, or 7 or 9. 1, 7, and 9 have to start sometime after job 0. And similarly, 3 and 8 have to start after 6, and so forth. So maybe this is manufacturing a car, and you can't paint the car until after you put the doors on, or whatever else you can imagine. Easily setting up precedence constraints that are natural for trying to complete this whole set of jobs. And so what we want to do is find a start time for each job that minimizes the completion time while still respecting all the precedence constraints. So when do we start each job? That's the parallel job scheduling problem. We assume that we got enough workers that we can have a bunch of jobs going on at the same time. So this graph model shows that we can change the job scheduling problem into a graph processing problem. So what we're going to do is create an edge-weighted directed acyclic graph the following way. We're going to have a source and sink vertex that the source is begin everything and the sink is end everything. And then we'll have a zero-weight edge from for every job, we'll have a start and a finish vertex for that job, and then we'll have an edge whose weight is the duration. And from the finish vertex of every job, we'll have edges to the start vertex of the jobs that it has to complete before it. Those are the precedence constraints. We have a zero-weight edge from the overall source to every job start, and a zero-weight edge from the overall, from every job finish to the sink vertex. And so, in summary, there's 3 edges for every job. There's from the begin to the end, the start to the finish, weighted by the duration. From the source to the beginning, 0 weight, and from the end to the sink, 0 weight. And the edges for the precedence constraints also have 0 weight. So that's a graph model. We took our scheduling problem and now we have a graph. And what relates this to what we've been talking about is the longest path from the source to each job turns out to give a schedule. So the job scheduling problem corresponds to a solution to the longest path problem in directed acyclic graphs. By the way, this graph doesn't have any cycles, because that would mean you'd have to do a job before another job, insist that 1 be done after 0 and that 2 be done after 1. You can't also insist that 0 be done after 2, because that would be a precedence cycle that couldn't be satisfied at all. And so now you have to think about this quite a while to understand why the longest path from the source will schedule each job. But that's a fact, in that it means then we have a fast linear time algorithm for solving this problem. Negate all the weights, run shortest paths with topological sort, and negate the answer, and you have the start times for every job. And in fact, in the book, on the book site, you'll find code that solves this parallel job scheduling problem using the critical path method. Again, showing how important it is to have a fast and efficient solution to the shortest paths problem. So finally, we're going to take a look at the implications of having negative weights in directed weighted graphs. So the first thing to notice is that the easy solutions don't work at all. Dijkstra's algorithm just doesn't work in the presence of negative weights. So say this weight from 2 to 3 is -9. What Dijkstra's algorithm will do is just immediately select vertex 3 and never revisit that decision, saying the shortest way to get from 0 to 3 is to take this edge 0, 3, which has weight 2. But the actual shortest path goes over to 4, and then over to 1, and down to 2 for a weight of 10, and then the -9 makes it 1. So there's a way to get from 0 to 3 with path weight just 1 because of the -9, but Dijkstra's algorithm won't find that. So that's not going to work. And you might think, well, why don't we just make all the weights positive by adding 9 to everything? Well, that's not going to work, because a longer path will have 9 added to it a lot of times, so it's just not any relation between shortest paths in this graph and shortest paths in that graph. So those easy attempts just don't work for dealing with negative weights in general graphs. So the conclusion is we need some different algorithm. And the topological sort one isn't going to work because the graph might have a cycle in it. So there's no topological sort. So we need some different algorithm. And the main thing to think about in terms of weighted directed graphs that might have cycles is that you can have this situation called a negative cycle. So this is a graph, it all looks fine, it's just got this one negative edge from 5 to 4 of weight minus 0.66. And these other ones are 0.37 plus 28, so there's plus 0.65. But if you go from 5 to 4 to 7 to 5, then the distance around that is minus 0.01. And if we're trying to find, say, a shortest path from 0 to 6, well, as soon as you hit this cycle, if you really want the shortest path, what you could do is spin around this, well, an infinite number of times. You can make the path as short as you want if you hit a negative cycle. So negative cycles definitely can get in the way of trying to solve the shortest path problem. It makes it somewhat ill-specified. The first thing is, if there's no negative cycles, then there's a shortest path tree. And if there's a shortest path tree, there's no negative cycles, assuming that you can actually get to the vertices. What we'll want is graphs that have no negative cycles, and then we can work with those. And there's an algorithm, an old algorithm known as the Bellman-Ford algorithm that does the job. It's only slightly more specific than the generic algorithm that we gave before. It just says, so if you have V vertices, for just V times, all you do is go through all the edges in the graph and relax each edge. So you make V passes through, relaxing all the edges in the graph. And that's an algorithm that finds shortest paths in graphs that don't have any negative cycles. If there's a negative cycle, we'll talk about what happens in a minute. So let's look at that one in terms of a demo. So we'll just take the list of edges in the graph, and it could be in any order, and just relax them all. To start out, we set the distance to the source 0 and everybody else's distance infinity as usual. And then here's the list of edges, so we'll relax. In this case, we start out with the edges sort of in the order that you'd get them by walking through the whole graph, so you get all the edges associated with each vertex together. So we relax 0, 1, relax 0, 4, relax 0, 7. That's kind of the way Dijkstra would start out. And then we go ahead and relax the edges that come out from 1. So 1, 2 takes us to 2 for the first time. 1, 3 takes us to 3 for the first time. 1, 7 is no help, so we ignore it. Now we relax, oh, sorry, I went too far. 2, 3, and 2, 6, and those that one takes us to 6 for the first time. And now 3, 6, that does not give us a better way to 6, so we ignore it. Now we go to 4, 5, that takes us to 5 for the first time. 4, 6, well, we could get to 4 and 9, and then 20 to 6, so that's no help. 4, 5, that's no help. Now we do the ones from 5, 5, 2. That's going to give a better way to 2, so that we improve that. And 5, 6 is going to give a better way to 6. Now 7, 5, that's no help. And 7, 2 is no help. So we've completed the first pass. And now we're just going to go through and relax all the edges again. Now a lot of them are really just what we did before, so they're not going to improve anything, like the ones at the beginning are not going to improve anything. But before too long, so still no improvement. But here, now the second time we relax 2, 3, it gives us a better way to get to 3. In first pass that didn't help us, but second pass we relaxed 2, 3 to get us to 3 and 17. Now that's going to change things for 3. If we had already been through 3, it wouldn't matter. In this we didn't take another pass to deal with, but in this case we're going to be coming through 3 later. Or there's another 2 to 6 gets better, and then 3 to 6, 2 to 6 beat it, so it doesn't help. And now I think there's nothing else that helps in this example. And in fact, there's no further changes. Once we have the shortest path tree, which we know from this example because it's similar to one that we did before, then there's going to be no changes to it. You're not going to find any edges that successfully relax. And so go through and try them all, and in the end we have a shortest path tree. So that's an example of the Bellman-Ford algorithm on a simple sample graph. Here's the visualization of the Bellman-Ford algorithm running on a bigger graph. And here's what it looks like after 4 passes, 7, 10, 13, And this graph has 100-some vertices, and it finds the tree in a relatively small number of passes. And we'll talk about the performance in a second. One thing is to be sure that the algorithm works. And there's a couple of ways to prove it. And again, the reason the proof has to be done with care is that there could be edges with negative weights, but no negative cycles. And the idea of the proof is that after you've done the ith pass, you've found the shortest paths containing at most I edges. And we'll leave that proof for the book. Now, there's a couple of ways to improve the Bellman-Ford algorithm in practice. And the most important one is that if you didn't change the distance to a vertex during one pass, then you don't have to worry about it in the next path. You don't have to worry about its edges in the next pass. And so what we do in practice is to just maintain a queue of the vertices that we found shorter paths to in each pass. We want to make sure that we keep at most one copy of each vertex on the queue. Otherwise, you could wind up with situations where the size of the queue blows up. But that's easy to do with a vertex indexed array to keep track of that. And so in the worst case, you could have all the vertices on the queue and then therefore all the edges relaxed in every one of the VE passes. But in practice, not too many vertices really get relaxed. So this is a quick summary of the algorithms that we've looked for shortest paths. And we didn't do the code for Bellman-Ford. We've done enough code today. It's quite simple code that you find in the book or on the book site. So probably the simplest algorithm is when there are no directed cycles. And that's when we just topologically sort the vertices and then go through that list and relax every edge. So that's linear time. You relax all the edges in the graph and that's it. And that works even if there are negative weights. If there's no negative weights, but there may be cycles, then Dijkstra's algorithm works. And then we looked at E log V algorithms are slightly faster depending on what kind of heap you use. The Bellman-Ford algorithm, which works with negative weights as long as there's no negative cycles, if you do the queue, you can get in practice, it turns out to be linear time for the kinds of graphs that arise in practice. Although in principle, in the worst case, it could be E times V, which is much too slow. So directed cycles make the problem harder. You need a Dijkstra instead of topological sort. Negative weights definitely make the problem harder because you might need to get the worst case of Bellman-Ford. And negative cycles, in the presence of negative cycles, it actually makes the problem intractable. And we'll talk about that a little bit at the end of the course. One thing that you can do with the Bellman-Ford algorithm is to at least find out if there's a negative cycle. And one practical reason to do that is maybe it has something to do with something ill-specified in the problem. And so if you can detect a negative cycle and deal with it, that would be useful. And we'll look at another important practical reason for finding negative cycles in just a second. So anyway, since it's a useful thing to do, we're going to add two methods to the API, and that is, does the graph have a negative cycle? And then an iterable, if it does have a negative cycle, please give it to me. So for this graph, it would return true, and then it would give an iterable that would have these three edges that give me the negative cycle. So the observation, or the way to find a negative cycle, is to realize that what will happen with Bellman-Ford algorithm, if there's a negative cycle, is that it'll, every pass through, it'll basically go around the cycle. Well, not every pass, and have the length of the cycle. It'll get stuck in a loop going around the cycle, depending on the order of the vertices. And it'll update and just get stuck going around the cycle. So by testing what happens after Bellman-Ford is done, even if there's negative cycles present, we can find the negative cycles. And that, in fact, if some vertex is updated in the last phase of the Bellman-Ford algorithm, then there's a negative cycle. And not only that, edge 2V is the last edge on that cycle. That's the way you got to V, and you can trace back to find the cycle. So just run the Bellman-Ford algorithm, and if some vertex gets updated the last time through, it means that there's a negative cycle. In practice, actually, you don't have to wait till the last phase. You can check the dist2 entries for negative cycles more frequently. But anyway, it's possible to find a negative cycle. And let's look at an application. This is an application that it really motivates some people to understand shortest path algorithms. And the idea is currency exchange. And so these are typical numbers that you might see in a newspaper table, or nowadays in an app on your mobile device that gives the exchange rates for various currencies. So to convert a dollar to euros, use a factor of 0.741 and compute euros to Great Britain pounds 0.888 and so forth. So this table is a table of exchange rates. And the problem is there an arbitrage opportunity? So what is arbitrage? Well, arbitrage is when just by making exchanges according to the legal rates in the table, you can make money. So say we had $1,000, and then these are the going rates. Well, we can convert that $1,000 into 741 euros. So now, if we take those 71 euros and convert them into Canadian dollars, it works out that we get 1,012.206 Canadian dollars. And if we take those Canadian dollars and convert them back to US dollars, it works out that we have $1,007. Well, that's arbitrage, and that's interesting. If we could go ahead and do that for, well, let's say $10,000, then we'd make $70 on the deal, or 100,000 would make 700, or maybe $1 million would make 7,000, or maybe $1 billion would make 7 million. No reason to stop there. With arbitrage opportunity, you're making money off the system. So of course there's intense interest in looking for opportunities like this. Of course, in modern financial markets, there's many more things you can trade than currencies, and these tables are big and complex, and the market is supposed to take care of eliminating these opportunities, but if you're using a computer and you've got a fast algorithm for finding negative cycles in directed graphs, then maybe you can find the opportunity and take advantage of it before the market. So let's look at how it works. What we do is, again, model the situation with a graph. So we're going to have a vertex for every currency, and then an edge corresponding to every transaction or every entry in the table. So this is actually a complete directed graph, and the weight is equal to the exchange rate. And what we're trying to find is a directed cycle whose product of edge weights is greater than 1. So that doesn't look like a shortest paths problem, although it's close, and actually it's very close. To convert this to a shortest paths problem, what we want to do is just take logs. if instead of using the exchange rate, we take minus the log of the exchange rate. And then multiplying turns to addition. If we're looking for multiplying the exchange rates, that's the same as summing the logs. And we took minus log, it means that what we're looking for, and when we're trying to find product bigger than 1, we're looking for a directed cycle whose sum of edge weights is less than 0. Find a directed cycle whose sum of edge weights is less than 0 in a complete digraph. That's the negative cycle detection problem, and we just saw that we can do that with the Bellman-Ford algorithm. And again, in a huge directed graph in a modern trading situation, that's an extraordinarily valuable algorithm, and you can believe that there are people out there running these algorithms in order to detect and take advantage of arbitrage opportunities. And if you don't have a fast algorithm, if you're using a slow one, it'll be gone before you can take advantage of it. That's a fine example of the value of building efficient algorithms for practical problems. So here's our summary of shortest paths today. We've seen some great classic algorithms that are important and extraordinarily useful. First one is Dijkstra's algorithm, which is a fine, efficient workhorse algorithm that you see used every day. And it's a graph search algorithm that is similar to Prim's depth first search and breadth first search that we've seen before and we'll see again. If the graphs have no cycles, which is a situation that arises in several important applications, we can do better than Dijkstra's algorithm. It's easier, and also negative weights are no problem, which enables us to solve scheduling problems and other examples. If there's negative weights and negative cycles, we can detect negative cycles, and if there aren't any negative cycles, we can find shortest paths. The general problem is intractable, and we'll come back to that. But the key point that I want people to remember from today's lecture is that shortest paths is our first real example of a general problem-solving model where there's a lot of important practical problems that we can cast as shortest paths problems, number one, and number two, we have fast solutions to those problems with these classic algorithms that we've talked about today. Today we're going to finish off our discussion of graph processing by looking at Maxflow algorithms. This is another general problem-solving model for which we have efficient algorithms. So where the difference between having a good algorithm and not having one makes the difference between being able to solve all kinds of practical problems and not being able to address them at all. As an introduction, we'll take a look at what the problem is and some of its implications. So first we'll start with what's called the Mincut problem. So this is a takes as input a edge-weighted digraph, and now we're going to assume that the edge weights are positive, and we refer to the weight as a capacity, and you'll see why in just a minute. And also we specify a source and a target vertex. This is not an absolute requirement, but it'll simplify our discussion for the lecture. So we have an edge-weighted digraph with a source and target vertex, and every edge has a positive capacity. Now a cut, an ST cut, S and T are specified, remember, is a partition of the vertices into two disjoint sets, where S is in one set and T is in the other. And we'll indicate a cut, as we've done before, by coloring the vertices in one set. So in this case, the cut consists of S in one set and all the other vertices in the other. So S is in one set and T is in the other. That's an ST cut. Now, given a cut, we talk about the capacity of the cut. And that's going to be the sum of the capacity of the edges that go from the set containing S to the set containing B. If you have edge going the other way, we don't count it. So in this case, this cut with the vertex containing just S in one set has capacity 30, 10 plus 5 plus 15. Here's another cut. This one contains 3 vertices, S and 2 at the bottom there. Again, it's an ST cut because S is colored and T is not. And then we can look at the capacity of that cut. Again, we count the edges that go from the cut containing S to the cut containing B. In this case, is 10 plus 8 plus 16. That's the edges going out, is 34. That's the capacity. We don't count the edges that go in from the set containing T to the set containing S. Capacity of the cut is the sum of the capacities of the edges going out. Here's a third example. And this one's got capacity 28. Now the 3 cuts that we've seen, you notice, have different capacities, 30, 34, 28. So the min-cut problem, clearly, is to find the minimum capacity cut. Find a way to divide the vertices into 2 sets, one containing S and the other containing T, with the property that the capacity of the cut is minimized. That's the min-cut problem. And this is an important practical problem with all kinds of applications. Just for fun, we take an application from the 1950s. This is around the time these sorts of problems were first articulated. So this has to do with the Cold War, and these are rail networks that connects the Soviet Union with the countries in Eastern Europe. This map actually wasn't declassified until 1999, but it shows a graph with vertices, a directed graph, with vertices corresponding to cities and edges corresponding to rail lines. And if you look closely, you can see that each of the edges is labeled with a capacity. The goal of the free world, say, if there was going to be a real war, was to find a way to cut the Soviet Union from Eastern Europe. And they want to do that. You can assume maybe the cost of cutting a rail line is proportional to its capacity. So they want to find the cheapest way to cut off supplies from Soviet Union to Eastern Europe. That's an example of a min-cut application. We'll look at some other applications later on. Well, look at a future, maybe this is a cut for today's world. So now you have a huge graph, maybe a social network, and maybe there's a government in power in some area of the world, and the goal of that government would be to cut off the communication to some set of people. And again, they want to do that in the cheapest way possible, find the minimum way to cut off communication. And certainly people are writing programs to process graphs like this with such goals in mind nowadays. These are huge, huge graphs and certainly are going to need efficient algorithms. In the 1950s, the graphs were pretty huge by 1950 standards, and wanted efficient algorithms then too, for sure, because computers were slower. All right, that's one problem. So let's talk about a different problem called the Maxflow problem. And it's the same setup. Inputs an edge-weighted digraph, source vertex S and the target vertex T. Every edge has a positive capacity. And now what we're going to talk about is what's called a flow. It's an assignment of values to the edges. So we have the capacities, and we're going to assign another integer to each edge called its flow. And the flow has to satisfy 2 properties. The first one is that the flows have to be positive, and they can't be greater than the capacity. You can think of the edges, again, as a rail line containing some commodity or a pipe containing some fluid. So the flow is how much stuff can you put through that edge. You can put more than 0, but you can't put more than the capacity. The other thing about a flow is that there has to be local equilibrium at the vertices. And again, that's a natural constraint. If you think about stuff flowing in on rail lines to a city, and you want to keep things going, the local equilibrium constraint says that the stuff coming in has to equal the stuff going out at every vertex. Except for the source, everything leaves from the source, and the target, everything goes to the target. And those have, the source has no inflow and the target has no outflow. So what you want is the inflow at a vertex. Say in this example, inflow at V, there's 5 coming in on this edge and 5 coming in on that edge, so that's a total of 10 coming in, and there has to be just 10 going out. So that happens on this one edge. And that has to be satisfied at every vertex. So this flow has got 5 coming in there and 5 going out, 10 going in there and 5 going out each way, and so forth. Every vertex except S and T. And we could even make it true at S and T by drawing an edge from T all the way back to S. So that's the max flow problem. That's the definition of a flow, and of course the max flow problem is to assign a value to the flow. Well, that's how much stuff can you get to the source, to the target, or equivalently, how much stuff can you push out of the source. And so the value is how much can you get into the target. There's lots of different ways to assign flows to the network that satisfy the capacity and local equilibrium constraint. Which one maximizes the flow? That's the maximum ST flow problem, or the max flow problem. So that's 2 different problems. The min-cut problem, how do we cut the graph efficiently with the minimal amount of work? And the max flow problem, what's the maximum amount of stuff that we can get through the graph? And again, if we look at the 1950s graph, what the Soviet Union wanted to do was find a way to maximize the flow of supplies to Eastern Europe. That was their goal in this case. And again, you can see in this old map, this is a assignment of a flow to this network that does maximize the flow for this network. So they figured it out. And nowadays, in the huge graph, maybe the free world wants to do the opposite. They want to maximize the flow of information to some specified set of people. How do we get the most information in there? There's another way to think of it. And again, these are huge graphs, and we want efficient algorithms. So that's 2 problems. They both have an input, a weighted digraph with a specified source and target. Min-cut problem is find the min capacity cut. Max flow problem is find the maximum value flow. There's a lot of computation to do. For example, in the max flow problem, we have to assign a value to each edge. So that's more work than just finding a path, as we've done in other graph processing problems. So it's more complicated. And the amazing thing about these 2 problems is that actually they're pretty much the same problem. They're what we call dual. If you solve one, you're able to solve the other. So that's an introduction to max flow min-cut. To get started, we're going to look at a general scheme for solving max flow min-cut problems known as the Ford-Fulkerson algorithm. Dates back to the 1950s. The idea is to start with no flow anywhere. So we initialize all edges to have capacity 0. And then find any path from S to T so that you can increase the flow along that path. Now the simplest case is when the edges all go in the same direction from source to target. We'll look at the other case in a minute. In that case, so there's a path, and this is a general algorithm. It works for any path. If there's a path from S to T, go ahead and find it. And if there's capacity left in each one of the edges, if none of them are full, then what we want to do is augment the flow along that path. So we put as much flow as we can through that path. In this case, we can put 10 units of flow through each path, through each edge. There's room to put 10, and 2 of the edges fill up in that case. but we've increased the flow in the network by 10 in that case. And the algorithm is just continue in that way, finding a path. So here's another path. And this one also, the edges all flow from source to target. And in this case, again, we can add 10 more units of flow because the last edge only has capacity 10. So load up those edges with that flow, and now we've got 20 units of flow in the network. Notice when we augment along an edge, we're preserving the vertex equilibrium, local equilibrium at a vertex property. We're putting some flow in and taking the same amount of flow out. So here's another augmenting path. Now this one has what's called a backward edge. So notice that the path going from S to T goes backwards along that edge. And the idea is that you can augment flow through the whole network by removing flow in that path. That is, if we add 5 units of flow from S to this vertex and 5 units of flow from S to this vertex, then what we can do is remove 5 units of flow along this edge. That's to preserve the local equilibrium. Essentially, that 5 units of flow gets transferred right through. So after we remove 5 units, we add 5 here, that's 5 coming in. We remove 5 here, that's 5 coming in. There's still 10 going out. And then for the forward edges, we add the flow. That is, we can augment the flow along an augmenting path by adding flow to forward edges and subtracting flow from backward edges. The maximum amount of flow that we can push through is the remaining capacity in forward edges and the amount of flow in backward edges. You can't remove more flow than is there. In this case, we can augment the flow in the network by 5. That fills up the first edge. And so now we've got 25 units of flow in the network. And again, the idea of removing flow from a backward edge is very simple. It's just a way to ensure that the local equilibrium condition always remains satisfied as we move along the path. So in this case, there's one more augmenting path. Okay, and that's forward, 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 backwards along that one again, and then forward, forward. So, and then what's the maximum amount we can push through? In this case, this one's got 5 in it, and it's got a capacity of 8, so we can put 3 more units of flow through this network. And we get now we have 28 units of flow going through the network. And the algorithm terminates when there's no way to find an augmenting path from S to T. And what's that mean? That means that every augmenting path, every path from S to T contains either a full forward edge or an empty backwards edge. We can't put more flow through a forward edge, and we can't remove flow from an empty backward edge. So when there's no more augmenting paths, the algorithm terminates. And so that's the algorithm. We start with no flow. As long as there's an augmenting path, we find that path and look through the path to find the amount of capacity left in the most full forward edge and the amount of flow left in the most empty backward edge. And we increase the flow on the path by that amount. And if we can't find an augmenting path, we're done. Now there's a few questions about this. So that solves the maximum flow problem. We have to look at how to compute a min-cut. We have to figure out a way to find an augmenting path. That's not too hard. That's similar to many other graph processing problems that we've already solved. And we have to ensure that, or at least show that it always computes a max flow. And there's even a question of, does it actually terminate? Maybe you could get stuck in some kind of situation where it removes flow on an edge in one path and adds it in another. And so even analyzing how many times it does augmentation is actually not so straightforward. So we'll take a look at these questions. That's the Ford-Fulkerson algorithm, a general scheme for solving Maxflow. Next, we'll look at a proof that the Ford-Fulkerson algorithm is valid, known as the Maxflow Mincut theorem. It also proves that the two problems are equivalent. So we need a couple of more definitions to show. First, we want to show the relationship between a flow and a cut. So in this case, we've got a cut where T is on one side and all the other vertices are on the same side as S. And what we talk about is the flow across the cut. And what that is the sum of the flow on its edges that go from S to T minus the amount that goes the other way. That's the flow across the cut. So there's what's called the flow value lemma, is that if you have a flow, then for any cut, the net flow across the cut is the value of the flow. That's called the flow value lemma. Doesn't matter what the cut is. This is a flow with value 25, and every cut is going to have 25 flowing across it. So this is a more complicated cut where S and these three vertices are colored. So the flow across that cut has to take all the edges that go from a gray vertex to a white one. So there's 10 plus 10 plus from a gray vertex to a white one, 5 plus 10 plus 0, 0. And then we have to subtract off the edges that go from a white one to a gray one. So we add up all the ones that go from gray to white, 10 plus 10 plus 5 plus 10 plus 0 plus 0, and subtract off the two that go from a white to a gray, and still the net value across the flow is the same, the value of the flow. That's the flow value lemma that gives a particular relationship between flows and cuts. And that's not too difficult to prove by induction on the size of one of the sets. For example, if we do an induction on the size of the set containing T, it's certainly true when that set consists of just T, because the value of the flow is exactly equal to the edges coming into T. And then to prove by induction, you can move any vertex from A to B, and local equilibrium is going to make sure that the flow value lemma is true, and so that's how it's proved. And a corollary of that is that the outflow from S is equal to the inflow to T, which is equal to all equal to the value of the flow, and that's also easy to see in all our examples. To get started, let's look at what's called weak duality. If F is any flow at all in a network, and AB is any cut, the value of the flow has got to be less than or equal to the capacity of the cut. So in this case, value of flow is 27, and the capacity of the cut is 30. Value of the flow is always less than or equal to the capacity of the cut. The net flow across a cut has got to be less than or equal to its capacity, because it's at least that, and then if there's any edges going the other way, they get subtracted to compute the net flow. Weak duality that's an easy thing to prove. What we want to prove are these two theorems. The Maxflow Mincut theorem is really two theorems combined, called the augmenting path theorem, that says the flow's a max flow if and only if there's no augmenting paths, and that the value of the max flow equals the capacity of the mincut in any network. And the way we prove that is to prove that the following three conditions are equivalent. Again, this is a proof that's a little intricate logically. It's worthwhile for me to go through it, but to really understand it, you're going to need to read it carefully and convince yourself that these three conditions work. So here's the three conditions that we're going to prove are equivalent. First one is there is a cut. There's some cut whose capacity equals the value of the flow. Second one is that F is a max flow. So if there's a cut whose capacity equals the flow, then F is a max flow. And if F is a max flow, there's such a cut. And then the third one is there's no augmenting path. So we're going to prove that those three conditions are equivalent. And we'll do it with a little logic trickery. So first we prove that 1 implies 2. If there exists a cut whose capacity equals the value of the flow, then F is a max flow. All right, so suppose that we have such a cut, capacity is equal to the value of the flow, then any other flow by weak duality, flow is going to be less than or equal to the capacity of that cut. The capacity of that cut's equal to the value of the flow, so therefore that's the maximum max flow. Value of any flow is less than or equal to the value of F, so it's the max flow. So that proves that 1 implies 2. Okay, now we're going to prove 2 implies 3. Now 1 implies 2, now we'll prove 2 implies 3. That also means 1 implies 3. So in order to prove that, we're going to prove the contrapositive. So we'll prove that not 3 implies not 2. That is, if there is an augmenting path, then F's not a max flow. Well, that's pretty straightforward because that's what we do in the algorithm. We could improve the flow by sending flow along a path, so it can't be a max flow. So that's pretty easy. If F is a max flow, there's no augmenting path, because if there is an augmenting path, F's not a max flow. So that's the second part of the proof. And now the third part of the proof, we'll prove that 3 implies 1. So that'll give you a circular logic condition that proves that they're all equivalent. So we want to prove that if there's no augmenting path, then there's a cut whose capacity equals the value of the flow. So if there's no augmenting path, then what we're going to have is a cut where A is the set of vertices that are connected to S by an undirected path with no full forward or empty backward edges. And so there has to be such a cut if there's no augmenting path. S has got to be in A, and T has got to be in B. Otherwise, there'd be a path from A to B with no full forward or empty backward edges. And the capacity of that cut equals the net flow across the cut, but all the forward edges are full and all the backward edges are empty, so that's exactly equal to the value of the flow. So if there's no augmenting path, then we can demonstrate a cut whose capacity equals the value of the flow. And that completes the proof of the Maxflow Mincut theorem. Sorry. All right, so the one last step is if we have computed a max flow, then what we can do is compute the min-cut by computing this set of vertices. And we can do that just by a graph search. We start at S, and if there's a path that has a forward edge that's not full, then we follow that path. And if we have a backward edge that's not empty, we follow the path. And we just do a graph search to get to all the vertices that we can reach with forward edges that aren't full and backward edges that aren't empty. We treat the full forward edges and the empty back edges as not being there. Otherwise, we do just a regular graph search. And that's going to give us then the set of edges that defined by that cut are going to be the min cut. So not difficult to compute a min cut from a max flow. So that's a proof of the augmenting path theorem and the Maxflow min cut theorem. So now we've got a general scheme for computing max flows and min cuts and a proof that they're equivalent. And next what we need to do is look at an analysis of the costs of computing things to try to figure out specific efficient ways to compute augmenting paths. So we already saw how to compute a min cut, so we'll just worry about doing the max flow. Find an augmenting path. Well, there's lots of ways to find an augmenting path. Anti-graph search is going to work. So let's just start with BFS, for example. If Fulkerson terminates, that means there's no augmenting path. Does it always compute a max flow? Yes, we showed that. That's if it terminates. Does it always terminate? Does it oscillate back and forth? Well, it's a little more work to show that it does always terminate. If you have to, a few other conditions, for simplicity, we assume that edge capacities are integers, or there's other things that can be done with a choice of augmenting paths, and maybe we'll come back to that. But to figure out how many augmenting paths there are, that's the key that requires some clever analysis. And there's been a lot of different schemes studied to try to understand a way to first find the paths cheaply and then decide to try to see how we can limit the number of augmentations. Let's look at an important special case, and it's true in lots of applications, where the edge capacities are integers between 1 and some big maximum u. A lot of the things that we talk about work when edge capacities are real numbers, but let's just talk about this case. One thing to notice in that case is that our Ford-Fulkerson method always keeps an integer valued flow. We never take half a flow unit and put it through an edge. So it's always integer valued because the flow in each edge is an integer, capacities are integers, and so everything stays to be an integer. Every augmentation either increases or decreases by the bottleneck capacity, which is always an integer. One thing that's definitely true is you only augment if you're going to increase the flow. You have to augment. You wouldn't augment if you couldn't augment by at most 1. It's definitely true that the number of augmentations is less than or equal to the value of the flow. There's what's called the integrality theorem that is important for some applications, and we'll come back to it, that says that there exists an integer valued max flow, and Ford-Fulkerson finds it. It's hand-waving a little bit to talk about that, but we'll work with integers and we'll be confident that we get to the answer. And so the proof of the integrality theorem is that it terminates, and the max flow that it finds is integer valued, and that's enough. But just to get an idea for what goes on, let's look at this bad case. Even when the edge capacities are integers, you could have a lot of augmenting paths, and we want to avoid this case. So look at this network here where we have S and T, and we've got 2 big capacity edges coming out of S and 2 big capacity edges coming into T, and then we just have a little edge of capacity 1 going between those 2 intermediate vertices. Here's what could happen. So in the first iteration, we could decide that we want to push flow along the path that goes across the middle. Now we're going to look at a lot of different schemes for finding augmenting paths. So maybe a scheme says if we have a choice, let's take as long a path as we can find. And so in this case, that's what it would do. There's another augmenting path that just goes from S to the left vertex down to P, but the algorithm, say it chooses this one. So we have an algorithm that chooses this one. So that increases the flow by 1. But then the problem is maybe the next time we make that middle edge a backwards edge, And so now we go through and increase the flow by 1 along that edge, and now we have a total flow of 2. And then maybe we alternate between these two schemes. Increment by 1 on the left, increment by 1 on the right. And it's going to take 200 iterations to finally get to the max flow. Whereas a different algorithm might have gotten it done in 2 iterations. And 100's not so bad, but maybe these weights are 1 billion or something. It would take 1 billion iterations. So that's bad news. That's too slow an algorithm. We want to try to avoid that. Now, there's an easy way to avoid that, and that's use the shortest path, or another way is to use the fattest path, the one that you can push the most flow through. That's just an example of the kind of pitfall that you want to avoid in trying to come up with an algorithm for choosing augmenting paths in Ford-Fulkerson. Now, the performance of the Ford-Fulkerson algorithm is going to depend on the method used to choose the augmenting paths. Here's listed 4 easy ways to pick augmenting paths, and they're pretty easy to implement. They're very similar to Dijkstra's algorithm and Prim's algorithm and others that we've looked at, but they lead to a different number of augmenting paths depending on the network. So for example, you could decide, let's use the shortest path. So that's just the augmenting path with the fewest number of edges. And that's just breadth first search, essentially, in the graph that ignores the full forward and empty backward edges. Now, it's been proven that there's no network for which the algorithm uses more than 1/2 E times V paths. So at least that's an upper bound that shows that it doesn't have this bad performance involving the capacity. I want to emphasize that this is a very conservative upper bound on the number of paths used. In an actual network, might not use anywhere near that number of augmentations. Another example is the fattest path. So that's the augmenting path with maximum bottleneck capacity. And again, that one is pretty easy to implement, very similar to our implementations of Dijkstra and Prim's algorithm, and we'll see in a minute. And again, the conservative upper bound on the number of paths taken by that algorithm is number of edges times the log of product of edges and capacity. But again, that's a very conservative upper bound, and in the real world, might only take a few augmentations to compute a max flow using that method. Or you could use a random path, which again is easy to implement, randomized graph search, or depth first search. Now, these conservative upper bounds are useful, but in real world networks, these algorithms are going to have running times that depend really a lot on properties of the network. So people use different algorithms in different situations. And the fact is that often we can get max flow problems solved even on huge networks with a relatively small number of augmenting paths. Next, we're going to look at Java code for solving the max flow problem. This is the most complex graph processing algorithm we've seen so far, but it's a relatively small amount of code that builds upon the mechanisms that we've been studying for the last couple of lectures. So now the graphs that we're working with are a little more complicated because we have to associate with each edge not just a capacity but also a flow. So we'll build a slightly more complicated data type for edges called a flow edge, where for each edge we can keep track of that information. So we not only have to keep the from vertex V and the to vertex W, the weight or the capacity C associated with the edge, and also the flow. So that's a flow edge. And then the flow network, since we're going to go through edges in the wrong direction, we're going to have to put every flow edge, kind of like an undirected graph, in both adjacency lists, and then we're going to test whether which direction we're going through an edge. It's kind of like using an undirected graph, but the flow network anyway has to have edges in both places so it can do backward edges. A simple way to arrange for this is to compute for the edges what's called the residual capacity. And that's just what we're going to use to compute the bottleneck value, the maximum amount of flow we can pull through. So for a backward edge, we'll assign the residual capacity to be the amount of flow. And for a forward edge, it'll be the capacity minus the flow. So that's the maximum amount of stuff we can get through the edge when we're augmenting. That's residual capacity. And to actually do the augmentation, you'll have a value which is your maximum amount that you're going to augment. And so if you're on a forward edge, you add it, and if you're on a backward edge, you subtract it. So that's the basic idea, and it's just quite natural from the graph representations we've been using and the way that the Fulkerson algorithm works. So one way to think of this is a little bit closer to the representation that we're using, is to consider what's called a residual network that for every edge, every forward edge in the network, it has a forward edge going that has the amount of flow left, and a backward edge with the amount of flow that's there. And if you have a full forward edge or an empty backward edge, then you only have one such. So this is an example of the residual network for this amount of flow. You can't put any more flow through from this vertex to this vertex, so there's no edge going that way, but you can remove 4 units of flow going that way, so that's because of the backward edge. In this case, we have a full forward edge, so there's no edge going this way because we can't put any more flow through, but there's 9 going that way. That's another example of a full forward edge. This empty one, you can put 8 units of flow that way, so we have an edge in the residual network going that way, but no way to go that way because there's no flow, there's no backward edge. And so this network is just a natural way to look at the network while the flow is being computed, because it's a digraph that we're going to search in to find the augmenting path. You have a directed path in this network, that's from S to T, that's an augmenting path. And that's a simple mechanism that helps us write compact and elegant code. So that's an augmenting path in the original network, and that just turns out to be a directed path in the residual network. So then we can just use our algorithms that we've already studied for finding directed paths in the residual network. All right, so here's the API for flow edges, and they just have the few extra methods to allow us to compute and make decisions based on the amount of flow and capacity in the edge. These are the computations that we need to implement the Fulkerson algorithm. So every edge has a from and a to, and if you have one point, it gives you the other one, which we need just as we did in undirected graphs. Every edge has capacity and a flow and a residual capacity, which we compute from the capacity and the flow. And then we want to be able to add residual flow to any edge. And it gets added if it's forward, and it gets subtracted if it's backward. Those are the basic methods in the API for a flow edge, and the implementation of all of them is straightforward. Notice that one thing that's a little different from many other classes is that actually the goal of our computation is to fill in these values flow. So they're not final variables. That's what we're computing. Now we do it through add residual flow, but still it's not a final. So create an edge just with a V to W given capacity, just fill in the instance variables. And then all these other ones are just getters. Other is just like in an undirected graph. And then residual capacity and add residual flow are also easy to implement. So residual capacity, if it's on the from edge, you return the flow. If it's on the to edge, it's a backward edge, you return capacity minus flow, just as we said. And add residual flow makes the same test to decide whether to add or subtract the flow. So very simple implementations of all of those operations for our flow edges in a flow network. So what about the flow network API? It's again going to be our standard API, just that flow networks are built out of flow edges. And they're going to be built for the client, which is going to be the Maxflow algorithm, is going to have a method that gives an iterable for every vertex of all the forward and backward edges instant on that vertex. So that client's going to use these basic things. And given everything we've seen, this implementation is pretty straightforward. It's pretty much just like edge-weighted graph, except we use flow edges now. And then when we add an edge, even though it's kind of a directed network to handle flow and forward and backward edges, we add every edge to both adjacency lists. But simple code, quite similar to what we've seen before. Networks usually huge and sparse, so we use a vertex indexed array, and the entry associated with each vertex will contain references to all the edges that are incident on that vertex, whether they're forward or backwards. So just like an undirected graph, you'll have two references to the same edge, one in its from and the other in its to. And then rather than just a weight, they have a flow and a capacity. So from 0 to 2, it's got capacity 3 and 1 unit of flow in it. So that's an example of how to represent that edge. So flow network has got flows in it, that's the gray, and it's got capacities, that's the white, and otherwise it's kind of similar to our undirected graph representation. But when we're processing the graph, we use residual capacity to make it kind of work in the residual graph in the natural way. So this is the implementation of the Fulkerson algorithm. And again, pretty straightforward to, given the description that we've done and the graph processing code that we've written up to this time. So it's got have an array of vertices that we've been to. It's got an edge to array, which is the how do we get to each vertex so we can provide the client with the flow. So that we can process paths in the graph, and then it's got the value of the flow. So let's look at the code. It's kind of self-documenting. So what we'll do is we set the value of the flow to 0. So we're going to find out if it has an augmenting path, and we'll look at that method in a minute. As long as it has an augmenting path, then when we call has augmenting path, basically what that's going to do is that's going to do a graph search and mark the vertices that it visits, and if it gets to this target, it's going to leave that path in the edge to array in the standard way. The edge to of T contains the edge that contains the vertex that took us to T and so forth. And so we'll use that edge to go back through the path and to figure out the bottleneck capacity. which is the minimum of the bottleneck capacity and the residual capacity in the edge that we're processing. So that's the maximum amount of flow that we can push through the network is go through the path and find the minimum of either the unused capacity in some forward edge or the available flow in some backward edge. So then once we have the bottleneck capacity, then we just go back through the path again and add residual flow to every edge in that path. So that's augment the flow. And then once we've augmented the flow, then we update the value. Notice that when this terminates, it terminated because we couldn't find an augmenting path. And we couldn't find an augmenting path meant that essentially we did a graph search that got stuck with finding all full forward edges or empty backward edges before getting to the target. And that's precisely the computation that we needed to do to compute the cut. So to tell whether vertex is reachable from S, we just check marked V, and so we can tell the client which vertices are in the cut, and then we can find the edges that leave that vertex to get the edges that comprise the cut. So now all we have to do to finish is to look at has augmenting path, which is the graph search in the residual network. And for this example, we'll use breadth first search, although the other search algorithms that we've studied can be adapted in the same way, depth first search, or using a priority queue as in Prim's algorithm or Dijkstra's algorithm. So we have our standard H2 and marked arrays, and so we're going to have a queue which is going to contain the vertices that we've encountered but not yet visited. We'll put the source on there. While the queue's not empty, we'll take a vertex off. And so we'll go through everybody associated that's connected to that vertex. It's a flow edge. And then you check the residual capacity. And if it's bigger than 0, that means you have a way to get to W. And if it's not marked, you haven't been there yet, then you go ahead and go there and mark it. It's essentially breadth first search. So that's the code for has augmenting path, and that essentially completes the implementation of breadth first search. And mark T tells returns true or false. If you can get from T to S after that search is gone, then T will be marked and you can return true. This method can return true. That's a Java implementation of the Maxflow. Let's finish up by looking at some applications of Maxflow. Like shortest paths, Maxflow is a very widely applicable problem-solving model. And this is really important to recognize at this stage. We've looked at a lot of algorithms for solving specific problems, and they're important problems, and it's important to have efficient algorithms for solving them. But when you have something like Maxflow or shortest paths, the importance that we attach to them is really magnified by the idea that they have this property that they're a very general way to state a problem, and we have many, many practical situations that we can cast in terms of these problems. We looked at arbitrage reducing down to a shortest paths problem, and we'll look at a bunch of problems that don't seem to be related at all that can be modeled as Maxflow problems. So they're extremely important because they're problem-solving models that work for a broad variety of important applications. Number one, That wouldn't be any good if we didn't have efficient algorithms for solving them, but we do have efficient algorithms for solving them, and so that magnifies their importance. And that's why people work so hard on finding efficient algorithms for solving these problems, and we'll talk about that as well in a minute. So these are, again, just a few of the many algorithms, applications of Maxflow. We saw a image processing algorithm called seam carving for shortest path. There's another one called segmentation for Maxflow that, again, if you have an image and you have one vertex per pixel, you have a huge graph. And you have many explicit huge graphs, and we talked about those types of things. But there are other things where the graph is an abstraction that it gets involved in the model of the abstract graph in the Maxflow problem is maybe a bit surprising at first. And we'll look at a couple examples of that to illustrate the point. Over here is a medical example having to do with that's the image processing one on a medical example, help identify some important part of a medical image. So we'll look at a couple of examples to emphasize the idea of a general problem-solving model that once we have an efficient algorithm, then we can think about using the problem-solving model. And later on, we'll see that this concept of a general problem-solving model has really profound implications, and we'll be looking at that later on. So let's just look at a couple of examples. Here's one called the bipartite matching problem. You have, this is a bit of an idealized situation, but it works in more messy real-life situations too. So there's N jobs out there, and N students apply for them. And we'll use a small example where there's 5 students and 5 jobs, but of course in the real world this can be huge. Now during hiring season, the students go out and apply for the jobs, and they each get a bunch of offers. So looking at it from the student's point of view, Alice gets offers from Adobe, Amazon, and Google. Adobe makes offers to Alice, Bob, and Carol, and like that. So this is association between students and jobs. Everybody gets several offers. And the question is, well, it would be good if everybody got a job, right? And the question is there some way for everybody to get a job? That's called the bipartite matching problem, and it comes up in lots of forms directly related to graph processing. Now, we could study, and people do study, algorithms for explicitly solving this particular problem. But what I want to emphasize is that actually Maxflow is a reasonable model for it. So we can use our efficient Maxflow implementation to get it solved. We don't have to come up with a specialized algorithm for this problem. So in terms of graphs, it's called the bipartite matching problem. Given a bipartite graph, find a perfect matching. And a bipartite graph is one where you have 2 sets of vertices, in this case one corresponding to students and another corresponding to companies. And you have every edge in the graph goes from one type of vertex to the other type of vertex. And a matching in the graph is a set of edges that are disjoint, that just connect 2 vertices, but that's it. And so in this case, there's a perfect matching. Works out that if Alice takes the Google job and Bob takes the Adobe job and Carol takes the Facebook job and like that, then everybody gets a job. So that's a perfect matching. But you can also have a situation where that's not possible. So let's look at how to formulate, well, the one thing is how do we find the matching? And then the other thing is there one? So this is easy to formulate as a network flow problem. That's what this diagram shows. So what we'll do is we'll create our source and target vertices. We'll have one vertex for each student, one vertex for each company in the flow network. And we'll add a capacity 1 edge from S to each student and a capacity 1 edge from T to from each company to T. And then it doesn't matter what the capacity, we'll add an infinite capacity edge from each student to each job offered. And then we'll ask for a maximum flow in this graph. So you can see that the flow, every augmenting path has to go from S to a student to a company to T, and so the flow will give us the matching. Let's see how it works. This is a one-to-one correspondence between perfect matchings of bipartite graphs and integer value max flows. So in this case, there's a flow of value 5, and that flow gives us the matching immediately. So what the Mincut tells us, if there's a no perfect matching, explain why. So here's an example that maybe could have happened with the job offers. And when the algorithm terminates, it terminates with a cut where a cut of the bipartite graph, which separates 2, 4, and 5 from 7 and 10. And essentially the cut tells us that students in 2, 4, 5 can only be matched to companies 7 and 10. You can see all the edges from 2, 4, 5 go to 7 and 10. So you have 2 companies and 3 students, so there's no way that everybody can be matched. Somebody's going to be left out. So that's the students, so there'll be a min cut, and the S will be the students on the S side, and T will be the companies on the S side, and if it's bigger than, S is bigger than T, then you can't have a matching. So in this case, there's only 4 jobs, and somebody's going to be left out. And it's also interesting to trace through what happens with the Maxflow algorithm on bipartite graphs like this. Essentially, augmenting paths or usually forward edges make some matchings. And then if it's possible to find a path that undoes some matching, it zigzags through, undoing matchings and trying other ones to find a way through to the target. But if there's no perfect matching, there'll be a min cut, and that one will explain why. So that's a problem, the bipartite matching problem, that we can model as a Maxflow algorithm and just use our existing code to solve it. Here's another one that's even further away. It doesn't seem to have a graph at all, but it does. It's called the baseball elimination problem. And this is, again, just to show the breadth of applicability of the Maxflow model. And it's interesting at certain times of year, you get near the end of the baseball season, and often you'll hear on the news or see in the paper or see on the web that your team is mathematically eliminated. Actually, most of the time they don't really get that right because they don't do the computation that we're going to talk about next. Sometimes it's easy. This is an example where it's easy. So we've got 4 teams. They already have this win-loss record, and this is the number of games to play. So in this case, Montreal has only 3 games to play. So the best they could do is win 80. But Atlanta's already got 83 wins, so there's no way Montreal is going to win. So that's a mathematical elimination that anyone can figure out. Usually the newspaper will get that one right. But sometimes it's more complicated. Let's say this case. So Philly has 80 wins, 3 games to play. So the best they can do is 83 wins. So that's interesting. But the thing is that Atlanta has a bunch of games against, it's got 6 games against the Mets. And either Atlanta wins one of them, which would give Atlanta 84 wins, or the Mets win all of them, in which case they get 84 wins. Either way, Philadelphia is mathematically eliminated. That's a bit more complicated decision about which team wins. The thing is, and there's many more complicated situations that show up, and the observation just from these two easy examples is that you can't figure out who's mathematically eliminated without knowing the full schedule of games. It depends not only on how many games have already won, how many are left to play, but it depends on the schedule and who's playing who. And usually your average sports writer is not going to do that computation without a computer. I hope that one of you becomes a sports writer and puts this in for the future for us. So let's look at a more complicated situation. So this is the American League East a while ago, near the end of the season. And the question is, which teams are mathematically eliminated and which ones aren't. Now, in this case, it turns out that this is pretty far from the end of the season, actually. There's 27 games to finish. And this is a proof here that Detroit is mathematically eliminated. But it's a pretty complicated argument. Well, you can reason it out with arithmetic. The tough part is to figure out this set of teams here are. So what we're going to see is that you can do a Maxflow computation to figure out this set of teams. And let's just look at it for this example. So at this point, Detroit is mathematically eliminated. And so it's got 27 games to play, so it could, in theory, win 76 of the games. But the logic that will convince you that they are eliminated is that if you take the four teams, the other four teams, and add up all their wins, there's 278 of them, and you look at the remaining games, there's 27, so somebody's got to win every one of those games. The total number of games won for that set of teams is 305, and if you divide by 4, it means the average is 76.25. And right there is a proof that one of them has got to win 77 games. So that takes a little thought, but if you have the four teams, then from the remaining games you can figure out that Detroit is mathematically eliminated. But the key is, how do we find those four teams? And the answer, as I've already said, is it's Maxflow. And so this is a Maxflow network that can be used to solve the baseball elimination problem. So the intuition is that you have a source vertex and you have what happens in the remaining games flowing from the source to the target. So here we're trying to prove that team 4 is, we're trying to decide if team 4 is eliminated or not. That's Detroit in this case. And so what we need is a vertex for each pair of vertices that are not the team we're interested in. And so that's going to relate to all the remaining games between the other pairs of teams. And then you have an edge from the source to each one of those vertices, and the capacity of the edge is the number of games left between those two. So that's on one end. And then you have a vertex for each team. And then what we do for each one of these pair vertices, we put infinite capacity edges to the two teams involved. So the flow is going to be an integer flow, and some of it will go one way and some of it will go the other way. But then for each of the teams, what we're going to do is make sure that they don't win more games than team 4, the team we're interested in. So we'll put this upper bound on the flow here that we won't let the number of wins get better than what our team of interest, team 4, can do. And the fact is that if you compute a max flow of this, you can convince yourself that if you can fill this network up going from S in the max flow, then team 4 is not going to be eliminated. Nobody's going to get more wins than team 4. And so the way to solve the baseball elimination problem is to run max flow on this network. And the Mincut will give the set of teams, Mincut will give the set of teams that you needed in this calculation to figure out, to prove to a friend that, or to a sports writer that the team you're interested in is eliminated. An interesting application of max flow. And again, we just take our problem, use it to build a network, solve the problem on the network using our existing code, and translate that solution to a solution to our original problem. That's called reduction, and it's a very important technique that we're going to use, I'm going to talk about in some detail later on. So now we come to the theory of max flow algorithms. This is an even hotter area than minimum spanning tree and shortest paths that we've looked at before, in that it's a very frustrating situation for theoretical computer scientists, in that we have this relatively straightforward to state algorithm, and we have all this design freedom, the Ford Fulkerson algorithm. There's lots and lots of ways that we could try to find augmenting paths, and there's even other methods that don't use Ford Fulkerson that are almost as simple. And the question is, how difficult is it to solve the max flow problem? And there's literally hundreds of papers in the scientific literature that are oriented at trying to solve this problem. Now again, the theoretical computer scientists are trying to find an algorithm that's guaranteed to work well in the worst case. So they're just counting the number of edges that the algorithms examine in the worst case. But when related to practical graphs, these are very, very conservative upper bounds. And the real performance is going to be totally different. So you can't use these to compare the performance of given algorithms. The performance of given algorithms really depends on the characteristic of networks. But still, there's a huge gap between the best algorithms that we know, and the most recent one was discovered just this year, that can guarantee e squared over log e, number of edges examined to try to find the max flow. So that's fine, but there's a huge gap between, and very small compared to, say, shortest augmenting path, which is e cubed, essentially. And that's fine, but actually in practice, the running time of many of the algorithms seems to be a relatively small factor of E, and no one can prove that there might not exist an algorithm. No one has proved yet that there might not exist an algorithm that gets the job done in linear time. So one of the exciting things about studying the field of algorithms is there's still room to discover interesting and innovative algorithms that could have a huge practical impact. Because we have algorithms that run well on practical networks, lots and lots of important practical applications use them. And if someone were to discover a fast, practical, guaranteed linear time algorithm, it would immediately have huge impact. So that's the first warning. When it's a worst case order of growth, you're not going to compare algorithms in practice. And there's plenty of research papers out there that have done empirical studies on the max flow algorithm for realistic networks in the so-called best so far in practice is known as the push relabel method with gap relabeling, which runs in time e square root of e, where e is the number of edges. And again, even that in practical networks is going to run faster than that. So there's numerous research challenges still to be addressed in studying the Maxflow problem. There's plenty of practitioners that are using codes like the ones that we've shown and variations to try to solve huge real Maxflow Mincut problems and try to get them done in linear time. There's many theoretical computer scientists that are trying to prove that there exists or not exists a Maxflow algorithm that is guaranteed to run in linear time no matter what the input. There's many people doing research, and there's still a great deal to be learned. It's a fine example of why it's exciting to be working in the field of algorithms. There's opportunity for new knowledge still available, and many people still working on them. Today we're going to talk about string processing, and we're going to start by talking about string sorting. We'll take a look at some classic methods, but first we need to talk a little bit about just what strings are. And actually that's really dependent on the programming language that you're using. So different programming languages nowadays really have completely different implementations of strings. So to get started, we need to take a look at efficient implementations of basic operations on strings. We're going to tailor our algorithms to a particular Java implementation, and they can be made to work in other situations, but certainly at starting point you have to be specific. So what is a string? A string is just a sequence of characters. And it's actually a very important fundamental abstraction that's been with us from the beginning of information processing. So pretty much everything we communicate is a string, email or our programs are strings. But even another important area of significance that has arisen recently is in computational biology, where our understanding of the way that life works depends on genomic sequences and is essentially based on string processing. We'll see examples of that later on. This is a quote that talks about that issue. The digital information that underlies biochemistry, cell biology, and development can be represented by a simple string of G's, A's, T's, and C's. This string is the root data structure of an organism's biology. So we're not talking just about data structures for information processing, but for models of life itself. Now, back to computers. The strings are made up of characters. What's a character? Well, the kind of classical representation of what a character is so-called 7-bit ASCII code. Where you have actually the underlying data type is 8-bit, so you could have up to 256 characters. But for many years, programmers used only 128 of those characters. That would include all the uppercase and lowercase letters and numbers and some punctuation. So that's 7-bit ASCII. That's the standard for the C programming language. That's a very widely used language. Nowadays, people use what's called a Unicode, where a character is a 16-bit integer. And that's to allow for many more characters, 2 to the 16th, 65,536, instead of only 256. And that allows for encoding characters from many different of the world's languages and mathematical characters. So it's a much more general and generous representation of what is a character, but it's important to be specific. So in Java, the standard is that a char is a 16-bit unsigned integer. Now, not all programming systems and applications have moved up to the Unicode standard, so sometimes you'll find programs looking for Unicode encoding and not finding it, and this T-shirt is a joke that has something to do with that. It's supposed to be a heart, which is a valid Unicode character in some worlds, but not on that T-shirt. So we'll come back to what is a character. We're going to use a simpler version in between those two, where a character is an 8-bit integer. Now let's talk about what a string is in Java. There's a built-in string data type. It's not quite built in, but many of the features for processing string are built into the Java language, so it's okay to think of it as being built in. So in Java, a string is a sequence of characters, and it's immutable. Once you create a string, you can't change it. And the primary operations that you can perform efficiently with a string are to, number one, find its length. So you can get the length of a string, and that's just the number of characters in it. You can index into a string and get the ith character. That's the char@. method. And you can extract a substring of a string to create a new string that's a continuous subsequence of the characters in the string. And one of the big features of Java's implementation is that you can get that operation done in constant time. And then you can also do what's called concatenation, and that's add a character to the end of another string. That one can't be done in constant time in the standard Java string data type. So this is what the implementation looks like for the string data type in Java. The private instance variables are an array of characters, an offset, that's an index into the first character of the string in the array, the length, and also to make it more efficient to search using string keys. Java keeps a private variable, which is the hash code for that string. So once the string is built and the hash code computed, then when it's time to use the hash code in a hashing algorithm, it's immediately available. So the length method simply returns that length. To get the ith character of the string, we add I to the offset and get that character. And to create a string, given an offset length and a char array, we just reset those values. And then the key thing is the substring method. Since all it involves is a pointer into the immutable string and a length, the index of the first character, we can build a string in constant time just by copying the reference to the character array. So that implementation, we give a good feeling of why substring method is constant in string. So this is the performance. It's a sequence of characters, it's immutable, and the underlying implementation is immutable instance variables that give the array, offset, and length. And so it means that we can get length out in constant time, char@ in constant time just by adding in the offset and indexing, substring in constant time just by essentially copying those instance variables. But to concatenate, to make a new string that results from adding one character to a string, we have to create a whole new string and make a copy of it because the string itself is immutable. So it takes time proportional to the number of characters in the string, and it involves making a new string. You can imagine string implementations, and they exist in various programming languages where these performance guarantees are different. And actually, Java has different implementations for applications where you might want different performance guarantees. And if you work out the memory usage for a string of length n, it's 40 plus 2n bytes. You might consider using a char array, but then you lose a lot of the convenience of being able to produce substring instantly, and also the language features that support strings. So here's a implementation of a different implementation of a sequence of characters in Java that is mutable. So the idea is that you can use this data type when you're building up a string a piece at a time, like maybe reading characters off standard input or something. The underlying implementation in this case is a resizing array of characters. So when it fills up, it doubles, as we've done many times before, and it keeps the length as an instance variable. So with String Builder, you can get the length in constant time, you can get characters in constant time just by doubling, and you can concatenate, add a new character, and amortize constant time. Most of the time it's constant. Every once in a while you might have to double, but you pay for that double by the number of operations that you did. The thing you lose, though, is that it takes linear time to extract a substring, because to extract a substring, you have to make a new char array that can be resizing and so forth and can be amenable to concat. So that's two different implementations of sequence of characters in Java with these two different, importantly different performance characteristics. So we have to be mindful of that in applications. And again, in other programming languages, something like the string builder is more like the standard, and you just have to know what the implementation is. There's another one called string buffer as well in Java that we'll skip for now. So here's a typical example that you might have a simple computation like how do we efficiently reverse a string. So you could use a string, or you could use a string builder. With string, you get to declare it almost like a built-in type and simply initialize with a null string, and then to compute the reverse string, we go backwards through the original string and concatenate the characters starting at the back to create our reverse string. Or with string builder, you use the string builder data type, and so create an object, and that uses the doubling array, and you use the append operation. So what do you think? Which one of these is going to be most efficient for a long string? And the answer is that it's string builder, because using the built-in string, every time you do a concatenation, you have to make a copy of the whole string. So if the string is of length n, that's going to take 1 plus 2 plus 3 all the way up to n, which sums to about n squared over 2. So it takes quadratic time to do for this algorithm to run for a long string. And that's going to preclude using it for huge strings, as we've seen so many times. Can't be using a quadratic time algorithm for a lot of data. On the other hand, with string builder, it's linear time, because the append operations are amortized and linear. So that's a simple example. Here's another example, a computation that we're going to look at later on at the end of the lecture, is how do we form an array of suffixes. So that is, we have an input string, and the suffixes of the string are the strings that you get by starting at each position. So the first suffix is the whole string, the next one starts at position 1, the next one starts at position 2, and so forth, each one less. And so we have algorithms that gain efficiency by forming an array of suffixes of a given string. And so how do we create that thing in the first place? Again, you can do it with string, or you can do it with string builder. So let's look at it with string. We get the length, that's going to be the length of the array. And what we do is for all values of I, we set suffixes of I to the substring of s you get by starting at I and going all the way to n. And that's our suffix array. And this is the corresponding code for string builder. But now in this case, the standard method is going to be linear, whereas the string builder, because there's only one string and the substrings are a few pointers into that string, whereas for string builder, we have to make a new string for each suffix, and there's a quadratic number of characters in all of those strings. So it takes quadratic time. So you can't use string builder to build a suffix array for a huge string. So again, those are typical examples of string processing where it really matters which string implementation that you're using. And if you're using Java, these trade-offs are clear. If you're using some other programming language, you better make sure that you know how strings are implemented before you even get started with string processing. So here's a simple computation that we'll be using. Suppose that we have two strings, and what we're interested in knowing is the length of the longest common prefix. So here's a static method that will implement this function. It takes two strings as argument. We only need to go as far as the length of the shortest of the two strings, so that's n. And then we just go ahead and start at the beginning and compare. As long as the strings are equal, we increment I. And if we get to a point where they're non-equal, that's when we return I, and that's the length of the longest common prefixes. In this case, they're not equal at 4. That means they match for 4 characters. And if we get to the end of one of them, then that's a prefix, so we just return n. So that's just a little bit of warm-up code, and the amount of time that takes is proportional to the length of the longest common prefix. Although if the prefix is short, like if the two strings have a different first character, then it's sublinear. It doesn't have to look at all the data, just has to look at the amount that matches. So the idea of a sublinear time algorithm for string processing is a really important one that we're going to be taking advantage of as we move into more complicated algorithms. So for example, you can compare two strings without looking at them all. It depends. You just have to find the first place that they differ. So you don't look at all the data, that's sublinear time. And we're going to see sorting algorithms that take advantage of that. Now, we're not going to really do it in the code that we show in lecture or even in the book, but it's actually fairly easy to take many of the algorithms that we're going to look at and make them so that they work for general alphabets. And for different applications, it might be entirely appropriate to customize the code to a particular alphabet. So like if the things that are being processed are numbers or positive integers, or things like account numbers, maybe only 10 decimal characters can occur. So we might as well work with strings made from those well-defined 10 characters. In DNA, there's only 4 characters, so we might as well know that we're working with 4 characters. And so we'll often talk of the radix, which is the number of possible different character values in the string. Now, we're always going to use what's called extended ASCII, just to fix ideas, where the radix is 256. And the number of bits, therefore, to represent a character is the log base 2 of that, so 8 bits, 256. And when we talk about performance of algorithms, we'll use R and log R just to make sure that it's clear that if we're working with a smaller alphabet or a larger alphabet, we can still use the algorithms, but the performance is going to depend on the radix. So that's an introduction to string processing. The first string sorting algorithm that we're going to look at is actually the basis for several more complicated algorithms. It's called key index counting, and it's very useful in a particular special situation. But let's take a quick review of where we left off with sorting. We considered a number of sorting algorithms, starting with insertion sort, and then merge sort, quicksort, and heap sort. And we got to the point where we could find an algorithm that's heap sort that guarantees to sort n items in time proportional to n log n without using any extra space. Unfortunately, not stable. And all these algorithms were useful, or are useful, for any type of generic key as long as it implements the compare to operation. And not only that, we prove that any algorithm that just uses compares has to use number compares proportional to n log base 2n. So in a very important sense, merge sort or heap sort, for example, are optimal. You can't use asymptotically fewer compares for either one, and with heap sort you can't use less extra space. So why do we consider other sorting algorithms? There's a lower bound. Why are we thinking about this? The question is, can we do better? And obviously we're here because the answer is that we can do better if we don't depend on compares. The lower bound, the one assumption made by the lower bound is that we use compares, but we don't always need to use compares. And so let's look at an example. Key index counting is a fine example of that, and it's representative of a fairly common situation where in sorting application, where it happens to be that the keys that we're using to sort are small integers. So in this case, this is supposed to mimic an application where there's students and they're assigned to sections. There's not too many sections, and we want to get the thing sorted. So we want to distribute the students by section, and so we want to sort according to the section number, and that's a small integer. And the implication of knowing that the key is a small integer is that we can use the key as an array index then. By knowing that the key is an array index, we can arrange for fast sort. So lots of applications for that. When you maybe have phone numbers, you can sort by area code, or if you have a string you just want to sort by the first letter, you could do it that way. And actually that idea leads to an efficient sorting algorithm, actually two different ways. Now, don't forget that we're sorting according to a sort key, but usually we're sorting bigger generic items that have other information associated with them. If you were just sorting the small integers, you could just count how many ones there are, how many twos there are, and like that, and then in one pass, and then if there's 3 ones, just output 3 ones, and so forth. But the complication is that we have to carry the associated information along, so we have to work a bit harder than that. Here's the code for this method called key index counting, and let's look at a demo. So here's the key index counting demo. Now, to make this a little less confusing and not so many numbers, we're going to use lowercase a for 0, b for 1, c for 2, and like that. So it's the a minus first letter of the alphabet, however you want to think of it. And we're only going to look at 6. So we're supposing that we're sorting this array that has 6 different small integers, and we're using lowercase letters to represent the integers so that we can easily distinguish between the keys and the indices. So now let's look at the processing for this. So the first thing that we do is we go through and we count the frequency of occurrence of each letter. So the way that we do that is we keep an array. Now the array is actually got to be 1 bigger than the number of different keys that we have and the number of different small integers that we have. So in this case, array of size 7. And just to make the code a little cleaner, we keep the number of A's in count of 1, the number of B's in count of 2, and so forth. Once we've set up that's what we want to do, then it's trivial to go ahead and count the frequencies. we simply go through, for I from 0 to n, we go through our input, and when we, A of I, when we access a value in our input, it's a small integer, so it's 0, 1, 2, 3, 4, or 5, and we simply add 1 to that integer and use it to index into the array. So when we see an A that's 0, then we're incrementing count of 1. And we see a B that's 1, we're incrementing count of 2, and so forth. So in this case, we increment count corresponding to D, and then A and C, and like that. So every time we encounter a new key, we simply increment one of these counters. In one pass through, we get an array that gives us the number of A's, B's, C's, D's, E's, and F's. That's the first pass of key index counting. Count the frequencies of each letter using the key as an index. Now the next step is called computing cumulates. And that's a really easy thing as well. All we do is we go through the count array and simply at each step we add the current one to the sum computed so far. So if we look before, we had 2 A's and 3 B's, so that means there's 5 letters less than C. That's the A's and the B's, and there's 6 letters less than D, and 8 letters less than E, and so forth. And that's just obtained by we start with 2, add 3 to it to get 5, add 1 to it to get 6, and with that one pass through the count array, then we can find out, for example, there's 6 keys less than D and 8 keys less than E, and those cumulates tell us where the D's go in the output. There's 6 keys less than D and 8 keys less than E, so the D's have to go in A6 and A7. So this is an array of indices that is going to tell us how to distribute the keys in the output. So that's the next step, is access the cumulates using the key as an index to move items. So let's take a look at, so now remember when we see an A, we're just going to count that as 0, so we're going to go to count 0, and that'll access this entry in the count array. So we go through the whole array to be sorted, and we move each key exactly to where it has to go, and we'll do that one at a time now. So when I is 0, we're looking at the D. The count array corresponding to D has 6, so it says just put D in there and increment that. It means if you get another D, it's going to go into 7. And these things, the way we pre-computed them, are not going to run into one another. So now A, we go, that goes in 0, and we increment the count array corresponding to A. Next thing is C, and so that's going to, it says to put it in 5, and then increment the count array corresponding to C. And F, it says put it in 9. Next is B, we put in 2. Sorry, another F we put in 10. Next is B that we put in 2. So you can see the keys from the input are getting distributed in the output according to the counts and the cumulates that we pre-computed. So now we get the other D, which goes into 7. We get the another B, which goes into 3, and then increment to 4 for where the next one goes. F goes into 11. The last B goes into 4, the E goes into 8, and the second A goes into 1. So that's move the items, again, simply by using the key as index into the count array. And then the last step is to just copy the sorted array back into the original input. That's a demo of key index counting. Quick summary of key index counting. We make one pass through the array to count frequencies of each letter using the key as an index. Then we go through that count array to compute cumulates just by adding each new one into the running sum. Then we use those cumulates and access that using key as index to actually move items over and get them in sorted order and then move back into the original array. What's the running time of this algorithm? Well, the analysis is actually quite simple because it's just a couple of loops through the array to be sorted and through the count array. And the key fact to note that it takes time proportional to n plus r and space proportional to n plus r. Now r, remember, is our radix. That's a number of different character values. So for ASCII, maybe that's 256, and for genomic data, maybe it's 4. And n, we're assuming we're sorting huge files. So really, this is linear time in many practical situations. There's also the question of, is it stable? Yeah, it's actually stable because when we do the move, we move things with equal keys in the order that we see them. We keep them in the order that we see them. That's just the way the method works. So we have for this special situation, we have a linear time stable sorting method which beats the n log n bound and is useful in many practical situations. Key index counting is a great algorithm, but that's not the end of the story. It's also useful for creating a more general purpose algorithm for strings. The first one we'll look at is called LSD Radix Sort, least significant digit first string sorting. And the idea is a very simple one. We have strings, so we're going to consider now a small example where the strings are all of the same length. And again, that's often true in practical applications, account numbers and so forth. Strings that uses sort keys may all be the same length. And what we're going to do is consider the character positions in the strings and move from right to left. The algorithm is to just stably sort using key index counting on the dth character of the key where D goes from the right and it decreases. So this is a stable sort of those 12 keys sorting on the rightmost character. The B's go before the D's go before the E's. It's crucial that the sort be stable in this application, and that's why we checked with key index counting to make sure that it was stable. So it's a stable sort on the rightmost character. And then all we do is move from right to left and do now the second character. And this now is a stable sort of those same keys on the second character. So now the ones with A in the second character come before the one with B and so forth. And not only that, it's stable, so their relative order is maintained, DAB, CAB, FAD, BAD, and so forth. And then to finish this sort, now we do it on the first key. And the magic of LSD radix sorting is that once you do it on the first key, then the strings are all sorted. So that's 3 passes, one for each character in the string, each taking linear time, and we get a string sort. That's LSD sort. Now we need to prove that it works, and so this is a simple proof by induction that it works. After we've done I passes, then we can assume by induction that the strings are sorted on the last I characters. So we're just showing that for after 2 passes, it's sorted on the last 2 characters. That's we're assuming by induction. So now what about the next character that we're sorting? Well, there's 2 things that can happen. If 2 strings are different on the first key, then key index sound is going to do the job. A string that starts with B is going to come before one that starts with a D and so forth. So if they're different on the sort key, the key index sort puts them in order. If they're the same on the sort key, then stability does the job. So all the ones with F stay in order because we insisted on a stable sort. That's a simple proof by induction that LSD string sort sorts fixed length strings in ascending order. And it's really easy to implement. This is a complete Java implementation of LSD string sort. So we're explicitly working with radix R equals 256. And where the radix comes in, the value of the radix comes in, is that's the size of the array that we use for the counts and the cumulates. We need one for each character. For each possible character value, we're going to index into that array. That has to be that big. And all this is the code for key index counting. And then all we do is take a variable t that goes down from, this is strings of fixed width w. We start at the rightmost character and go down to the first character. And instead of dealing with our string a of I, we're just looking at the dth character, which is a character. Otherwise, just with that replacement and that replacement, it's the same code as we looked at for key index counting. So let's do key index counting on the dth character, going down from the width from right to left. That's a remarkably compact code, and that's going to be the method of choice for lots of situations with fixed length keys as the sort key. And it gives us another look at the performance of sorting algorithms. That gives us another line in the table that, well, we're requiring that they be fixed length keys. There's ways to work around that, and we'll consider another algorithm that deals with that in a minute. But again, it's often or typically the case that the width of the keys is not that long. It's a small constant, and therefore we have a linear time algorithm. This even works if the keys are binary numbers represented in a binary word. We can break them up into groups of small number of bits. Say a 64-bit number could be broken up into 8 8-bit characters or 4 16-bit characters. 4 16-bit characters, W would be 4, and you can get a huge array of that kind of number sorted in just 4 passes through the array. If they don't have the same length, we have to do some extra work. It's an interesting problem to think about. We're going to look at a different method in a minute. So here's the type of question that somebody might get asked for a job interview. Actually, a web services company every day might be in the position of needing to sort 1 million or 1 billion 32-bit or 64-bit integers. And an algorithm student interviewing might get asked, what sorting method do you use?
Now, Senator, you're here at Google, and I like to think of the presidency as a job interview. Now, it's hard to get a job as president.
Right.
And I mean, you're going through the rigors now. It's also hard to get a job at Google.
Right.
We have questions, and we ask our candidates questions. And this one is from Larry Schwimmer.
Okay.
What, you guys think I'm kidding? It's right here. What is the most efficient way to sort 1 million 32-bit integers?
Well,
I'm sorry. Maybe
no.
I
I think
that's not a.
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay. I didn't see computer science in your background.
We've got our spies in there.
Well, why not? Let's ask a different interview question.
So the bottom line is, if you want a good job, maybe you ought to know about LSD string sort. Actually, this method has been around for really a long time. So we'll start with a little bit of a story. So what did people do in the 19th century when they wanted to take a census? And actually the story is that for the 1880 census, it was actually obsolete before it was completed. It took 1,500 people 7 years to manually process the data. So during that time, there was room for some invention, and a man named Herman Hollerith developed an automated machine that could help do the census faster. So what his idea was to use punch cards to record data, the kind of data that was taken in the census, and then the machine could tabulate the data by sorting one column at a time. And we'll look a bit at how it does that in just a minute. And the idea was that the result of that was that the next census finished really much earlier and under budget because this machine automated much of the process. And that had really a profound effect on the development of computing because punch cards, it turned out, were useful not just for census but for many other applications. For accounting and for many other business processes. And for many decades, punch cards were the primary medium that was used to store, enter, and process data. And Hollerith's company for building his machine later merged with a bunch of other companies. And in 1924, that company became known as IBM. And actually, punch cards were used up into the 70s and even the 80s in some places. It's important. Let's take a little break and talk about the role of LSD string sort. For a couple of decades, people who wrote programs were working with punch cards. And of courses at universities, if you wanted to write a program, you wrote it by putting one line on each punched card, and your program therefore was a long deck of punched cards. If you had a 1,000-line program, you had 1,000 punched cards. They came in boxes that held 2,000, and people would carry around these boxes of punched cards that were their programs. To enter the program, there was a thing called a card punch, which had a keyboard kind of like a typewriter, but all it did, you could see the cards, it would actually punch holes in the cards with what you typed. Now, there was a huge, so then your program was punched cards, and there was a machine called a card reader, which would take the cards in and convert those punches back into binary and characters that, again, could be processed on the computer. And then you get your results printed out on paper in a line printer. So for many, many years, people programmed by making decks of punched cards, handing them to an operator or put them on a card reader, and then waiting for the printed output to come out. There were other devices, but this was the main thing for a long time. And lots of people learned to program this way. Now, there was a huge flaw in the system, though. The flaw was if you dropped the deck, then your program was completely scrambled and out of order. Finally, we're going to look at suffix arrays and string processing using this data structure that has really played a very important role in string processing applications that would not otherwise be possible. To get a feeling for the idea, we're going to look at a really old idea that you're actually familiar with called keyword and context search. And the idea is that you're given a text, a huge text, and what you want to do is pre-process it to enable fast substring search. That is, you want a client to be able to give a query string, and then you want to give all occurrences of that query string in context. So if you look for the word search, it'll give all the occurrences of where the word search occurs in context, or a better thing is another one. And that's a very common operational one. You're certainly familiar with it from web searching in your browser, and there's many other applications. This is a pretty old idea that dates back to the late 50s, early 60s. People have always wanted to do this. And there's an easy way to look at it called suffix sorting. The idea is you take your input string and then form the suffixes. Remember what I talked about at the beginning with Java's string data type, you can get this done in linear time because each suffix is basically a pointer back into the input string. The suffix, remember, the I suffix is just start at character I and take the rest of the string. So what this does is it gives sort keys that contain kind of the pieces of the string itself in context. And all we do is just run a sort on that suffix. And what that sort does is it brings, if you do a search, it brings the things that you're searching for close together. You can use, once you've done that suffix sort, you can use a binary search to find all occurrences of the string that are there. That's the basic idea of keyword and context searching. You suffix sort the text, then do binary search to find the query that you're looking for, and then you can scan for wherever the binary search ends up. And so this is all the places where the word search occurs in the text of Tale of Two Cities, and then you can use this index to print out the context, whatever's needed. It's a fine and effective way for solving this important practical problem. And that's interesting, but I want to talk about another really important problem that has hugely important applications. And this is the longest repeated substring problem. So you're given a string of characters, find the longest repeated substring. In this case, this is genomic data, and there's the example of the longest repeated substring. Now, in scientific data, the long repeated substring is often something that scientists are looking for. And these strings are huge. It might be billions of these characters. So it's really important not only to know that you can find long substrings efficiently, but also that you can do it for huge, huge strings. Another example is cryptanalysis, where a long repeat in a file that's supposed to be encrypted random file indicates that somebody did something wrong and might be the key to breaking the code. Another example is data compression. When you've got a file that's got a lot of repeated stuff in it, you might want to do this operation to take advantage of these long repeats and not keep multiple copies of them. Here's another example. This is for studying or visualizing repetitions in music. In this example, every time there's a repeat of the notes, then there's an arc drawn to visualize the repeat. And the arc is thick if the number of repeats is long, and it's high if the repeats are far away. and this is an interesting way to analyze repetitions in music. So how are we going to solve this problem? It's a very simple to state problem. Given a sequence of n characters, find the longest repeated substring. As with many problems, there's an easy brute force algorithm that at least gives us an idea of what the computation is like, but it's not going to be useful for huge strings. And that's you try all possibilities, all pairs of indices I and j, and then just compute the longest common prefix for each pair. The problem with that is that if n is the length of the string, you've got n squared over 2 pairs, and for every one of those pairs, you might have to match them up to length d. It's definitely quadratic time, more than quadratic time in the length of the string. And can't be using that for, you're not going to be able to use that for strings that are billions of characters long. Another way to look at, one way to solve the longest repeated substring is to use a suffix sort. In fact, just what we talked about before. So we take our input string, we form the suffixes, and then sort the suffixes, and that brings the long repeated substrings together. So that's a quite elegant and efficient solution to this problem. Just build the suffix array. That's a linear time process. Do the sort. We just saw we can do that with n log n character compares, and then go through and find the repeated substrings. So it's just one pass through to check for JSON substrings to see which one's the longest. And this is very easy to code up. Here's the Java code for computing the longest repeated substring. We get the length of our string out. We build our suffix array. Remember, that's linear time and space because of Java's string implementation allows us to do substring at constant time. Then we go ahead and sort the suffixes, and then find the least common prefix between the adjacent suffixes in sorted order. Just keep track of the max. So that's the longest repeated substring. And if so, for example, this sentence about such a funny, sporty, gamey, justy, jokey, hokey pokey lad is the longest repeated substring in the text of Melville's Moby Dick. And we run that one to prove that we've got a linear arithmetic algorithm because there's a lot of characters in that, and you're not going to find this without a good algorithm. And this is just a humorous approach to what we've talked about today. If you have 5 scientists that are looking for a long substring in a genome, they might encounter this problem with a billion nucleotides. And there are plenty of scientists that are not aware of important algorithms of the ones like the ones that we're talking about. And the one that uses the good algorithm is definitely more likely to find a cure for cancer. But there is a flaw even in this that computer scientists discovered as they got into ever more complex algorithms for problems like this. And that is if the longest repeated substring is long, there's a problem. So this is just some experiments for finding the longest repeated substring in various files from just a program to the text of Moby Dick or a chromosome with 7.1 million characters. And using the brute force method, you get stuck in too slow very soon. But using a suffix sort, you can get these jobs done even for huge files like the first 10 million digits of pi. By the way, if there was a really long repeated substring in the first, in the digits of pi, that would be news. Maybe it would help us understand more about this number. So lots of people write programs of this sort. But the big problem is if you have a really long repeated substring, then suffix sort's not going to work. Our fast algorithm doesn't complete. So what's going on? And the explanation is really simple. If, for example, you have two copies of something, when you form the suffix array, what happens is if you have the longest repeat, but you also have every version of that repeat appears, and you have to look for those when checking for the longest repeated substring. So if D is the length of the longest match, then just to check for the longest common prefix, you got to do at least 1 plus 2 plus 3 plus 4 up to D character compares, which means it's going to be quadratic just for checking for the longest common prefix of adjacent elements in this algorithm. It's also a problem for the sort. So if you have very long repeats, we still don't have an algorithm. So the question is that was confronting computer scientists in the late 80s, early 90s is how can we get this done? What's the best algorithm for this problem? And there was a great algorithm called the Manber-Myers algorithm that I'll talk about in just a minute that got the job done in linear rhythmic time. And actually, there's a clever old algorithm that uses a data structure called suffix trees. But it was really the Manber-Myers algorithm that got people excited about this area. And so I want to describe that briefly. Actually, these two computer scientists, one of them went on to become chief scientist of an internet company, and the other one went on to become chief scientist of a company that won the race in sequencing the genome. In both cases, good algorithms for processing long strings are very important. And this is a great algorithm. Now it's a little too complex to give all the details in a lecture, but I can give a pretty good idea of how it works. So the overview is that it's kind of like an MSD sort, but what it manages to do is double the number of characters that it looks at in each pass through the array. And the idea is that since you're doubling the number of characters that you look at each time, it finishes in log n time. That's the size of the suffix array. If you double until you get to n, it's log n. And it turns out what's really ingenious about the algorithm is that you can do each phase in linear time. This is an example of how it works. So it's going to do a suffix sort, and then I'll talk about the least common prefix as well in a minute. So sort of the first character, well, we just use key index counting or something like that. So we know how to do that in linear time. And then the idea is, given that it's sorted on the first character, we can easily sort on the first two. Well, again, we could use key index counting. But now what we can do is double the number of characters that we involve each time. So the next phase of the Manber-Myers algorithm now gets it sorted on 4 characters. And of course, the more characters we have sorted on at the leading part, the smaller the subfiles in the trailing part. So that's certainly a feature. And then in this case, after we get to 8 characters, then all our subfiles are of size 1, and we're done with the sort. Now, the key to the algorithm is the idea that once it's going, it uses what's called an index sort, which essentially means that it can do compares in constant time in the middle of the algorithm. And let's just take a look at how that works. Let's look at trying to compare string 0 with string 9. And we know that we've already got the thing sorted on 4 characters, and we want to sort it on 8. So 0 and 9 are equal on the first 4 characters. They're in the same subfile, so we got to get it sorted on the others. But the thing is, if we add 4 to our given indices, so we're at 0 and we add 4, that gets us to 4, and we're at 9 and we add 4, that gets us to 13. We already know that the thing is sorted on those characters, and we know that 13 appears before 4 in the sorted list. It's already sorted. And we can keep track of that by using an inverse array, which says for every index where it appears in the sorted order. So this says that 13 appears at position 6 and 4 appears at position 7. That is, 13 appears before 4. So when we're trying to compare this string here, that's the 0th suffix with the 9th suffix, we can go in and again add 4 to get 4, add 4 to get 13, go into the index array and see which one's less, and the one that appears first is going to be less. So that's a constant time comparison. 13 is less than or equal to 4 because the inverse of 13 is less than inverse 4, which means that suffixes of 9, if you take 8 characters out of 9 and 8 characters out of 0, it's less. It's a really simple and, of course, easy to implement operation. So maintaining the inverse, I can get constant time string compare. So what does that imply for the whole suffix sort? With a constant time compare, then I can get, at a minimum, I can get an n-log n sort just by using quicksort or merge sort. And then I get much faster than quadratic performance no matter what the strings are. That's a big key to the success of this algorithm. And actually, if you use version of the 3-way quicksort, it's been proven it even gets down to linear time for the sort, no matter what the input is. That's one thing, and then the other thing is when you need to do the longest common prefix to look for the longest match after the array is sorted, you can also do this constant time string compare and get the job done. So this is really an ingenious algorithm that can get suffix sorting done very fast, even in the presence of a huge repeat. And I think really underscores the importance of careful algorithmic thinking in addressing new computational challenges. So string sorting, just to summarize, is a really interesting area of inquiry. For one thing, we can develop linear time sorts for many, many applications. We thought we were doing well when we had n-log n sorts, but actually we can do much better for many applications. And in fact, we can even get to sublinear where we don't even have to examine all the data. In today's world, when we have huge amounts of data, to be able to get it sorted without even looking at it all is really quite a miracle. 3-way string quicksort, you can't do better than that in terms of the number of characters that you have to examine, and there's a lot of deep mathematical analysis behind that result. But I think the other lesson to learn is that algorithms like 3-way string quicksort and Mamber-Myers show that we really have a lot to learn still in string processing. And they're not really random. In fact, a lot of times we're looking for non-randomness, and we might want to use specialized algorithms. It's string process. This is our introduction to string processing. We're going to look at many other string processing examples in the coming lectures. We can also get strings sorted by moving from left to right. That's called MSD string sort, or most significant digit first string sort. And this is kind of related to what we did with quicksort. It's maybe viewed as a generalization of quicksort. So the idea is that we start with the first character to use key index counting on the first character of the array, and that'll partition it into the strings that start with each character. So if we use the first character, the leftmost character in the string as the first character in this case, then we get all the strings that start with A, followed by all the strings that start with B, and so forth, and then recursively use the same method for each subfile. Essentially, we have a subarray for each of the characters, and that cumulate that we built with key index counting gives us the subarrays. It actually completely delineates the subarrays that we need to sort. Remember, we had built up this array that said that there's 6 keys less than D and 8 keys less than E and so forth. So that tells us exactly precisely the boundaries of the subarray that contain the keys that start with D, and then we can just use the same method recursively to sort each of the subarrays, one for each character. Now this is a little bit complicated trace, but if you look at it more carefully after the lecture, you'll see that it's pretty simple setup for what we need to do. So here's our input, and we sort on the first character. If we sort on the first character, in this example we have lots of S's. So the subfile for the S's, it's already sorted on the first character. This D is the digit that we're currently working on it. So then we sort that on, it's the rest of it on its first character, so it's the second character and all the words that start with S. And then there's a lot of them that start with E, so we move on to the third character for those. And then there's some that start with A and so forth. So recursively, every time that we move on one character, we have to keep going until, well, one thing we have to do is, if there's 2 keys that are equal, we have to examine every character in the keys. We never find out that the 2 keys are equal until the end. And if you reach the end of a string, you can just assume that goes before any character value. And with those 2 things, then you can trace through the recursion to see how MSD string sort works. So again, in this case, it sorts by the first character. A and B have only subfiles of size 1, so you don't have to do anything. So then most of this slide is showing what happens with the keys that start with S. And then at the end, there's the 2 keys that start with T, and they have both H's and both E's. We have to go through the whole thing. So that's an example of MSD string sort. Now, if strings are variable length, like they were in that example, we just treat them as if they had an extra character at the end that's smaller than any character, so they'll appear before, they're supposed to appear alphabetically before strings that have the same starting characters that are longer. And you could do that by overloading, implementing char to just return -1 if we're past the character that we're looking at. So that's an easy part of the implementation. One thing to point out, in the C programming language, the representation of strings puts an extra character that's 0 at the end, and no string has a 0 character. So actually we don't have to do anything at all. But with that change, the code for MSD string sort is also really an extremely simple modification or extension to key index counting. So we've got our sort, and it takes its input array and then the output buffer, and then we have to take the delimiters of the subfile we're going to sort, low and high, just like we've done for other recursive sorts. We go ahead and we do the key index counting again to take care of, we have to take care of the fact that we have an extra character, that kind of the end of string character, and also pull out the def character of our string, just like we did for LSD sort. And we just go through the whole thing and sort according to the given character. And then what we do next is just do a recursive call for every entry in the count array, where we just sort the part of the array from count of r to low plus count of r to low plus count of r plus 1. Really just one line of code for each subarray, and then we move to the right one character. So again, this is very little code to get a very useful and powerful sorting method. That's MSD string sorting. One thing to notice is that with the extra output buffer, we can use that even with the recursive calls, but not the count array. We have to keep the count array around, so it's it's got to be local to the recursive procedure, because when we call for the next character, we're going to need a new count array for that character. We have to say the old one to do the next subarray for the calling method. So that turns out to be important because there's the potential for big problems with MSD sort when we start looking at the analysis. And the thing to notice is that if you have a tiny array, say an array of size 2, doesn't matter how small your array is, you need to have a count array for each potential character in the alphabet. So for ASCII, just to initialize the count array, to set it to 0, just create it, it's going to be 100 times slower than just sorting the thing or just copying it back. And if you're using Unicode, it's 32,000 times slower. And what's worse is it's a recursive program, so there's going to be lots of small subarrays. Sorry, this feature or characteristic of MSD string sort actually reared its ugly head in a lot of applications that were using it when people switched from ASCII to Unicode a while back. All of a sudden, programs that were really efficient sorts all of a sudden became hundreds of times slower with the switch to Unicode because these big arrays in the recursive procedure. It was a serious performance problem, so you definitely have to watch out for that with MSD string sort. Now there is a good solution to avoid this danger, and it's the same solution we've used before. If you've got a small subarray and the sort is going to be slower, just cut off to insertion sort. And the other thing you can do is save some more time, is to just have insertion sort start at the character that we're currently working on, because we know things are equal to the left. We're just looking to the right. And that's easy to implement just by changing the implementation of the compare function to take into account which character we're at. Notice it's quicker, and it happens to be quicker in Java to just pull out the substrings and use compare to than to go in and get the chars. That's just a feature of the implementation. Switching to cutting off to insertion sort for small subarrays is definitely a good idea for MSD string sort. And so what about the performance of this method? The key characteristic of MSD string sort is it examines just the characters that it needs to examine in order to get the keys sorted. So that means that its performance is going to be really dependent on the data. Now, in the worst case for the algorithm, it has to examine all the data. In this case, all the characters in all the strings. And that's, for example, when they're all equal. It's going to look at all the characters. If you have some duplicate keys, it might have to examine all the characters in those duplicate keys, but there's plenty of other strings that it doesn't examine all the characters. So that depending on, and if the keys are random in some way, if they're approximated by random keys, then it's not going to examine very many characters at all. Actually, and this is a typical case, say for account numbers or some situation, library call numbers or some situation like that. In a case like that, MSD string sort will examine only a small fraction of the data, a small constant fraction of the data, and so it's going to be sublinear. Now, it's also possible that sorts that do comparisons can be sublinear, but MSD string sort is good in that it really only examines the characters that need to be examined in order to get the sort done. So this gives us another line on the table. And the key here is that if the data is approximated by random, log base R of n is going to be pretty well approximated by a constant in the real world. So this is going to be a fast method. The one danger is that you have to worry about using too much extra space with those big count arrays. But that's an important and useful practical sorting method. So now let's look at MSD string sort versus quicksort for strings. They are similar in many ways. They're both recursive methods that partition a file up. So one of the problems with MSD string sort is that it tends to, when it's doing the counting, it's kind of making random accesses to memory, and particularly when it's distributing the keys out. So on modern systems that have caches, not everything is in the fastest memory at the same time, and programs that move from one piece of data to another right next are going to be much more efficient. And quicksort's like that, and MSD string sort is not. Another disadvantage of MSD string sort is that there's actually quite a few instructions in the inner loop with the indexing and the counting and the plus and the accumulating and so forth, whereas quicksort, remember, is fast because it has only a few instructions in the inner loop. And MSD string sort uses extra space. Whereas quicksort, there's two things. One is it's not linear in these applications where MSD string sort is. And kind of the reason that it's not linear is that if you've got keys that have a lot of the same characters at the beginning, when it's doing the compares, it has to rescan or recompare lots of those characters. So what we're going to look at next is try to get this, achieve this goal of combining the advantages of these two sorting algorithms. Next, we're going to talk about three-way Radix Quicksort, which is that algorithm that combines the benefits of Quicksort and MSD Radix Sort. This algorithm actually came into development during the development of this course. As it turns out, radix sorting, while it was really well known to everyone in the 60s and 70s, it was kind of lost sight of for a while in the 80s as people moved to higher level programming languages, and it wasn't so easy or efficient to get characters out of keys. You had to either work with numbers, you had to use abstractions like compare to, and radix sort were kind of lost for a while. But then string processing became more and more important as computers became bigger and faster. And so we needed to talk about how to sort strings. This algorithm is a really simple algorithm that comes out when you start to address that problem. So the idea is that what we're going to do is use three-way partitioning for quicksort, but just by character. So since we're going to do one character at a time, there's going to be a lot of equal keys for that character, And the idea is that when you do have equal keys, you'll pull them together with those leading characters, and then you can recursively sort the subarrays, but you can do the normal quicksort thing for those. So for this example, when we partition on the first partitioning item, we're going to use its first character, and we're going to divide up into less than that, equal to that, and greater than that. And then we recurse 3 times, one for the greater, one for the ones that start with the same character, and one for the less. That's the overview of the algorithm. So let's do just a quick trace of the first few recursive calls. So partitioning item again is S. We divide it up that way, and so now we're going to sort the top subarray, the ones that are less than S. So we partition that on B, and then we get down to subarrays of size 1. And now the next thing that we need to do is the big middle subfile. We need to sort it on its second character. So the partitioning item is E this time. So we rearrange those to have the ones that start with SE, the ones that are less, there aren't any, and the ones that are bigger. And so the next recursion is on the third letter in that middle subfile. In this case, it's A. And so we have the ones that are equal. So that's the ones that start with SEA, and the ones that are bigger are the 2 cells, and then move on to the next character. So it picks off the ones that are equal in a kind of a controlled way. And that's an example of the trace for 3-way string quicksort. Now, it's a program that almost writes itself. Once you've seen the idea and you've seen an implementation of quicksort, it's a very minor modification to the 3-way quicksort that we discussed when we were talking about quicksort. So we pick out the dth character. We take D as an argument. We pick out the dth character. We do the regular partitioning element, again picking out just the dth character for each key that we look at. And this is the standard 3-way partitioning. And then when we're done with the partitioning, we do the array of ones that are less, that dth character is less, and the ones that are bigger. And then in the middle, if we had any, we sort the middle subarray and we move over 1 character. That's a very compact string sorting algorithm that performs very well. Now, what about the performance of that algorithm? Well, we talked about standard quicksort performance. And if we randomly order the keys ahead of time, use 2n natural log n string compares on average. And the thing is, though, if you have keys that have lots of long common prefixes, and this happens in lots of applications, then those compares are going to go through all those keys every time. But 3-way string quicksort uses, although the analysis is pretty complicated, it uses only 2n natural log n character compares. So that's an amazing, that's a huge saving for typical common cases. It doesn't have to go through the long common prefixes that usually cause the problem. Now, what about versus MSD sort? Well, MSD sort has this caching problem, and it's got the count arrays, and it's got all this overhead involved maintaining the counts, whereas 3-way string quicksort is still cache friendly because most of the time it's partitioning the same way that normal quicksort is. It's still got that short inner loop, and it doesn't use any extra space. And there's all kinds of applications, for example, library call numbers or account numbers, where long string keys that have non-randomness in them, this algorithm adapts really well to such situation. And the bottom line is, if you've got string keys, 3-way string quicksort is the method of choice. It's simple to implement, and it's going to perform well. We'll probably leave sorting algorithms with this bottom line. And the idea is that now we've got a quite fast algorithm that does a linear arithmetic number of character compares. And that's in random keys in some way. But even if they're not random, it's difficult to characterize really the worst case. But it's more when data is not random, this algorithm will perform well. And even better chance of getting sublinear performance than all the other algorithms. That's three-way Radix Quicksort. Today we're going to talk about tries, which is a data structure for searching with string keys that is remarkably effective in enabling us to deal with huge amounts of data that we have to process nowadays. Just as motivation, when we left off talking about searching algorithms or symbol table implementations, here's where we were. The best algorithms that we examined were balanced red-black binary search trees and hash tables. And with respect to the basic search, insert, and delete operations, red-black BSTs were able to guarantee that we can get those done in logarithmic time, actually pretty efficiently. And for hashing, we get them done in constant time under certain assumptions that we could have a uniform hash function. And also, for hashing, we need to compute a hash code. For binary search trees, we use a compare to function. And another difference is binary search trees, we can support more operations than we can support with hashing. Ordered operations, for example, getting the rank of a key in the tree and other things. And those are terrific algorithms, and we looked at plenty of good applications of those algorithms. But still, there's the question, could we do better? And the answer is that yes, we can do better. As with string sorting, we can avoid examining the entire key, which is going to give us algorithms that can compete and even beat these classic algorithms. So to get started, we're going to articulate an API for symbol tables that's specialized for the case when the keys are strings. So simply we just add the modifier string to our standard symbol table API, and we can take a generic value, but the keys are strings. And then we take all the methods that we articulated before, and for key type instead of generic, we use string. And this is going to allow us to develop efficient algorithms that take advantage of properties of strings. Our goal is to get some algorithms that are even faster than hashing and maybe more flexible than BSTs, and we're going to be able to achieve both those goals. This again is the summary of the running times for when in the case that the keys are strings for red-black BSTs and for hashing. Let's take a look at those. So if L is the length of the string and N is the number of strings, and then also the radix R is going to be a factor later on, but it isn't for these two. Then for hashing, for every operation, we have to compute a hash function, which basically means looking at every character in the string. Actually, in Java, string hash functions are cached, so sometimes there's efficiencies because you only have to, and they're immutable, so you only have to compute the hash function once. And then this is roughly the amount of space that takes into account the table and the string size. For red-black BSTs, the analysis is a bit more complicated. For a search hit, you have to look at the entire string, entire key to check that every character is the same. And then the comparisons, depending on the nature of the keys. For a typical case, though, it's something like log squared n. We had log n comparisons, but usually you have to look at something like log n characters in the key in order to get down the tree. For a search miss, you might find out before you get to the end of the tree, and same for an insert. So the running times are something like this. And then here's some experimental evidence that that we can use to test out these analytic hypotheses. And we'll just look at two examples. One is the entire text of Melville's Moby Dick, which we've used before, and that's about 1 million characters and maybe 200,000 strings. And out of those 200,000 strings, about 32,000 are distinct. And then this is another file of actors from the Internet Movie Database. It's much bigger, maybe 2 orders of magnitude bigger, and it's got maybe about 1 million different words. So we'll want our algorithms to do better than, or at least as well as, red-black BSTs and hashing on these data sets. I think our test is to dedupe these data sets. So that's our challenge: efficient performance for string keys, and try to come up with algorithms that can compete with the best classic algorithms. Now, in order to do that, we're going to look at R-way tries. That's a particular data structure that was invented actually really quite a while ago. This data structure dates back to the 60s. And the first thing to know about it is that the name is based a little bit on a pun. It actually is the middle letters of the word retrieval, but we don't pronounce it tree because then we couldn't distinguish it from binary search trees, so we pronounce it try. And this is a confusing fact of life that we've been living with for many decades now with this data structure. And let's look at what a try is, and we'll look at some examples before we get to the code. So for now, we're going to think of a try as some nodes, a tree structure with nodes, where we store characters in the nodes, not keys. And the other thing is that each node has R children, where R is the radix, the number of possible characters. And there's the possibility of a child for each possible character. Now, in the standard implementation, this is going to involve null links. We have to have a placeholder for each possible character. So there's a lot of null links in tries, and we'll get back to that in a minute. But to get the concept, we'll use this graphical representation where we have characters in nodes and we don't show any null links. And the other thing is, remember, a symbol table is associating a key with a value. So this try is built for this set of key value pairs. And what we do is we store values in nodes that correspond to the last characters in keys. And we'll look at, so that's what these numbers here are, and we'll look at a little more in detail on how this try is built in just a second. So that's the basic idea. We're going to have string keys, we're going to associate values, and we're going to use this this tree data structure, but we're not going to draw the implied null links for now. So for example, in this try, so the root represents all strings, and coming out of the root is one link for each possible letter. In particular, in this try, the middle link is the link to a subtry that contains all the keys that start with S. And we go further down, each time we go by a node, we pick off a letter, so that this link, for example, goes to the try for all keys that start with S, followed by H, followed by E, and so forth. So now, out of all the keys that start with SHE, actually one of them, the one that has just those letters and then ends, has a value associated with it. So in the node corresponding to the last letter, the E, we put the value 0. And so that's how the try is going to look. So just given that definition, then let's look at how to do search in a try. All we do is use the characters in the key to guide our search down the data structure. So let's say we're looking for the key shells. So we start at the root and we go down the S link since we started with an S. Now our second letter is H, so we look to see if there's a non-null link that corresponding to H, and in this case there is. Now our next letter is E, so we look for an E. Now no need to examine the value here because we haven't looked at all the letters in our key yet. So now we look for L, now we look for another L, and then finally we find the S, and when we find the S we look to see if there's a value there. In this case there is a value, and so that's what we return, the value associated with the last key character. So that's a typical search hit in a try. Another way is, so that node was down at the bottom, but if you were doing a search for SHE, you follow the same path, but now when you get to the E, that's the last character of that key, and so we just return that value associated with that node. That is, the search doesn't have to go all the way to the bottom, it might terminate at an intermediate node, and we just return the value associated with the node corresponding to the last character in the key. What about a search miss? Well, there's two cases for a search miss. One of them is we've followed down the tree, picking off the letters in the key one letter at a time as before. And then when we get to the end of the key, we take a look to see if there's a value. In this case, there's no value associated with the last key character. That means there's no key in the data structure that's been associated with a value, so we just return null. Or the other thing that can happen is we can reach a null link. So our key now is S, starts with S, and then H, and then E, and then L, and now our next letter is T, so we look to see if there's a non-null link coming from this node associated with T, and in this case there's no such link, so we return null. That's evidence that that string, there's no key associated with that string in our data structure. So that's a search miss. Now what about insertion? Well, insertion is also pretty simple. We follow two rules. One is, again, we go down links corresponding to each character in the key. If we come on a null link, we create a new node that's associated with the character that we're on. And just keep doing that until we get to the last character of the key, in which case we put the value. So if in this try we're supposed to associate the value 7 with sure, we follow our path from the root to S because our first letter is S, and then H because our next letter is H. And then O, we ran into a null link, so we have to put a node there with the character associated with the character O, so that later searches for this key will be able to find it by passing through that node. And now we move to the next letter, and there's no node again, and the next letter, there's still no node. When we get to the end, then that's the last character in the key, and we put our value 7. And now we've modified the data structure, adding the nodes that are necessary for a later search to go through character by character and find the value associated with that key. So that's insertion into a try. Just to cement all these ideas, let's do a demo of how that tree was constructed from scratch. We have a null try. We're going to start by putting associating the value 0 with the string SHE. We start at the root node, which a null try just has that one node. Create a new node for S, create a new node for H, create a new node for E, associate 0. So the key is a sequence of characters from the root to the value, and the value is in the node corresponding to the last character. This try represents a symbol table that contains just one string, SHE, and associated with 0. Every other string, if you search for any other string in this try, you'll either end at a node that doesn't have a value, or you'll end at a null link. All right, so now let's say we put in the key SELLS, and you can kind of tell where it's going. We made room for it in the try. So we go for S, and now the second letter E corresponds to a null link, so we create a new node. And similarly, we go through and create new nodes for each of the remaining characters in the key, and then associate the value 1 at the end. So now we have a trie that has 2 keys in it, SHE and SELLS. Now our next is to insert SEA. So now we have S, we already have a node corresponding to E, and so now we just have to create one new node, the one corresponding to A, and put our value 2 there. And now we're going to put SHELLS in. So we already have the S, and we already have the H, and we already have the E, so now we have to add nodes for the last 3 letters in that string and associate the value 3 with it. Now we're going to put finally a key that doesn't start with S, so that means we create a new node corresponding to the first letter of that string and to the other letter 2, and then associate the value 4. And here's another one that doesn't start with S, so we create new nodes corresponding to each one of its characters and associate the value 5 with the last one. And now here's SEA. So this is, remember, our symbol table API is associative, which means that if we get a new value for a key that's already in the table, we overwrite the old value with the new value. That's the way, the convention that we've chosen for symbol tables. So that is easily done with tries as well. Now here's one more key, SH, and now we have to add a new node because there's no node that's a child of H that corresponds to letter O, so we have to create new nodes for O, R, and E and associate the value 7 with it. So that's a trie that has precisely 8 keys. If you look for any one of those 8 keys, you'll get the value. If you look for any other string, you'll either come to a node that has a null value or go out on a null link, and so the search would be unsuccessful. That's a demo of trie construction. So now that you have a basic idea of how what tries are and how they work, let's take a look at what's needed to implement them in Java. The key idea in the trie representation for an implementation in Java or any computer language is that instead of representing a node as a character in the node, what we do is we represent the links as an indexed array with one entry for each possible character. And the idea is that the characters are actually implicitly defined by link indices. So just for example, we have this small trie that we built over here. In this case, the root has only one node below it. That's for all the keys that start with S. The way that's represented in the real representation, and this is for efficiency, and it's the way that tries get their efficiency, is we have one link corresponding to each possible letter, and the only one that is non-null is S. So the character S is defined implicitly by the fact that that link that that corresponds to S is not null. Over here, there's from E to A, there's 2 links coming out of E, and the only way that we represent A is by having the first link be not null. If the link corresponding to a letter is not null, that corresponds to having that letter in the node that it points to. So in this case, we have E connected to A and L, so we have the entries corresponding to A and L filled with non-null values. So you can see immediately the correspondence between this trie, the way we've been drawing it, and the Java representation of it, where each node contains 200 or R links, if there's R different letters, and letters are implicitly represented by non-null links. Values go in the node. So for example, in this trie SEA, which is easy to follow down through the trie. We're looking for an S, and S is the 20th letter in the alphabet or so. We index into the 20th position, and that takes us right to S. And then E is the 5th letter, we take the 5th link, and then A is the 1st letter, we take the 1st link. So we can use the character as index into the array of links to quickly travel down the tree. Then when we get to the last character, we can check the value at that node that's stored in the node. One slight complication in the implementation that we encountered before with hashing algorithms and other things, we're going to need arrays of nodes. That's what our links are. So we can't have any generics within node, even though we'd like to. So we have to declare the value to be of type object, and then we'll have to cast it back to whatever type it should be when we return it, and we'll see that in the code. Other than that little complication, this is a quite straightforward representation of tries, and it leads to a very easy implementation. So the keys and the characters are not explicitly stored. They're there implicitly because of the links. And that's a very important point to think about when it comes to implementing and using tries. Given that representation, this code for implementing trie symbol table in Java almost writes itself. It's a symbol table implementation, and this slide has the implementation of put using the same recursive scheme that we've used many other times in building trees. What are the instance variables? We declare R to be 256. As usual in our string implementations, we're working with extended ASCII. And then we have one instance variable that matters, and that is the root of the trie. So tries begin with, all tries start with a null node. So first thing we do is create a new node and put a reference to that node in root. So our empty trie consists of a node that's got remember when you create a new node, we build an array of R links to nodes, and at the beginning those will all be empty links or all null links. So the root points to a node that has 256 null links. Now to put or to associate a key with a value in a trie, we use this instance method that calls a recursive method, again the same way that we've done for other tree construction schemes before. So it takes, the recursive method takes a node as argument and returns a node. So it takes a reference to a trie and returns a reference to the trie that it constructs after associating the key with a value. Just to get started, suppose that our first key has just one character. So in that case, we would call the recursive put for the root with our one character, so our one character key, and call the recursive routine. Now our node is not null, it's the root node. Our key is length 1, and we call it starting at 0. So the first thing that we do is pick out the dth character of our key, so the 0th character, which is our one character, and that gives us an index, whatever letter it might happen to be. Say it's B, then C would be 2, that sort of thing. And then all we do is recursively follow that link, insert associate our key value in the trie pointed to by that link, and then take the link that we get and put it back into that link out of the root node. So the next call, there's nothing in the root.next, it's null, so the next call we get null, so we create a new node. And in that new node, at this point, we've called with d+1 moving to the next character. So now we have d equals 1, which is equal to our key.length. So we associate the value in that node with our node, and we return it. So that return, one level up, will set the link of the new node in the appropriate entry corresponding to the root. Again, once you've learned our normal recursive way of structuring, building tree structures, this code is very natural. So for a longer key, again, thinking recursively, we find if we're supposed to insert the key, associate the key with the value, and we're working on the dth character, we pick out the character at the dth position. We use that to index into the link array, the current node, and then that's the link that we set when we do a put of the new node. So when we start with a longer string in a perfectly empty tree, we create new nodes all the way down and then put their links to their parents all the way up in this recursive structure. And it's a very simple and natural recursive code. So that's the put. That takes a little study, but not so much once you're used to our standard recursive way of producing tree structures. And get is even simpler. So contains and get. So our standard convention is to return null if we have a key that's not there, and that's contains. And the get function is again a recursive procedure that will return a reference to the node, and if that's null, we return null. Otherwise, we can get the value out of the node returned by the recursive procedure, and then remember we had to make our value in nodes of type object, so we have to cast that back to the type value. And the recursive get is very simple to find the node that contains the value associated with a given key, and we're working on the dth character, and we're currently on node x. We just return null if x happens to be null. That means it's not there. If we're at the last character in the key, we return our current node. Otherwise, we get that dth character and we use that to index into the next array of the current node and recursively call the get routine for that node, moving one down the tree and incrementing our key pointer by one. Extremely simple recursive code to do the try implementation. So what about the performance? Well, in a search hit, we simply go down the try, examining all L characters, just using each one to index into a next array at some node, and then go down to the end to see if there's a value there. Search miss, we might have to go all the way down to the last character, but we could also just have a mismatch on the first character and find a null link right away. And actually, typically in a try, in typical applications, we only examine a few characters. So right away, you can see by thinking about a search miss, that try algorithms can be sublinear. We can find out that a key is not in the tree by only examining a few characters. If we don't have any strings in our try that begin with the same few characters as our search key, then it's not there. That's a typical case. Now, the downside of try performance in lots of applications is the amount of space used. There is the problem that every node's got R links in it, and particularly down at the bottom, the leaf nodes that correspond to the last characters in keys, no prefix in the key in the try, there's going to be null links. Now, it is possible in a huge try with lots of strings that are short, sharing common prefixes, to actually use much less space than this. but the R null links at each leaf is a real problem in some applications, and we're going to take a look at how to deal with that. So the bottom line is for symbol tables with relatively small numbers of string keys where the amount of space used by the null links and leaves is not a problem, then we get a very fast search hit and even faster search miss. But we burn up some space. That's the bottom line about try performance. And just a typical application, maybe you get a job interview question about what data structure do you use for spell checking. And this is just an example to show how effective tries can be for such an application where all the words are 3 letters. And the solution is build a 26-way try. So the spell checking usually there'll be pre-processing to strip out everything but the lowercase letters that make up the word. So you can build a 26-way try that will immediately tell you whether you have a misspelled word or not. Another interesting thing about tries is that deletion is very easy. What do we do to delete a key value pair? Well, you find the node corresponding to the key and set the value there corresponding to null. So that's easily done. So we want to delete shells, we cross out the value there. And now there's 2 cases. One case is this one where that node, now we set its value to null and it's got all null links. There's no reason for its existence. So it wouldn't have been created except for the fact that we inserted shells. So if the node's got all links, you just remove it. And then just delete it, and then when you go back up the tree, which you do because you got down there, every node that you touch, you check. If it's got a null value and all null links, just delete it. And you keep going until you find one that has either a value or a non-null link, and then that's when you can stop deleting nodes. So it's pretty easy to delete a key value pair in an R-way try, and that's unusual for other search structures that we saw. The deletion was a significant challenge to implement often. So our challenge is to find a way to use less memory, particularly because nowadays many strings are built with Unicode and the number of null links in a try would be truly huge. Again, we talked about this with radix sorting, that a lot of programs broke when the switch went from ASCII to Unicode. And any program that used this representation for tries certainly broke. So that's an introduction to tries with R-way tries. Next, we're going to look at ternary search tries, which is another data structure that, new data structure that responds to the problem of too much memory space used by R-way tries. This is a very easy to describe and implement data structure, and it came out of the same paper that John Bentley and I wrote in the 1990s when we developed the 3-way ternary quicksort. The idea is now we're going to actually store characters in nodes and values, but we're not going to store whole keys in there, just characters. But we're not going to use this idea of a big array where a non-null link is the implicit value of a character. We're actually going to store the characters. But what we're going to do is make each node have 3 children. Not 2 like in a binary search tree, and not R like in an R-way try, but exactly 3. And the three children are for the trie corresponding to smaller keys, the trie corresponding to trees that start with the same character, and the trie corresponding to larger trees. And just given this description and experience with many of the data structures that we've talked about already in this course, many of you could go off and implement this data structure, and we'll see how simple the implementations are. But still, let's work through precisely what the data structure looks like, because sometimes the recursive code looks almost too simple and kind of mass understanding. So this is the representation of tries that we started with. And all we do with ternary search trees is it's almost like having a binary search tree representation of the non-null links for every node. In this case, we're going to have an S at the root, and that depends on the order in which the keys are inserted. And the key idea is the middle link coming off the root node is a link to the TST that have all the keys that start with S, with the S stripped off. Now, but for the left and right links, those are for keys that start with some letter that appears before S on the left and after S on the right. And then, say on the left, the node for B is, if you go down this link, it's all the keys that start with B. Otherwise, the B is just to divide the ones that are less from the one that are bigger, and so forth. And again, if you search for a key by, say, search for SHE, so that's going down middle links and matching keys, then some nodes will have values associated with them. That's the value associated with the last last character in the search key. So that's what the data structure looks like. And I began to describe the search algorithm. It's quite simple given the definition of the data structure. Again, we follow links corresponding to each character of the key. If we have a character that's less than the character in the node, we go left. If we have one that's greater, we go right. And if it's equal, we move to the next character and take the middle link. So this is an example of a search for SEA. Start with S, that's a match. We take the middle link. Now the next character is E. That's a mismatch, and E is less than H, so we go to the left. Now we find a node that has E, and we didn't update our pointer into the key character because we didn't find a match. So we're still looking at the E, and now we can match that E, so we go down the middle link. Now we're looking at the A in the search key, and that's less than L, so we go to the left. Now we're still looking at the A in the search key, and that's a match, and it's the last character in the key, so we return the value associated with the last character in the key. So it's the same basic algorithm that we used for tries, except we just have a different way to decide whether we matched a character. We explicitly store characters in nodes. We follow middle link on a match and update the pointer in our key character. Otherwise, we follow the left or right link because we know that the key has got to be found in the left or right subtree. And each node has exactly 3 links. So here's an example of search in a TST. Again, this is the example I just talked about in a dynamic form. So the S is the first character in the key, matches the S in the first node in the tree, so we take the middle link and move on to the second character in the key, which is E. Compare that against H, it's not a match. In fact, it's less, so we go left. So now we're still looking at E and C, and it's a match with the character in the node that we're currently processing, so we take the middle. And now move to the next character in the key, which is A. And now we take A compared to L, and A is less, so we go left. We're still looking at the A. Didn't update it because it's not a match, and now it is a match, and it's the last character in the key, so we look at the value, and that's the value we return. What about unsuccessful search? Well, let's see how that works. So for shelter, it starts with an S, so we take the middle link. Second, and move to the second character. Second character is an H, and that's a match, so we take the middle link and move to the next character. Third character is an E, and third character, and that's also a match, so again we take the middle link and move to the next character. Fourth character is an L, that's also a match, so again we take the middle link and move to the next character. Now the next character is a T, which is not a match, so we want to move to the right, but moving to the right takes us to a null link, so that means that shelter is not in the TST, and so we return null. Again, at every step, what we do is completely well defined, and any search for a key that's in the TST is going to return the associated value. Any search for any other key is either going to go out on a null link or end on a node that involves a mismatch. With that basic idea, let's take a more detailed look in a demo of how the tree gets constructed. And following through this demo will give you a pretty good feeling for how these trees are constructed. So we're going to associate the value 0 with the string SHE. Again, every time we move to a new letter, we have to create a new node until we get to the end of the key, and in which case we associate the value with the node that contains the last character in the key. So that's the starting point. Key is a sequence of characters down middle links that goes to from the root to some node, and the value is in the node that corresponds to the last character. How do we put a new one in this tree? In this ternary search try, first character is S, so we go down the middle. Next character is not a match, we go to the left, and it's a null link, but we have a node that we want to put there. That's the one corresponding to the second letter in cells. So we do that, and then we make nodes with middle links going until we get to the last character in cells, and we associate that with the value 1. So what about SEA? Let's see how that one works. First character is S, so we take the middle link. Second character is E, which is less than H and not a match. So we move to the left and continue looking for the E. Now at this node we find the E, so we take a middle link and move to the next node, next character, which is A. A is less than L, it's not a match, so we go to the left, that's a null link, and that's where we put our A, and we associate it with the value 2. Okay, here's shells, so we have a match at S, go to the middle link and go to the next letter, match at H, middle link, next letter, and then we go down and add the 3 nodes corresponding to the last 3 letters, and put a 3 at the node corresponding to the last letter. Now BY, we look at S, not a match, it's less, so we're going to go to the left, that's a null link, that's where we put our first character, and then we go down a middle link to add the node for the last character, and then associate the value 4 there. And then D is a similar thing on the right, a new node for the T, and then H and E, and that gets associated with the value 5. SEA, again, it's associative, so we do the search. So S is a match, so go down the middle link and move to the next letter. E is less than H, so we go to the left and keep looking for E. Now we find E is a match, so we get down the middle link and move to the next letter. And that's A, which is less than L, so we go to the left to look for A, and there we find it. and we're building an associative symbol table, so we update and overwrite the old value with the new value 6. SHORE, we match the S, match the H. Now we're on O. That does not match E, so we go to the right and keep looking for O. We don't find it, so we create a new node for O, R, and E, and then put the value 7 in the value associated with the last character in that key. So that's construction of a ternary search tree containing 8 keys. So let's take a look at a slightly bigger ternary search try. So here's our example with 3-letter words. Now for that example, we didn't show all the null links, but there's lots of null links, 26 null links in each leaf for this 26-way try. And there's other null links higher in the tree, and actually counting up, there's over 1,000 null links in this tiny 26-way try. But in a TST, it's got about the same number of nodes. It's actually got more nodes because it's got one for each character, and the other ones correspond to links, but not that many more nodes. But the key thing is it has many fewer null links because there's only 3 links per node. And this effect is obviously going to be much more dramatic when R is much bigger, like a 256-way try, or even a Unicode 65,000-way try. That's the key benefit of TSTs, that they're much more space efficient than R-way tries for large R. So let's take a look at the implementation in Java, and then we'll look at the code, and then we'll talk some more about performance. Well, the representation in Java is very straightforward. As I said, many of you could code this up just from the description. What does a node have to have? It's got to have a value, it's got to have a character, and it's got to have references to left, middle, and right TSTs. And that's what it's built from. So whereas the standard try representation has an array of links with characters implicit, a TST has explicit characters with only 3 links per node. So that's the TST representation, and then given the representation, the code follows almost immediately. With our standard setup, if we're supposed to, we call a recursive routine, giving the root as first argument and give the tree returned, and give a reference that back to the root. So our recursive routine takes a node and returns a node. And for most of the time it doesn't do much, but when a new node is created, this this code is effective because any link we go down will replace with the link that we got back, our standard setup. So the recursive port routine, if we're at character D, we pull out the dth character. Once we've done that, if our node is null, we create a new node and give it that character. And now we test our character in our search key against the character in the given node, either the one we just created or the one we happen to be on. If it's equal, it will fall through to test if we're on the last key. If we're not, if we're on the last character in the key, we just reset the value. If it's equal and we're not on the last character in the key, we go down the middle link, and we replace that link with what we get by going down the middle link, but moving to the next character in the key. Otherwise, we go either down the left or right link under the same circumstances without moving to the next character in the key. So that's extremely straightforward code for put in ternary search tries. And again, get is even simpler. It's a similar setup that we've used several times before. Use a recursive routine that returns a node, and we pull our value out of that node. We don't have to cast in this case because we don't have any arrays, and our node just has the value type in it. And if we get a null node back, we return null that it's not there. The recursive routine will pull out the character. If it's less than our search, if our search character is less, we go to the left. If it's greater, we go to the right. And if it's equal, and we're not at the end of the key, we go down to the middle and move to the end of the key. If it's equal and we are at the end of the key, we return the node, and either that node is going to contain a value or it's not, but that's what we return. So extremely straightforward implementation of both get and put for ternary search tries. This adds this line to our table where the amount of space taken for ternary search tries is just 3 lengths, plus a value character in each node. Similar to what red, black BSTs and hashing would use. So no space disadvantage. Determining the cost of search hits and search missed, these values are given for random keys, and they're the subject of deep analysis. But it's not too many, let's put it that way. And our experimental results bear that out. So for a search miss in a ternary search try, you don't have to look at the whole key. Usually you look at many fewer characters than the whole key. And actually, these results are for typical or random, but actually TSDs really shine in the case when the data is not random. They very well adapt to the data. Text written in the English language is not really random, and you can see that ternary search trees actually outperform both hashing and red-black BSTs for our benchmark, which is deduping these big text files. Now, you can go ahead and try to get worst case guarantees by using rotations to balance the internal binary search trees corresponding to each character in TSTs, although that's probably normally not worth the trouble. But the bottom line is that TST is at least as fast as hashing for string keys, and it's space efficient for sure. And it's pretty easy to speed it up. The idea is to speed it up, that works extremely well in practice, is to use R-way branching at the top of the TST. So rather than fool around with the first couple of characters, simply do a big branching at the root. You could do R-way branching at the root, F26, but in practice, proven works fine to do, say, R-squared way branching at the root, and immediately take care of the first 2 characters, which is the common case. And then get down to small TSTs. And there's variations of this that you might imagine, but this is a really simple one that almost always works. You have to deal especially with 1- and 2-letter words, and we'll leave that for exercise. But with that change, now we get an algorithm that is definitely faster than hashing and red-black BSTs. For our benchmarks, and that'll turn out to be the case for many applications. So just to summarize, what are the trade-offs between TSTs and hashing? For hashing, you have to examine the entire key in order to compute the hash function. We talked about examples where people try to skip doing that and wind up with performance problems. Not much difference between a hit and a miss in a hashing. And there's a lot of reliance and maybe difficulty of implementation depending on the hash function. And also, hashing is really only good for search and insert. The other kinds of operations that we like to perform in symbol tables when there's order in the keys. It's not supported by hashing. With TSTs, it only works for strings, or if you have keys that are numbers, then you can rework them into strings or string-like things. And that's a restriction, but it does cover a huge number of applications. It only examines the key characters that it needs to, and in particular, a search miss might involve only a few characters. So in typical applications, you'll get sublinear performance in TSTs. You can get searches done without looking at the whole key. The other thing is there's the ordered symbol table operations you can easily support with TSTs just by extending what we did for binary search trees. And even more important, there's other interesting operations that we can add for string keys that are very useful, and we'll see applications and implementations of these in just a minute. So the bottom line is that this data structure is a relatively new data structure, but it's better than the classic ones for important applications. It's faster than hashing, particularly for search misses, and it's got more flexibility even than red-black BSTs, and that's what we'll talk about soon. But that's an introduction to TSTs. Now we're going to finish up by looking at some extra operations that are supported for string keys when we use tries. We're going to look at a couple of character-based operations that are quite useful and can be supported by the string symbol table API with tries. One important one is prefix match. So that's given a prefix like, say, sh, what we want is the method to return all the keys that start with that prefix. In this case, it would be shells, shore, and she. Another one is so-called wildcard match. So that's when we don't specify one of the characters or multiple of the characters. So we put a dot to say we'll take any key that matches the other characters, and we don't care what that one is. So .he would match she and thee. And another one is so-called longest prefix. So now we've got a long key, and we want to find the best match that's in our symbol table that matches that key. The key in the symbol table that has the longest match with our key. So in this case, the one that's the longest prefix of shell sort is shells. And later on, we're going to see applications of some of these. And the important idea for now is that these are easy to articulate, and not only that, they're easy to implement with tries and ternary search tries. So we're going to take our standard API and add these four methods. Well, there's keys that returns all keys, and as is our usual practice, when we have a lot of things to return, we're going to return them as an iterable, so the clients can just iterate through what's returned. That's usually what clients want to do. And then we have keys with prefix, give a string s, and the iterable will return all the keys in the symbol table that have s as a prefix. Client wants to find the associated values, they can do gets to get the values. And then we have keys that match, so that's where we allow dot to be a wildcard in s, and we want to return all the keys that match s, taking dot to be a wildcard. And then longest prefix of s is the key in there, that's the longest prefix of s. We're going to see later on this particular one plays an important role in a more complicated algorithm. We could also go ahead and add all the ordered symbol table methods that we considered when we looked at binary search trees like floor and rank. We're not going to take time to do that right now. It's very straightforward. One thing that we haven't really talked about, but it's a good warm-up for the kinds of methods that we're going to look at for these implementations, is ordered iteration. And this is try traversal. So we're going to do an in-order traversal of the try. That is, visit the left, visit the middle, visit the right. In that traversal, we can maintain the sequence of characters on the path from the root to the current node just by adding a character when we go down and removing a character when we go up. And when we encounter values, then we can put out the characters that we have, and that's a way to pull out all the keys in the try. So for example, in this case, we go down and we have B, and then we hit the Y, so we can output, say onto a Q, we can output by. And then we go back and we have S, E, and A, and we find a value, so we go ahead and put out the A. Now we drop the A and do the L, and SEL, and LL, and then we get to that S, we have a value, we can put out cells. And then we can drop these, get back to the S, and get to SH, SHE, find a value, and put the SHE on the Q. LLS, and put shells on the Q. Drop all those values down to the H and get SHO, SHOR, SHORE, find a value and drop sure onto the Q. And then finally T, TH, and THE, and find a value and put D on the Q. So it's easy to, very easy to keep track of the sequence of characters on the path from the root to every node, and at every node check for a value and throw it on the queue. That's ordered iteration. And the implementations of these extra operations are just based on modifying ordered iteration. So this is an implementation of keys, which is essentially the operation that I was tracing on the last slide. So if the client wants keys, we make a queue, then we call a recursive routine that collects all the keys in the try starting at that node, and given a null string, which is the sequence of characters on the path to the given node. When that recursive routine returns, then we just return the queue. And the recursive routine does encode what I said in words most of the time. This is for a try. You could do the same thing for a ternary search tree with just a little more code. So for every character, we just move down the try for that character, add the character to the prefix, and also pass the queue along. If we get a non-null value, we put what we have on the queue. When we get null, we return. So a very simple implementation of ordered iteration, recursive. So that's the implementation of the keys method. Prefix matches and other things like that are going to work just by modifying that. And you're familiar with prefix matches. When you type nowadays in your browser a search function, you're getting a prefix match of all the things that you typed or other people have typed that matches those strings. And you find that also nowadays when searching in your address books. It's a quite common function nowadays. So let's look at how that looks in an R-way try. So what about finding all the keys in a symbol table that start with a given prefix? Well, we just search for that prefix and then
then just do a collect at the keys in that subtry. So that's very straightforward. So you get the node that is the one you get to by starting with that prefix, and then you just call the recursive collect, and boom, you're done. Extremely simple implementation of keys with prefix in an R-way try. What about longest prefix? And here's one that is very heavily used in the internet. If your query strings are IP addresses on the internet, and you have some given destination IP address, the router has a lot of IP addresses in a routing table, and it wants to choose the one that would get you as close to the destination as you can, so it's going to choose the longest prefix. So if you want to get to 128.112, you can think of these as hops on the way to where you want to get, where 11 is the final destination. And essentially this table says it knows how to get this far, and so that's what it wants, is the longest prefix. Longest prefix match of, say, this one, well, it doesn't know how to get any further than 112, and this other one only to 128. And this operation gets performed extremely often on the internet nowadays. Just a quick note, it's not the same as the floor function. It actually is a kind of a string operation. These things actually usually on the internet, they're not represented as strings, they're represented as binary numbers. But in machine or assembly language implementation, tries are even easier. And you can just take a bunch of bits and use them as index into a table to move down the try. And actually tries are pretty old because it was so easy to implement data structures in that way in the past. You'd be surprised at how much of our computational infrastructure is built by programs, or consists of programs that are written in machine or assembly language that can make really efficient use of low-level representations like this. But it's also useful in high-level languages. So what does it look like in an R-way try? Well, all we're going to do is just do a search, and then we're going to keep track of the longest key that we encountered. So we have a path, and on that path, there's the most recently seen value. That's the longest key that we found. If we end at a null link, that's fine. If there's a value on that node that's got the null link, that's the value we're going to return. So that's a very straightforward implementation, just keeping track of the longest key encountered on the search for our key. That's the implementation of longest prefix of in the usual setup of making a recursive call, and this code is quite straightforward. Application of this one is so-called T9 texting. Now, when we do a course like this, we try to keep up with modern technology, and modern technology is moving almost as fast as we can. There are lots of young people who really don't know about texting with keypads anymore, but there's a certain range of 5 or 10 years where people got extremely adept at doing so-called multi-tap input, where the only keys on the phone were the 9 keys to dial numbers, and then we had 3 letters associated with each number, like on old dial telephones, and to enter a letter, you had to, like to enter an H, you had to tap twice, because that's the second letter on the 4 key. You had to tap 4 twice, and like that. So the so-called T9 text input would use the kinds of algorithms that we're talking about, to make it so that maybe you didn't have to do multi-tap. So rather than type 2 4s, it would do a try type search to figure out which word that you typed. And that looked good to us as a potential application for a while. I'm glad we didn't spend too much time on it. If you study this keyboard, maybe you'll see why. Well, you think about how to implement it. But once we get into it, we realized, Kevin realized, there's no S on this sample keypad. What happened to the S? So what are we going to implement because there's no S there? So what exactly are they doing? Well, this is maybe a bit of a fantasy that this is the response that he got. Maybe these people lived in a world with no S's. Well, anyway, we've moved on from tries, from that type of way of entering text. But I still want to mention just a few more ideas because the basis behind tries and ternary search trees is still out there and is still really an important part of our infrastructure. And there's some really great algorithms that we just don't have time to cover. One of them is an old algorithm called Patricia. This one is a really interesting and intricate algorithm, particularly when implemented for binary tries where you just do a bit at a time. And people, again, implemented this kind of algorithm in machine language and got extremely efficient performance. If we cast it in the R-way tries that we've talked about, it's really the best way to think about it is a way to remove one-way branching. Seems wasteful to have all these nodes that just have one branch. And so one of the main ideas behind Patricia, there's others that don't really show up in the high-level representation we're using. But one of the main ideas behind Patricia was rather than associate a character with each node, associate a sequence of characters with each node, so you just don't have any one-way branching. Implementing this, it's maybe one step beyond this course, but maybe it's within what we could do in this course. We're just not going to take the time to do so. And you'll find implementations that in practice avoid the one-way branching that are used in many applications, performance-critical applications for searching nowadays. I already mentioned IP routing tables. There's probably no piece of code that's executed more often than that one, and that's based on a try-type algorithm. And we have these other applications listed as well. It's got some other names too. Another thing is so-called suffix tree. That's building a tree from a suffix table. We talked about having, for the suffix sorting, we talked about applications. You can also build a search structure from suffixes of a string. And that admits all kinds of fast string processing applications. And again, usually eliminate one-way branching in suffix trees. And also, amazingly, you can get them constructed in linear time. And there's all kinds of interesting applications of suffix trees. Probably the most important nowadays are in computational biology databases. Again, extensions of the kinds of algorithms that we've talked about today. So I think the bottom line for considering string search trees is that it's a real success story in algorithm design and analysis. It's a number of clever algorithms that really have made a difference in the kinds of operations that we can perform, in the amount of data that we can handle in modern applications. We started with red-black BSTs, which is a pretty good solution for general symbol tables, and also hash tables, which are also widely used. But with tries and ternary search tries, we have a performance guarantee where we only have to really access log n characters. And when you think about that, that's even when n is huge, that's going to be a pretty small number. So say we're looking among billions so billions of things, log n, even if you only have two-way branching, would be 30. And when we have 256-way branching, it's way smaller. And that's just the number of, so it's the number of characters accessed. And really the bottom line is, if you can set things up nowadays, even on the internet, when there's huge amounts of data out there, you can set things up so that you can only need to look at maybe 100 bits to get at anything. When you think about 100 bits, that specifies 2 to the 100th of possibilities. 2 to the 100th is a huge number. There are not 2 to the 100th pieces of information, even on the internet, even will ever exist on the internet in the life of this galaxy. But with just 100 bits, which really isn't too much, we can search for anything efficiently. And that's an amazing success story for algorithm design and analysis. So that completes our look at tries and ternary search tries.